Wow, sorry. I didn't want to distract your conversations. Um, no, no, we're ready to start. Welcome to day two. I hope, was yesterday good? Did, awesome. Um, yeah, I think we had a few gremlins, but not too many. So we were a little more nervous than normal. New venues for both the event and the banquet last night, but I think that worked out fairly well as well. Just a quick reminder for everybody, there's a bunch more booths on the second floor and some posters, so mosey up there and take a look. There's some good stuff. And there's great views from the third floor if you want to go there and check those out. Okay, so let's get the day started. We have another great day of presentations, and we're going to start with a keynote. And as you know, or maybe you don't know, but NASA has been a tremendous supporter of CubeSat from the beginning. The first U.S. launch was GeneSat in 2006, and that was a NASA mission, and it really changed the U.S. government and industry's perspective on what these satellites could do. The fact that NASA jumped on board so soon was great for us, and they've been awesome ever since. You know, Alana is putting all our student missions up in orbit, and many of the high technology systems that we're trying to fly. So in that spirit, we brought Jim Ryder from the NASA headquarters to come here and tell us about some of his ideas about what CubeSats can do. He's the Deputy Associate Administrator for Programs within the Space Technology Mission Directorate. So he's actually responsible for budget and for allocating funding for technology development. So you may want to have a talk with him when you see him afterwards and have some influence. Before that, he was at NASA Marshall, and he's worked on all kinds of things. I'm looking at his resume, and I have to just like pick a few. But he's worked on asteroid redirect mission, on Orion, on the multi-purpose crew vehicle. Before that, he was working on shuttle and a variety of other systems. So he knows his way around putting things in space, which we really like people like that, because eventually we need that 10-minute ride to make our systems work. He got a degree from the University of Minnesota in Minneapolis in mechanical engineering, and he's got a number of awards with NASA, including 4 NASA medals, Silver Snoopy Award, and a Space Station Award of Merit. So without further ado, Jim, the floor is yours.
I'm amazed anyone's awake after the festivities last night, this early. And thank you, George, and thank you for the warm reception. It's really a great pleasure that I join you here, and it's part of the 14th annual CubeSat Developers Workshop in a really beautiful campus. It's my first time here, so it's great to see it. And this is the birthplace of the CubeSat. Well, I know there was another university a little farther north that contributed some too then, but I can't remember its name. My goal today is to talk about NASA's role in small spacecraft technologies today and in the future. That's what I thought I'd try to talk about. This is really a great time to be in the space industry, I think. It's an unprecedented level of commercial space funding and interest. Nowhere is that more evident than in the small satellite field, and especially with CubeSats. What started here in 1999 as really an exceptional hands-on education tool for university students is now exploding into a global ecosystem. Based on a study completed earlier this year by the IDA Science and Technology Policy Institute, or STIPI, it's estimated that there will be over 3,600 small satellites launched in the coming decade, and that's probably low. The commercial imaging market by itself is expected to grow from a $15 million industry in 2015 to a $164 million industry by 2020. We don't think about this, but the emerging unmanned aerial system market is expected to be a $20 billion opportunity for small sats. Further, there's $22 billion in revenues anticipated by 2025 for small sat launch and manufacturing alone. While private funding for small sats may soon exceed government funding by an order of magnitude or more. There was nearly twice as much venture capital invested in the space industry in 2015 than the previous 15 years combined. So it's kind of numbers like these that has caused us to re-examine, well, what should we do at NASA? And how do we best invest in the CubeSat market to further both NASA's and the nation's interests? And so I'm here to kind of talk about that and our thinking. Worked once. I heard yesterday was fun. See, our so first I thought I'd talk a little bit about, I'm space technology, and so we'll talk about that for a couple slides, and then we'll get into a little bit more of the CubeSats. So first, our goals are to enable a new class of NASA missions beyond low Earth orbit, deliver innovative solutions that dramatically improve technological capabilities for NASA and the nation, develop technologies and capabilities that make NASA's missions more affordable and more reliable, invest in the economy by creating markets and spurring innovation for traditional and emerging aerospace businesses, and engage the brightest minds from academia and small businesses. So that's why we're here. We do much of our investing by establishing partnerships with both industry and academia. This includes well over 700 partnerships since 2011 that have involved more than 130 U.S. universities that have led or are partners on more than 550 awards. So the way we organize our portfolio in space technology is pretty much along the lines of what we call technology readiness level scale. So our early stage portfolio, I think I have a, on the left part of the scale or low technology readiness levels, they range from research grants to universities to conceptual studies that what we want is for innovative solutions with substantial potential benefit, and the only requirement we put on them is you have to obey the laws of physics. And innovation funding for our center research activities, and many times they, in turn, partner with universities and businesses as well. Commercial partnerships portfolio, which is up here, engages in partnerships in a wide variety of ways, including small business innovative research, technology transfer activities, suborbital flight opportunities, and small launch vehicle technologies. Our game-changing development program seeks to advance technologies from breadboards in a lab to demonstration in a relevant environment and ready for infusion into a mission. In our technology demonstration missions program, demonstrate technologies at a system level, either in space flight or integrated ground tests. And then finally, the one that we're here to talk about, especially primarily, is our small spacecraft technology program, which focuses on developing and demonstrating capabilities for small spacecraft. And our leadership team is here enjoying these 3 days of conference or workshop. And so while small spacecraft technologies is where our focus is for this area, we can and will invest in small sats really across our portfolio. So NASA pursues small spacecraft activities in 3 areas that align with our mission directorates. Space technology, that's our mission directorate. We're responsible for developing and demonstrating new small spacecraft technologies and capabilities for NASA's missions in science, exploration, and space operations. Exploration is responsible for providing launch opportunities to the U.S. CubeSat community and sponsoring missions to address strategic knowledge gaps for exploration. And science is responsible for conducting scientific investigations and developing precursor instrument technologies for future science measurements while providing mission opportunities for secondary payloads. CubeSats really can't totally replace larger scientific instruments, but there are many areas where they can address high priority science goals, including things like solar and space physics and Earth science applications that explore the Earth's atmospheric boundary region. That's a really good area for CubeSats because what you need is, whatever you have, you're going to lose. It's fairly short life. So CubeSats that can investigate that area is a great opportunity for those that really can't, it's hard to reach any other way. Planetary science, where you do some in situ investigation of the physical and chemical properties of the planetary surfaces or atmospheres, and you study them by deploying CubeSats from the mothership. So they get a ride there, and then they get deployed and do their investigations. Astronomy and astrophysics is also a good area, things like low-frequency radio science, and biological and physical sciences in space, where CubeSats offer a platform to help understand the effects of the environment encountered in deep space, such as microgravity and high levels of radiation, and many other possibilities. There are really too many CubeSat missions that NASA is pursuing to describe them all in this presentation, but what I can talk about is some of the key missions to try to demonstrate the diversity of our portfolio. And several more of these are being discussed over the since yesterday and throughout the workshop. Tropics is a science mission that has the objective to study the insides of hurricanes with a constellation of 12 3U CubeSats. It's targeted for launch in 2019, and it will use radiometer instruments that will make frequent measurements of temperature and water vapor profiles throughout the life cycle of individual storms. And I think MIT talked about yesterday leading up to this activities leading up to this mission. Cygnus science mission, it stands for Cyclone Global Navigation Satellite System. It provides a new measurement technique and mission architecture enabling frequent and accurate measurement of ocean surface winds to improve hurricane forecasting by GPS reflectometry. Traditional remote sensing of surface winds can't penetrate the precipitation due to scattering and attenuation. But the 8 small spacecraft will enable frequent and accurate measurements that can be combined with global precipitation measurement data for coupled observations to fundamentally improve really our tropical cycle intercore dynamics and energetics. Cygnus was launched last December 15th. And it's successfully completed now the development and on-orbit commissioning phases of its mission as of March 23rd, and it's now moving into the science operations phase. Now going on to the moon, Lunar Ice Cube. Lunar Ice Cube exploration mission, its objective is to prospect for water and other lunar volatiles using a compact infrared spectrometer. It's a 6U spacecraft, and it will be deployed by the Space Launch System on the inaugural EM-1 flight. Lunar Ice Cube uses really kind of an innovative radio frequency ion engine with iodine propellant combined with a low energy trajectory to achieve lunar capture. The mission team is comprised of university, NASA, and private sector partners, and they're now preparing for the critical design review. It's kind of the last major design review before production. And I believe there was also a talk on this one yesterday. Skyfire. It's also an exploration mission, consists of a 6U CubeSat that will also be deployed from EM-1, the first SLS mission, with the purpose to use visible and mid-infrared lunar surface mapping to collect data on the thermal environment and as a precursor for low size, weight, and power common sensor suite for relative NAF. This is a TIVAC commercial bus assembly being adapted for deep space. The CubeSat Launch Initiative. It's NASA's initiative that provides access to space for small satellites developed by NASA centers and programs, educational institutes, and nonprofit organizations, giving CubeSat developers access to a low-cost pathway to conduct research in science, exploration, technology development, education, and operations. Since its inception in 2010, there have been 152 CubeSat missions sponsored and in development from 85 unique organizations representing 38 states and the District of Columbia. The goal is to hit every state. 46 CubeSats have been flown on 12 missions, with 52 more manifested for flight. The payload focus areas to date include technology, 64% of them, scientific research, 51%, and education, 57%. And if you're kind of wondering about the numbers, well, naturally, several of them got counted in a couple categories. The CubeSat Launch Initiative missions have included things like a BisonSat, which was the first CubeSat built by a tribal college, a TJ3 Sat, which was the first CubeSat built by a high school, and then The STM Sat-1, the first CubeSat built by an elementary school. So next preschool is going to be coming, I think, pretty soon, I think. So I would really appreciate it if you'd attend this afternoon's presentation on the CubeSat launch initiative. It's a very successful team. Still working. So now I want to talk about some of the space tech programs that engage in small sat activities. Our primary investments, as I said earlier, are through our small spacecraft technology program, whose objective is to expand the U.S. capability to execute unique missions by rapidly developing and demonstrating capabilities for small spacecraft. And that includes things like enabling new mission architectures, expanding the reach of small spacecraft to new destinations, and augmenting existing assets and future missions with small spacecraft. Our Flight Opportunities Program advances U.S. capabilities by fostering the operational readiness of innovative space technologies and commercial spaceflight services. So it includes supporting flight demonstrations of promising technologies from industry, academia, and government through testing on commercial suborbital platforms, and establishing public-private partnerships to accelerate technologies that enable frequent lower-cost launch of small satellites to orbit. We ourselves have a lot of problems with getting access to space, and it's an area that really needs investment, but it's starting to grow very well. We also have a CubeQuest challenge ongoing in our Centennial Challenges program, where we offer up to a $5 million total prize purse that will be awarded for the development and demonstration of CubeSats for deep space operations. We recently awarded, we have 4 different ground tournaments, and we're on the we just finished the 3rd one. And there was 5 winners, each got $30,000 as part of that top scoring team and going on to the finals. And 4 of those 5 were university led. The ground tournament 4 winners will be announced by mid-June, and then with 3 CubeSats will be provided a ride to cislunar space on the first SLS flight. And then space technology, we just recently announced our Phase 1 Small Business Innovative Research, or SBIR, awards about 2 weeks ago. And that included small spacecraft awards in propulsion systems, communication systems, power and thermal control, structures, mechanisms, and manufacturing, avionics and control, active microwave remote sensing, cryogenic systems for sensors and detectors, and particles and field sensors. We had a total of 25 awards were made in the small spacecraft area, plus an additional 5 awards in small launch vehicle technologies and demonstrations. And we have, so that was through this year, and then we're getting ready for next year's call again. The call comes out, it'll be in November timeframe with the responses due by January. And what we're setting up is a 3-day industry day at Ames Research Center on June 25th to 27th. And the intent of that is to provide in-depth information about the SBIR and processes and opportunities. And it'll be an opportunity to talk and interact with program experts, technologists, and fellow industry and university partners. And so we were really looking forward to getting strong feedback before we finalize our topics for next time. This time we said, well, as burgeoning as the small sat industry, it was a major push for us this year, and we'll debate again, seeing the very strong success and strong input we had this time. And then finally, I'd note that picture. That's actually a picture up there. It may not be obvious from you. And it's showing this payload stage separation during the up aerospace flight, which was conducted through our Flight Opportunities Program, of the small spacecraft technology-sponsored Mariah sample return capsule. The camera view is from the already separated nose cone looking back. Okay, so what I want to do now is talk about several of our small spacecraft technology demonstration missions. I'll start, let's see, the first column, then the second column. What the heck? The Optical Communications and Sensor Demonstration, or OCSD, it's an aerospace mission using 2 1.5U spacecraft that will demonstrate 200 megabits per second optical downlink, as well as some proximity operations and a non-optical crosslink between the 2 satellites. So this will further both optical communications and swarm technologies, basically, on this mission. The spacecraft are ready for flight and an October target launch date. The CubeSat Proximity Operations Demonstration, or CPOD, is a TIVAC mission that will conduct autonomous proximity operations, relative station keeping via cold gas attitude control, and a docking event with 3U spacecraft. The spacecraft are also ready for flight with an August target launch date. These have been around, actually they've been ready since last summer, so, or even spring. So I'll have some short 30-second videos at the end of these two demonstration missions at the end of my presentation. The third one there is the Integrated Solar Array and Reflect Array Antenna, or ISARA. It's a JPL and aerospace mission using a single 3U spacecraft that will demonstrate a compact flat panel array that can replace parabolic dishes. They're which of course are much harder to package and deploy. And so it can do that and still achieve 100 megabits per second downlink. Unlike optical comm, the system can be used with existing ground stations and can also be used to replace parabolic dishes for instruments like radar. The spacecraft is ready for flight, awaiting launch, and all these you can see out at our display outside. The Pathfinder Technology Demonstrator, or PTD, has a goal to conduct a series of low-cost demonstration missions that will test new technologies derived from public-private partnerships, from our SBIR projects, and from other sources. The 6U TIVAC bus that we selected is really a very capable system with 3U of payload space available. The spacecraft is based on a design that TIVAC is building for several other customers, and they're here. The first flight's payload has a BUSIC system targeting a 2018 launch, and I believe there was also a discussion on this topic yesterday. And then next, the THEA synthetic tracking demonstration is a Trans-Astra demonstration mission that uses a 12U spacecraft and will seek to detect near-Earth asteroids and orbital debris for increased space situational awareness through a new technique, a novel technique that helps detect small, fast-moving objects that are very dimly lit. It's a very big challenge to be able to detect those asteroids, and they have a synthetic tracking system planned to detect the object streaking through a field of view, and then working in a way that's kind of like the high dynamic range imagery, build a composite image of a lot of rapid, very high-speed exposures. And then finally, the CubeSat Iodine Solar Electric Propulsion Demonstrator is an ExoTerra demonstration mission that will flight test a 300-watt solar electric propulsion system that uses iodine as the propellant on a 12U spacecraft. Iodine can be launched as an inert solid and then vaporized into an ionized gas once in orbit, so that avoids the rideshare safety restrictions on launching with energetic and pressurized materials. The mission will attempt then after it demonstrates the technology, it'll attempt to do a flyby of a near-Earth asteroid with an instrumentation payload provided by Deep Space Industries. So it's a great public-private partnerships for us. Then I know you can't really read this chart, but when you look back over the last several years, Small Spacecraft Technology Program traces its lineage back to PhoneSat work at the Ames Research Center. That team that worked on PhoneSat left NASA. They started a company that was called Cosmosia and now is kind of better known as Planet. The 8 1.5U CubeSats that we had on the Edison mission were unfortunately lost in the Super Stripey launch failure. But 2 spares that we had were used for a very successful NODES mission that we deployed from ISS, demonstrating network communications and simultaneous multi-point measurements. OCSD that we talked about launched its engineering development unit into space in 2015. That flight uncovered issues that were able to be fixed on the primary spacecraft that are ready for flight and currently manifested on the OA8 ISS resupply mission for an October launch. And it really demonstrates one of the key advantages of having a really low-cost CubeSats is that you can test and fly and learn. The TIVAC CPOD mission helped them develop other products and missions, and NASA is now benefiting from, under the Pathfinder demonstrations that we talked about, Skyfire and RainCube, which was talked about yesterday. The first Pathfinder spacecraft with an integrated payload will be delivered for launch in 2018. And CPOD is manifested on an August launch out of Vandenberg Air Force Base. The Thea and iodine solar electric propulsion missions that we talked about, they're public-private partnerships. We selected them in January, and they will test new capabilities of mutual interest, as we talked about, with very significant private interest investment in these. These missions are deliberately aggressive from a technological, budgetary, and schedule perspective and targeted for launch in 2019. So we decided to go out and just see if we put in some very strong motivational, very hard challenges on both in cost and schedule for that actually demonstrated a mission, and we were very happy with our response for that. Okay, so future mission needs. Recent studies, including the National Academy's report on achieving science and CubeSats that was published in 2016, has looked at gaps in current small spacecraft capabilities that, if we closed, would enable missions of scientific interest. NASA, I think, must have really liked this report because we ended up hiring the chair of the report to be the Science Mission Director and Associate Administrator. Now, I think there may have been other reasons too, but this was a really big reason. So, but if you want to question anyone whether there's an advocate in the Science Mission Directorate, right at the top, this is a very strong report for the role of small spacecraft. And then the Space Technology Policy Institute, or STIPI, recently completed a study for us to look at our small spacecraft investments, and they've interviewed 57 organizations across industry, academia, and government to determine their needs. And I'll be talking about some of those findings in upcoming charts. And in addition, NASA recently selected 10 studies under the Planetary Science Deep Space Small Sat Studies program to develop mission concepts using small satellites to investigate Venus, Earth's moon, asteroids, Mars, and the outer planets. This will inform science's small satellite strategy with the goal of identifying high-priority science objectives in each discipline that can be addressed with CubeSats and small sats. The plan is to manage for appropriate cost and risk while leveraging and partnering with the very growing commercial sector to collaboratively drive instrument and sensor innovation. And, when you look at the 10 groups, too, it's a very nice cross-section of NASA centers, universities, and some industries of the 10. It's broad across all those destinations. So, as I said, STIPI did a report for us, and what they did was they defined a small spacecraft ecosystem that's shown in this chart. And they categorized the actors in terms of upstream, like the materials supplier, component manufacturer and system integrator, the midstream, the launch vehicle provider, the launch provider and broker, the satellite operator and ground system operator, and then downstream, the raw data provider, the data aggregator, and the data analytics provider. So some companies span like the entire value chain, like OneWeb. Others focus on a single part of the chain, like Busick with their propulsion systems. So NASA Space Technology's small spacecraft investments, what we typically have done, and we've dispersed about $80 million since 2013, 60% of it going to industry. And we primarily support that upstream actors on the left, the developers, suppliers, and integrators of the systems that enable the missions envisioned by the midstream actors to get the data that's needed by the downstream actors. STIPI noted that companies that focus on these upstream technologies don't tend to fare well when obtaining private fund investments, as they cannot project large markets and customer bases like the downstream can. They really are the place that really needs investment from outside, is what they've highlighted. And most of that investment comes from NASA and AFRL, Air Force Research Lab. Much of the other government fund, although there's certainly other sources too, much of the other government funding, as well as most of the private funding, typically focus, STIPI found, on the mid and downstream actors, the operators and downstream analytics firms. For example, the National Geospatial Intelligence Agency is purchasing multispectral imagery from Planet. NOAA is buying space-based radio occultation data from GeoOptics and Spire Global. The National Science Foundation has a focus on science missions for geospace and atmospheric research. And NASA's Science and Exploration largely focus on missions for research and to address knowledge gaps. In addition, science is evaluating a small satellite constellation initiative where NASA would invest in one or more pilot data purchases to explore alternative approaches to acquiring Earth observation data with a probable initial focus on GPS radio occultation and land imagery. So a key part of our investment strategy is public-private partnerships, and what we seek to do is push the frontiers and develop new technologies by supporting and harnessing innovative ideas from all of you. NASA tries to enhance the rapid pace of innovation in the small spacecraft community through public-private partnerships with industry and academia, by leveraging advances in industry through SBIR awards, and by technology transfer of intellectual property from NASA that supports new companies and serves new lines of businesses. To date, we've engaged in industry partnerships for small spacecraft propulsion and attitude control systems, end-to-end capability demonstration missions that we've talked about, and small launch vehicle technologies. We have numerous partnerships with academia, including 29 right now for small spacecraft technology and instrumentation development efforts. And the next round of partnership solicitations with both industry and academia should be out this summer. You can look for them at our website, www.nasa.gov/smallsat-institute. And next, the Small Spacecraft Virtual Institute. One of the ways we're looking to maintain engagement with small spacecraft stakeholders in industry and academia, while also supporting this overall small spacecraft community, is through a new NASA Small Spacecraft Virtual Institute. This institute, managed by the Ames Research Center and jointly funded by Science and Space Technology, seeks to promote innovation and exploration of new concepts by establishing effective conduits for the exchange of information. The Institute provides a unified portal for external entities looking to engage with NASA or on small spacecraft topics. It's hosting and will continue to update the NASA Small Spacecraft State-of-the-Art report that describes current and near-term small spacecraft subsystem technologies for the community. So, and I want to invite you to check out the website, provide us feedback, and also invite you to listen to Bruce Yo's presentation later today on this. So then, common barriers. Taking into account the needs of NASA's missions and the findings from our studies, we've identified several key areas that represent common barriers to achieving more challenging missions using small sats. They include high-efficiency propulsion that is secondary payload compatible, affordable techniques for increasing radiation tolerance, low size, weight, and power instrumentation, high bandwidth communications for deep space and data-intensive swarms, high-performance onboard processing and navigation for deep space and autonomy, and formation flight for distributed systems, interferometry, and coordinated multi-point measurements. Science is primarily interested in finding novel ways to achieve decadal survey goals using lower-cost small spacecraft, and they invest in miniaturization or radically new compact instrumentation technology to help do so. Exploration is interested in using small spacecraft to close strategic knowledge gaps for further missions to the Moon and Mars. In space technology, we're interested in determining where the gaps are in currently available technologies that are needed to achieve those missions, and then closing the gaps. So while the technology needs that we identified here are really based on our NASA needs, we believe that the effort of pursuing these will drive overall advancement in capabilities of benefit to industry, to academia, and other government agencies as well. So, and a note just on the picture, that's a Goddard Dellinger 6U CubeSat, which is scheduled now to fly to ISS and be deployed from there later this year, with instruments to study atmospheric elements composition and Earth's magnetic field measurements. So, confronting the barriers. In broad terms, NASA supports the community through launch opportunities and helps develop and reduce the risk of emerging technology by funding and then flight demonstrating. We plan to continue providing support to the community through partnerships. And now, as part of closing, I want to show a couple videos of upcoming tech demo missions. We'll see if it starts. Yeah, the CubeSat Proximity Operations Demonstration Mission consists of two 3U CubeSats built and operated by TIVAC. The spacecraft will separate, deploy solar panels, and then begin a series of proximity operations, maneuvers to test relative station keeping, precise circumnavigation, and ultimately docking. The optical communications and sensor demonstration consists of two 1.5U spacecraft built and operated by Aerospace Corporation. After release and deployment, the spacecraft will precisely target the ground receivers at Mount Wilson Observatory in Southern California and test a 200 megabit per second optical downlink. The two spacecraft will also test some relative position measurements using cameras, beacons, and laser rangefinders. Okay, to end, what I'd like to do is kind of start with or come back to a reflection on just how far CubeSats have come. Back in 1995, Clayton Christensen, who's one of the world's top experts in management, innovation, and growth, introduced the idea of disruptive innovation and defined it as the process by which a product or service that takes root initially in simple applications at the bottom of a market and then relentlessly moves up market, eventually displacing established competitors. This innovation pattern is really seen in a lot of our market forces that we've all experienced, from the introduction of personal computers that disrupted the mainframe computer industry and were in turn disrupted by laptops, to cellular phones that disrupted the fixed line telephones and then were further disrupted by the smartphone, to, well, Blockbuster and other video stores that were disrupted by Netflix, originally mail service, and then video streaming. In fact, I just noted, I saw the CBS Sunday Morning Show this past week. In one of their programs, they highlighted one of the 12 remaining Blockbuster video stores. I didn't know there were any left, but there are 12. One of which was, the one they highlighted was in Anchorage, Alaska. And so, so maybe you can see the niche market. But and then, you know, it's just, you think about the life cycle of that business. It's like this. So they, at one point, they were building a new store every 17 hours. They were opening a new store, and now they have 12 left. 3D printing is another example of disruptive innovation. So disruptive innovations have unique characteristics that distinguish them from other types of innovation, and I wonder if some of this will sound familiar to you. At the start, they have poorer performance than the current standard solution does. They're also significantly cheaper than the status quo and target underserved areas or new applications or users. Their performance improves rapidly and at low cost. They are typically introduced by a non-mainstream player, are advanced by enabling technologies, and then follow business models not typically followed by the incumbents. So, as the Achieving Science with CubeSats report points out, CubeSats really fit nicely into that model. CubeSats began with a minimum set of capabilities, but today those capabilities are improving as the technology matures and number of users increase. CubeSats are typically substantially lower cost than traditional satellites, and were originally created to introduce students and other typically non-aerospace firms to space technology. And we know where that started. CubeSats are now introducing new functionalities, often not feasible with traditional satellites. And most of all, by virtue of being able to launch low-cost constellations and swarms comprising up to hundreds or even thousands of new architecture, thousands of data collection platforms, CubeSats have the potential to introduce entirely new architectures and ways to conceptualize space science. CubeSats that began as platforms for education or technology demonstrations are now increasingly being sought to supplement and supplant traditional satellites and spacecraft. They were introduced right here at Cal Poly when you were not a household name in the aerospace sector. And CubeSats are being helped along by advances in non-space-related commercial technology areas like software advances, processing power, data storage, camera technology, solar array efficiency. And finally, these platforms are typically being developed by university-based and private sector entrepreneurs using low-cost, off-the-shelf components, small teams, rapid iterations, and high-risk postures. That model is unprecedented in the risk-adverse satellite sector. So, as a result, I am privileged to be here, able to become here and address you all, the community that has created this emerging disruptive innovation. It's been an amazing multi-year journey for you that is now really exploding. And so I thank you all for being disruptive. I'll be glad to take this. Yes? Uh-huh.
which basically uses the CubeSat paradigm to put things into new tech demonstrations, basically in low Earth orbit. So would you comment on your support for it and how you would implement a similar program for deep space, which would take advantage of the CubeSat paradigm
Yeah.
and the newer launch services and use them in a sort of regular cadence to be able to get things into deep space via, for example, a very elliptical orbit around the Earth?
Yeah, yeah, I think that's a really good point. It's one of those critical downstream actors that really is fundamental for how we go forward and are able to go forward. So we are trying to work very closely with the Science Mission Directorate and coordinate our investment strategies with them. And we'll definitely look into that. Any other questions? Did you have one? Okay. All right. Well, thank you. I'll hang around for a little while at the break.
We are on break now until 10:15. I just want to remind everybody, if you guys want to see the Cal Poly Labs, we have tours at 12, at 2, and at 4, and they leave from the registration area. So if you're interested, the students will take you there and show you the lab, and then enjoy your coffee. Thanks.
At 12:30 on the second floor in the Founders Room, there's going to be a meeting organized by InfoStellar about ground station networks and automatic CubeSat launch and operations support. They arrange international CubeSat initial operations, and anyone interested in organizing such international collaboration is invited to attend that. Again, that's at 12:30 on the second floor in the Founders Room. Okay, our next presenter, please welcome Diana McKissick from the United States Air Force.
Good morning, everyone. My name is Diana McKissick. I am the lead for SSA sharing at the 18th Space Control Squadron. Most of you probably are familiar with us as the JSPOC. So today I'm going to introduce who the 18th is, what we do, and then talk about it in relation to the CubeSat community. So the 18th Space Control Squadron mission is to deliver foundational space situational awareness to assure global freedom of action in space. So in a nutshell, we provide foundational SSA data not only for the US government's purposes, but for the global space community, mostly through the website spacetrack.org. So this is kind of a high-level overview of where the 18th fits into the organizational picture. We used to be part of the JSPOC. We were the Space Surveillance Division. But last summer, they actually pulled us out and made us our own squadron so that we could focus on foundational SSA, and the JSPOC and the National Space Defense Center, which used to be known as the JICSPOC, could focus on space defense. So what is foundational SSA for the Air Force? It all starts with our sensor network. So these are the sensors that we have around the globe. It's a mix of ground-based radars, opticals, and then also space-based sensors. And so all of the data that we collect from these sensors and some very exciting sensors that we'll have in the future are what feed our foundational SSA cycle. So our squadron is about 80 people. We're a mix of military personnel and civilians. And we do 3 primary functions around the clock: tracking, identifying, and detecting. So we detect launches. We track all man-made objects in space. It's approximately 23,000 objects at this point. We use those observations to do our identification functions. So that includes everything from creating new space objects to retiring old ones and everything in between. One of the things that's missing from this slide is the information that we get from satellite operators and launch agencies. And this information is absolutely critical to helping us create not just foundational SSA, but timely and accurate SSA. So as I go through the next slides, we're going to talk about our mission areas. I'm going to talk about those in relation to the CubeSat community and how all of you can help us improve SSA for the community. So launch support, this is probably the most important portion for new operators. We do launch conjunction assessment for all launches out of the US. That's a process of screening a launch trajectory against the full catalog and then providing the information to the launching agencies so they can decide when or when not to launch so that they don't impact anything. Launch analysis is basically getting a launch plan and then creating a whole tasking plan for our sensor network so that we can track everything on that launch and then catalog it, identify it, and begin providing data on it. Very critical to this portion in the process, if you have a satellite and you want it to have a certain name in the satellite catalog, this is when you need to reach out to us and tell us exactly what you want that name to be. Otherwise, our launch analysts kind of take liberties, and you might end up with a satellite named something differently than you want it. But this is also a key area where we try to reach out to new operators and existing operators for launch information if we don't get it directly from the launch provider. So we also have an advanced orbital analysis team. They focus on processing space events. In relation to all of you, this is the team that when we have a complex multi-payload launch, they're the ones that take a look at all the observational data and piece it together to actually make an orbit. So during this process, we actually encourage operators to have a dialogue with us so that we can create new objects, send out the positional data, and then the operator can help us actually identify objects so that we can get those cataloged faster. Conjunction assessment is the core of our spaceflight safety service that we provide. What's quite interesting is that ever since 2009, the Iridium Cosmos collision, Stratcom, which is our higher headquarters, has been given congressional authority for us to provide spaceflight safety data to every single operator of an active spacecraft. So we do that quite often whether the operator wants it or not. So right before launch, actually as soon as we can before launch, we identify the satellites that are going to launch, we get in contact with them, and we get them set up on the website spacetrack.org. And a lot of this for the CubeSat community happens through my counterpart, Cynthia Wilson. She's here today, so I encourage all of you, if you have an upcoming mission, to come talk to us so that we can get you enrolled in this spaceflight safety service. So as I said, we provide this unequivocally to every operator of an active spacecraft, to include China, to include Russia. And we do this because it's in our best interest to provide or prevent collisions for our own activities. We also have a human spaceflight cell completely dedicated to spaceflight safety for the International Space Station. We work a lot with them when it comes to CubeSat deployments. So if you're deploying through NanoRacks or another deployer off the ISS, we're in contact with NASA to get that information. And we also coordinate with them on all of the activities surrounding them. So as you can imagine, this is our highest priority when it comes to spaceflight safety. So a lot of CubeSat activity when we talk about it is centered on how it's going to affect the ISS. And then finally, SSA sharing. This is my team and Cynthia Wilson. And our job is to interface between the 18th and all of their mission areas and all of you. So we're here basically to make sure that you know about us, to know that we do everything we do at no cost in the name of spaceflight safety, and to make sure that you're getting the information you need to optimize your operations. A big part of our job is also making sure that we get as much information from you to inform our operations. And again, this is something that happens at absolutely no cost and is really just so that we can improve foundational SSA. We have 3 levels of services, basic, emergency, and advanced. Advanced is open to those who have signed an agreement with Stratcom. Emergency are basically that conjunction information or anomaly support that we provide for operators. And then basic is everything available on spacetrack.org. And hopefully most of you are familiar with SpaceTrack. This is literally where we push all of our unclassified data in the form of TLEs, the satellite catalog, reentry and decay predictions. If you're not familiar with SpaceTrack, we have a table on the 2nd floor. Please come see us. We will walk you through the entire site and get you signed up for what you need. So there are some limitations to the SSA sharing program. We are a military organization, so we have no authority to tell anybody what to do or recommend courses of action, force somebody to maneuver out of the way of something. So instead, what we really focus on is providing the highest accuracy data possible to empower operators to make the best decisions possible. And so we do this primarily through SpaceTrack, and then we also, through SpaceTrack, encourage operators to talk to each other. So I know the CubeSat community has gotten a lot of criticism for launching unnecessary debris into space and being irresponsible. One of the biggest things I can recommend to do is to share your contact information with all operators and make your positional information available to them. Even if you can't maneuver, if that other operator can get in touch with you to at least get the most up-to-date orbit or confirm that you're not maneuverable, it can save so much time in the maneuver planning cycle. So again, you can do that through SpaceTrack, and please come see us so that we can show you the interface. So this is a snapshot of how our operator community has kind of evolved since we started doing this in 2010. You can see that in 2010, it's hard to see the black numbers in the box, but in 2010, we were only serving 108 organizations and only screening 890 satellites. Now, we're actually up to about 1,500 satellites that we're screening, active satellites, and we're serving actually close to 300 different organizations. So it's, over 7 years, more than doubled. And a lot of that, as you can see circled in red, is due to the academic community. So this is actually very surprising for a lot of people. They assume that most of the activity up there is commercial. But all of you are actually a huge influence on the space community in general, and that's exactly why we're here, is because we want to establish, I think, a more consistent dialogue with all of you. So that takes me to the next presentation, which will be loaded here, that was created by one of our contractors. As I said, we're here because we want to create a more consistent dialogue with all of you. We are very accustomed to dealing with bigger constellations, bigger satellites that maneuver. So we want your feedback on how we can better serve all of you to maybe dispel some of the myths surrounding the risks of CubeSats. So we're gonna go over some baseline slides of just kind of what we're dealing with in general in relation to CubeSats, and then we'll talk about some future initiatives. So the hardest part about studying anything related to CubeSats is how you define a CubeSat. So for the purposes of the next few slides, we just divided it into two categories. Those that do fit the U form factor, and those that don't. So the nanosats will be separate. So taking a look at our entire satellite catalog, we've identified 558 CubeSats that fit the form factor definition, 116 which have decayed, 50 small satellites that do not fit that definition but are still small sats, two that have been decayed. And then in relation to the 19,000-ish in the public catalog, that represents 2 to 3%. So this first slide, we'll actually also have these up at our table, which might be easier to see. This just really shows kind of the launch cadence over the years. So the red are the ones that don't fit the CubeSat definition, the blue are the ones that do. The size of the circle indicates the number of payloads on the launch. So you can definitely see how the launch cadence and launch number have evolved over the years. This kind of depicts the same thing you saw in the last image, but it really shows the blue are things that have launched above the ISS, and the other colors are the ones that have launched below. So you can see when it comes to the CubeSats, it's almost split 50-50. Ideally, we like to see everything launched under the ISS, but we realize that for research and scientific purposes, that's not always ideal. So this is just a snapshot of all satellites that have launched since 2010 to kind of show where they've ended up. All of the green are kind of non-LEO, and then LEO is basically the bottom line. And then we zoom in LEO. And the takeaway from this slide is that even though the CubeSat community gets a lot of criticism for launching above the ISS, guess what? They're actually not the biggest offenders. And a lot of those that launch above the ISS are not maneuverable either. So we like to think that the responsibility of a satellite operator has a lot more to do with just where you launch. So definitely off the ISS is a great place to start. So things we're working on in the future. We want your feedback on what statistics would be most meaningful to you. You're the ones that really are designing the spacecraft, operating the spacecraft. We're the ones with the wealth of historical data. So if there's anything we can do to inform what you're doing, we definitely like to do that. We want to do a conjunction risk analysis based on the historical data we have. Take a look at how is this impacting our sensor network and how we task it, maybe how we can optimize some of that tasking. Just figure out how we can refine the probability of collision analysis that we do on CubeSats. Right now, we certainly use a bigger hard body radius than is realistic. And then take a look at the timelines from launch to actually satellite identification and when you get your data. We realize that a lot of you depend on the data that you're getting from SpaceTrack. But a lot of that timeline depends on the information that we get from you. So we want to, I think, do a more robust analysis of how that's going and then work with you to improve it. And then some things we would like from you. First and foremost, please register your satellite on spacetrack.org. It's actually, if you come to your table, we can show you how to do it. And it's very basic. We just want to know what you're launching, when you're launching, who you're launching with, and a very brief description of your mission profile. And this is going to allow us to actually reach out to you before you launch to make sure that you get everything you need for spaceflight safety and positional information. We want to know if you have any propulsion capability, especially because we want to make sure you understand our collision avoidance process. And then also knowing your operational status is huge for us. We don't treat CubeSats any differently than we treat big communication satellites. So if we think you're operational, we dedicate sensor resources to you. We dedicate analysis efforts to you. So knowing when you're non-operational actually helps us quite a bit to optimize our resources. So finally, I just want to emphasize that the whole reason we're here is really just because we want more feedback from you. And we also want you to understand that the 18th Space Control Squadron, one, isn't the JSPOC anymore. And two, even though we're a military organization, we are definitely here to provide information to you by direction of the government. So take advantage of your tax dollars, because that's where this is coming from. And please come see us up at our table on the second floor if you have any other questions. Thank you.
Thank you, Diana. Now please welcome Cassie Wade from NNU.
Hello, thank you. I am Cassie Wade. I am a senior electrical engineering major from NNU, and we are a small private college outside of Boise, Idaho. I am also one of the team members on Radio Frequency Tag Satellite, or RFSAT, and we are the second undergraduate team from NNU to be researching and developing a CubeSat. So I'm really excited to have this opportunity to represent them and present to you today. So first, let's start off by imagining that we are astronauts on the International Space Station. We need to apply a range of distributed sensing across the 100-meter length of the station. However, the places that we need to apply our sensors, such as, don't know how to work this apparently, such as a solar cell or a structural member, are hard to reach areas, and monitoring and applying our sensors in these areas could be very risky, as well as require complex wiring systems. So in order to mitigate these problems and apply the sensors that we need, we propose a solution using RF tags that utilize backscatter data communication. RF radio frequency tags with backscatter communication provide means of very low power communication between a tag and a reader, and are a great solution to in-space distributed sensing. So today, I'll explain to you what this RF backscatter communication system is and how it works. I will then move into its benefits and applications. And lastly, I'll explain to you the NNU RFSAT mission and how we will perform a technology demonstration of this system in space. So first, let's talk about the system. We have two parts, an RF tag reader and an RF sensor tag. The tag reader is fixed and has its own power source, and it interrogates the tag by sending a transmitted signal at the tag. The tag can then harvest the energy from that signal and use it to power itself as well as other sensors on. The tag can then send data back to the reader by modulating the signal that is backscattered or reflected at its antenna. The data coming back from the tag to the reader can be any sort of digital or analog information, including sensor data that are on the tags. This system, the RF power of the system, can be maximized by the antenna gains as well as the transmitted power. So we have two equations called our link budget equations that govern the power of our system. The first is our power up link budget, and this describes our power of the power being received at the tag. This is directly proportional to our power being transmitted by the reader, the transmit antenna of the reader, the gain of the transmit antenna of the reader, and the gain of the tag antenna. By increasing these three values, we can increase the power being received at the tag and therefore increase our radius between a tag and our reader. Our second equation is our bistatic backscatter link budget. So this describes the power being received at our reader. So once again, it's very similar to the first equation. However, we have the received gain of the reader antenna as well as the tag antenna gain is squared and our radius is to the fourth power. So once again, by increasing those values, we can increase our power being received back at the reader, therefore increasing our distance between our tag and our reader. On Earth, systems like this can communicate up to 20 to 30 meters. However, in space, with different conditions and parameters, we believe that we could get a similar system to work up to 50 to 100 meters of communication. So now let's talk about the benefits and applications of this system. The first one is power. So spacecraft has sufficient computational capability as well as enough power that we could mount a reader right onto the structure of the spacecraft and plug it directly into the power bus. The tag, on the other hand, is passive and requires no power from the spacecraft. So we can mount a tag on an area like I described earlier, and the only power that it needs is tens of microwatts to a few milliwatts, which is coming directly from the signal from the reader. This allows us to keep our power consumption and complexity with the reader on board the spacecraft, while our tag's power consumption and complexity is greatly reduced and allows us more freedom on those areas to place them. Another benefit is that they are typically small in size and mass. This is an image of a tag that will be used on CubeSat, very similar to what we'll be using. And you can see it's only a few square inches. It is also only 40 grams, so they're not very big at all. Next is that they can perform basic computing functions. So modern low-power microcontrollers can actually be mounted right onto these tags and be able to perform basic computation. Lastly, they can be integrated on a spacecraft after deployment. So once your spacecraft has been completely designed and launched into space, you can mount a reader and a tag right onto it, and adhering the tags onto the outside of the spacecraft is very similar to putting a postage stamp on a letter that you're about to mail out. So if we go back to our original scenario, what we can do is mount an RF reader on the central rotating beam of the ISS. We can then mount RF tags in those different areas that we need. And by rotating and pointing that RF reader at the different tags, we have means of distributed sensing across the whole length of the station. An application of this could be putting IMUs on those tags and being able to measure the oscillations across the station after an impact such as satellite docking. Another application of this could be CubeSat rendezvous. So many CubeSats, after they're deployed into space, need to conjoin to each other. So if they have this system, they can use characteristics such as the signal strength and the phase of those signals to find each other, locate, and orient, and up to millimeter precision on that. So it's a great application for CubeSat rendezvous. Now that we've seen some of the benefits and applications, let's move into the NNU RIFSAT mission. So we are creating a 3U CubeSat to perform an in-situ technology demonstration in space. We are using, the 3U CubeSat will house the reader of our system, and we will be deploying the end plate of our system with the tags mounted onto it to perform this demonstration. We would just like to be able to have a proof of concept that the system works in space, as well as receive sustained space weather data. So to do that, we will be doing incremental data measurements. So once our satellite has been launched, we will deploy our boom and turn on our reader. So the tag and the reader will communicate at the deployed distances. And we want to be able to have a full range of functionality for this system. So we have decided to deploy our boom in 10 centimeter increments all the way up to a 1 meter total max. And at each of those 10 increments, we will be taking those data, such as temperature and radiation, to provide our space weather data. To do this, we have 6 subsystems, excuse me. The first one is an aluminum structure. So it's a basic aluminum structure coming from near space launch. As well as that is our electrical power system from near space launch, and that is our solar cells as well as our battery stack. And that component contains our iStar radio as well. So the iStar radio is a simplex radio that works on the Global Star network, and that will be our main communication from our satellite back down to Earth. Next, we have an amateur radio. So this is a duplex radio that will be a second means of communication between the satellite and Earth. And this is actually being provided to our satellite by a collaborating high school. So Caldwell High School from Caldwell, Idaho, will be adding that amateur radio, and that's a great opportunity to provide some hands-on experience to those high schoolers. Next is our interface board. So this interface board is our essentially onboard computer for the satellite. It will take all of the power, distribute the power from the electrical power system to the different payload subsystems, and it will also be in charge of all communication between the EPS and the different subsystems. And this board is actually being created at NNU. Me as well as Daniel Slemmer have created the first prototypes of this board, and we have already begun testing and communicating with that. Next is our RF system. So this is coming from a research group, the propagation group at Georgia Tech, their graduate research program. and they are developing and we're purchasing the system from them. We have 2 boards. So the first is our circuitry board for the reader, and the second is the reader board antenna. So you can see it's mounted as physically close as to the end of the satellite as possible. That way we don't have to worry about interference between our aluminum structure and the communication between the tag and the reader. Under that is a conducting boom. So we have purchased a motorized non-conducting boom from Composite Technology Development. It's a carbon fiber spool boom, and on the end of that will be the end plate of our satellite with the mounted tags. So we have a power budget for this. We're going to move on. So the RF system for our satellite is actually, like I said, being purchased from a research group from Georgia Tech. And this specific system that we are purchasing from them works on the 5.8 gigahertz frequency band, and it has a transmit power of 24 dBm, and the antenna gains of our satellite are 10 dBi. So using that information, we wanted to get an anticipated range that our system will work in space. So we used those link budget equations I described earlier, and we're able to graph the power being received at our tag versus distance. So in this first graph, that is the power being received at the tag. The red line is our tag sensitivity threshold. So as long as the tag is receiving negative 16 dBm of power or more, it will be able to have enough power to turn on. So as our distance increases, our power decreases, and we meet an intersection close to 4 meters. So like I said earlier, our boom will deploy a 1 meter max, which means that this system does fit within that criteria for our mission. The second equation was our bistatic backscatter communication link budget, and this describes the power being received back at the reader. So we have a negative 50 dBm sensitivity for that, and as we increase our distance, we receive an intersection at about 2 meters for the reader, so we will be able to once again fit within our 1 meter range that we need for our mission success. Our tags that we are using will have 3 sensors mounted onto them. They'll have an IMU, a RadFET ionizing total dose radiation sensor, and a temperature sensor, and those will be used to receive that sustained space weather data. So we are a team from NNU. We are a small undergraduate team. There's 6 students and 3 faculty advisors. We received the USIP grant from NASA in April of 2016 and have been working on it for the past year. We will have our engineering model completed by August of 2017 and flight ready by March of 2018. We have not yet been manifested for flight, but we will be ready for flight after our testing anytime after that March 2018 date. So today we have gone over what RF backscatter communication is and how it works. I explained some of the benefits and applications of it, and then I went over the NNU mission for RIFSAT. We were really excited to have this opportunity to create a CubeSat and open that door for RF applications in space. Are there any questions? Yeah. Yeah, that's a good question. So the power coming from the reader, the microcontroller can harvest that power and it can use it to turn on the tags, or the sensors. If the sensors are not passive sensors, you could mount small battery packs right onto the tag if the sensor needs it. But the sensors we're using are also passive and can use the power coming from that transmitted signal. Yeah. NNU does not. Yeah. Currently, we're not planning on creating a business off of this. We just want to do the proof of concept, but we would be interested in maybe creating another CubeSat later on to increase the distance. Like I said, we're only doing a 1 meter max right now, but essentially this system could get a larger distance. So we would like to research more and be able to increase that distance in space. Yeah. I actually do not know the data rates on this system. It's a developmental system from Georgia Tech, but if you'd like to find me afterwards, I could look into that and let you know. I do not know that right now, sorry. Are there any other questions? Thank you for your time.
Thank you, Cassie. And now please welcome Daniel Oltraghi from AGI.
Hi, let me start out with a couple questions for you. How many people are concerned about collision risk in low Earth orbit? Raise your hands if you are. Great. Now, second question, how many are concerned about the perception others have about CubeSats and debris risk? Cool. Just curious. What I'm going to talk to you today about, I'm Dan Oltraghi from AGI. I'm in a small research group. I do space standards development in space operations and in debris mitigation. And I have done some research here, or we've done some research that we thought you might be interested in. So I'm going to talk to you first about what we think, and we're not dead sure, but what we think the actual population of debris is in space. And then we will take a look at using that population and even the current public track population, what we think the collision risk is in low Earth orbit. And then we'll talk about what happens were we to have a collision. So today's space environment. This is, I realize, totally hard for you to read, but it's showing apogee and perigee altitudes. Perigee is on the y-axis. And it's showing you color-coded, this is from back in 2011, what the density distribution is of objects in space at that time. I keep using this chart because I fared in a curve here that is the 25-year orbit lifetime limit. And so you'll be able to look at this chart later, presumably from the conference. But if you're to the right and up from that yellow line, that means that if you're injecting into that orbit, chances are you're not going to just passively meet the 25-year lifetime guideline. So that means if you're going to be a good space operator, you need to try and do something to come down quicker. This is a video we put together which depicts in this segment the publicly tracked LEO crossing population. And you'll see there's 13,700 some objects publicly tracked. Now we're going to go, instead of the public population, we're going to look at what we think is up there based on some of the debris surveys that have been conducted. And we're stepping down in size and showing you the composite number of objects that are either that size or bigger as we step down. And what you'll see is that eventually we're going to get to that 13,000 number from the public catalog depiction earlier. And that's kind of, that'll show you what we're tracking today, and then we'll go down to 1 centimeter, I think it is. So, you know, showing debris in space in this sort of depiction, it can be always misleading because we have objects the size of Rhode Island in the video. Well, obviously that's not true. But just looking at the scope of them in this depiction, I think is still useful. So just to highlight, the public catalog is only tracking like 4% of what's in the actual, what we think is actually in space today. So that's a pretty small number. That means that we could collide with something and chances are it's not in the current public catalog. This is a favorite cartoon of mine. We've photoshopped it a little bit, but people have had the big sky theory in mind for many, many decades. They think that because they haven't been hit, there's absolutely no risk. And I'm here to tell you that's not true. It's worth looking into what the real risk is. Risk is increasing in LEO for a number of reasons. First off, there is a lasting legacy. We've had decades in space now, and unfortunately, you know, whether it stemmed from irresponsible actions or just bad luck, and I'm sure it was a combination, we have lots in space. It's the gift that keeps giving. We're going to have repeated collision risk just from that. And it's really against that backdrop that CubeSats are coming into their own. Did I click it or did I not? Oh, I did, but now I clicked it twice. So the next thing is we're orbiting more and more objects. It's cheaper to do so. Launch access is improving, as you know, and then we're looking at potentially huge constellations being flown. Okay, there was the last click. And then just to highlight, it's not just CubeSats communities that should be concerned, it's the overall space community. I sat in on a space debris conference briefing last week in Germany, and an ESA study they briefed said that only 60% of LEO spacecraft comply with a 25-year post-mission lifetime. And only 20% of those above 650 are compliant. Those are pretty low numbers. And notice, I'm not qualifying those with CubeSat. This is just satellites. So what we're going to do next is look at some current, future planned constellations, and then also throw in some CubeSats. And the hypothetical there is highlighting 3 different CubeSat constellations I introduced. And then we're going to try and evaluate what the collision risk is. So we're going to return to these constellations in a moment. Let's see, caution. Oh, I'm getting from public sources these definitions of constellations, so, you know, the actual constellations may be slightly different. I'm not convinced the answer will be much different. So think about how you would assess collision risk. How would you do that? Well, I'm going to tell you that one of my favorite phrases is, if humankind were to disappear from the Earth today, there would still be a collision risk. It has nothing to do with us being here, or more importantly, our knowledge of what's there and our characterization of the errors that are part of our knowledge. So any assessments that use some of the standard conjunction assessment collision probability equations really don't apply to this thing. So we came up with a couple methods. I think we had 5 or so in total for LEO. And one was just to ask the operators, have you had a collision? And we're surprised that some operators told us, yes, they had, even though they hadn't publicly previously disclosed that. Obviously, I'm not going to go into who, but the point is that you don't always get shared that information. There are things happening in space that you don't know about necessarily. Another method is to look at our Space Data Center. I'm a program manager for something called the Space Data Center. And for 33 operators with very, very large fleets, we do conjunction assessment and reports. So we can get some statistics from that. Another method we can use is the JSPOC method or services that were announced earlier. And that's a great source of data, conjunction data messages. Many have been generated, and that's a great statistical repository. Another way we can do it is using some STK simulation tools. We have something called Advanced CAT, Collision Avoidance Tool. And we can use that parametrically and run it out for many decades, if not hundreds or thousands of years, and see how many conjunctions it says there will be. And the last method I'll present is something called volumetric encounter method. Sal Alfano and I came up with this a couple of years ago. We just got a patent awarded for that technique. And it's really designed for the high-density LEO environment, but is very suitable for what we're trying to do. Just briefly, a look at what it does. It takes the mean anomaly of satellite 1 and 2, and there's a trend line, this purple line here. That's the progression of this pair of satellites through that space. And there's an ellipse in that space where if that progression line goes through the ellipse, you'll have a collision. This is the kind of plot we end up producing out of our methods. We call it a log plot because a log plot because it is. But in the red line, we're showing the volumetric method and the number of encounters or collisions we would expect. And then the green line are our independent advanced cat runs, and you can see they lay right on top of each other. Turns out this is an R-squared relationship. I'm just going to flip through here very quickly for time's sake. But this characterization allows us to actually map these rates down to hard body radius size. Missed distance is the x-axis here. So if you know the summation of the two hard body radii coming together, you can use this to figure out how many collisions you'll have without any parametric Monte Carlo sampling. That's very valuable. There is a similar thing we find in molecular gas dynamics. That R-squared term I mentioned, you see a D squared in that middle equation there. I'm not going to go through this, just to say there's an equivalence here, which was encouraging to see. So these are results. You can look at it later, but suffice it to say in the middle three columns, we're showing the rate of collisions, encounters to 3 kilometers, and maneuvers to 1 millimeter that all of these constellations would have to do for the public catalog. And then in the right three columns are against what we think is up there in space. And I've highlighted in color code here some things that are very red, very, very high rates. You'll notice that in green I've highlighted the CubeSat rates. It turns out that the rate of collisions is pretty low for them. I tried to do this more in a graphical sense, and so I have relative color symbols. The symbol size denotes the rate, the risk, and there's some little dots. I'm going to find them here. There's a dot right there that you can't even see. There's another dot there that's very small, and then there's, I think, another dot up here. Those are the CubeSat ones. And relative to some of these very large constellations that are going up, the risk is small. If we flip to the next depiction, though, this maps the warnings, 3 kilometer warnings, which would imply that an operator would have to screen and take action and try and avoid hitting a CubeSat, for example. And the message here is that now this plot no longer depends on your object size. It just depends on you being there. So the more objects we have in space, the more work the flight dynamics people are having to do to avoid collisions. Now, why should we care? This is the Iridium Cosmos video on the right. And then on the left is something called DebrisSat. It's a US Air Force-led and NASA-led investigation. And that, in DebrisSat, they actually built a satellite that had kind of typical components for today's satellites. It was actually designed to be, hit in a hypervelocity sense. And it's actually being hit by a CubeSat. So if you think a CubeSat wouldn't cause damage to a satellite, I can assure you it will. Even the largest fragment from that is still very small, or fairly small. It comes off of that. This is where, in a right ascension declination, an inertial frame, objects from the Iridium Cosmos fragmentation event happened. And the message here is that the relative velocity imparted from a collision is so high that it can cover the global sphere quite quickly. In aggregate, taking that previous animation, this is what you get. This is places in space, in inertial space, where a collision could happen at 780 kilometers. And then you can look at what satellites against that space are put at risk by a collision. This is a rank ordering of the top 20, for example, from Iridium Cosmos. And you can see the SCD-1 satellite, that's this. When you fly it through, it actually has risk areas. And then over here in the depiction, you can see it's flying through the debris field, and that was the highest at risk from Iridium Cosmos. So how can you help prevent collisions? Well, be a responsible operator, obviously. You can, and why wouldn't you, use the JSPOC SSA service that was briefed earlier. It's a great service, free. There are other options as well. And one of them is called the Space Data Center, Space Data Association. I'm not advancing for some reason. There we go. And that's just operators that got together to share their information and their authoritative ephemeris and maneuver plans and physical characteristics for their vehicles. And then you can also subscribe to some external services like the Commercial Space Operations Center that AGI runs that fuses data of optical and radar and passive RF to get really good orbit solutions. So in conclusion, the LEO environment is getting increasingly crowded. CubeSats are dominating the newly deployed objects, but as I showed, they're not really a huge risk just to their size and the altitudes they're typically deployed to. The mega constellations or large constellations, I think that is more of a threat. So, you know, we should feel good about this. CubeSat community should feel good that the risk is not that high. But at the same time, I want to caution you that just your existence in space, if you leave it there, causes other operators to have to try and avoid it later. And it doesn't matter that you're a small object, they have to avoid it. And I do like the ISS deployment, as Diana McKissick mentioned earlier, because it keeps you out of harm's way. And that's my talk. I don't really have time for questions, but if you would like to ask questions of me, see me later. Thank you very much.
Thank you, Daniel. Now please welcome Brian Cooper from Astro Digital.
Hi, everyone. So I'm representing Astro Digital. I'm Brian Cooper, and I'm going to be talking about differential drag for collision avoidance. So orbital debris is a growing problem, as you may have just heard in the past 15 minutes. We have things like the Iridium Cosmos collision. People are talking about the Kessler syndrome in the news. Sandra Bullock is in danger. So that's when you can tell when things are serious. So there's a lot of objects in orbit. We just saw a lot of great graphics about that. About 750,000 objects of 1 centimeter or more. And then about 18,000 of those are tracked, and then 4,000 or so are active or inactive satellites. So mostly things we can't track and mostly very small things. But 1 centimeter is the equivalent of a hand grenade going off if it runs into you at 7 kilometers per second. And orbital debris is only increasing. And most of it is due to past collisions and explosions of large satellites. So a lot of things that aren't actually active satellites and a lot of things that are only up there because other satellites have exploded. So the future is mega constellations and probably increasing finger pointing at CubeSats and small satellites for cluttering orbit and raining down destruction from above on our heads. So we got a lot of different constellations coming online, and we should probably, care about that because it is causing damage. There's going to be more and more risk over time. This is an image you can see with the red arrow of Sentinel-1A, and they got hit by something on this order of 1 millimeter. And you can see it took out a pretty significant chunk of their solar panel. And so as large operators like ESA and NASA start experiencing damage, and they're in touch with regulators, we're going to start getting more rules and more regulations and more fees placed on us just to get to space in the first place. Oops. So as a CubeSat community, we should probably come up with a response to this preemptively. We could say that there's already lots of debris in orbit. Why do we have to worry about this? But that obviously doesn't address the problem really. That's just avoiding it. We could say CubeSats are so small though. We just heard that that's not really a big deal. Satellites are going to have to maneuver to go around us, and also there's a lot of CubeSats. We could say large satellites are the real problem, which is true, but we should still do our part, even though an explosion of a large satellite creates more debris than every CubeSat ever launched and to be launched in the next 10 years. We still should do something about this because we are contributing to debris in some way. We could use deorbit devices, which is extremely helpful, but there is still the problem that during your operational life, you're potentially going to be running into satellites, other satellites. We could say we have propulsion on our CubeSat, which is, the ultimate solution, but, it's not going to work for everyone. It's expensive. There are design constraints. Maybe you can't fit a propulsion system. Or you could say our CubeSat has attitude control, and that's good, and it's a little cheaper than propulsion as well. Attitude control equates to avoiding collisions through differential drag, which is simply turning your satellite narrow face into the wind or turning your satellite broad face into the wind to change its average drag area, which then changes its predicted position at the time of closest approach, because JSPOC uses your average drag area to calculate where you're going to be in a few days. So there's different levels of effectiveness for different form factors. With a 1U CubeSat, there's not much difference between the average drag area, the maximum drag area, and the minimum drag area. It's just about a sphere almost. So you're not going to get too much effectiveness there compared to something like the Corvus HD or Planet Labs Dove, which has broad panels that it can use in one direction, or really narrow face in a different direction to change its velocity. And then in general, CubeSats have an advantage here because of their characteristically low mass over area ratio. So we get a lot more acceleration compared to a large satellite that has a lot more volume compared to how much surface area it has, a lot more mass. So this is what a maneuver would look like. This is calculated for Corvus BC in a 600-kilometer orbit. And you can see it's comparing if you use the minimum drag area to change your position versus the maximum drag area, or the maximum compared to the average tumbling surface area. And so kind of the big deal here is you can move a significant number of kilometers within a few days. And since JSPOC provides warnings, usually 2 to 3 days ahead of time, that you might run into something, that means if you act quickly, you could definitely make sure you miss that collision, even if the other object didn't move at all. And also note that, in general, for most form factors, using the minimum drag area to perform a collision avoidance maneuver is more effective because the minimum drag area typically differs a lot more from your average drag area than does if you use the maximum cross-section of the satellite. And this is a plot showing the relative differential drag acceleration that you can achieve, and also the maneuver time. Those two are inversely proportional. The faster you accelerate, the quicker you can get somewhere. And so the big takeaway here is that you can move over a kilometer in about 1.5 days with basically a wide range of satellite form factors, which means most CubeSats, as long as they're in an orbit that's less than 650 kilometers, which is typically true, can actually use differential drag for collision avoidance. So that's a big response that we can have to people that say that we're just creating debris, we're tumbling around out of control, we're running into things. We can say, well, actually, no, we can control where we're going to be, and we can dodge other people. So then the problem starts to become, though, how much time are you spending on this? And especially for a constellation, you have to think of things like, if I'm going to do a differential drag maneuver, all of a sudden my satellite is going to shift its position in the constellation. So how do I make sure that I keep my constellation, which a lot of CubeSats, the purpose of a CubeSat is to have a constellation because you can build a lot of CubeSats, launch them all up there at once. And so let's say we have a constellation, we want to keep them all evenly spaced. We have these 4 satellites. They're all doing their operational thing, roughly average drag area because they're rotating around every orbit. And then we get a warning from JSPOC saying satellite 2 is going to experience a close approach in 3 days. So, okay, we need to avoid that approach. It's really close. It might come within 200 meters. That could be an actual collision. So what we'll do is we'll put all of our satellites into a minimum drag mode. They'll all shift in the same way so that they all stay evenly spaced in the constellation. We'll successfully avoid the collision, and then immediately afterwards, we'll re-enter operations with all the satellites still evenly spaced. So the problem with this is that now every time we experience a collision warning, we have to maneuver our entire constellation we're wasting a lot of time, especially if you're doing things like, let's say, you experience a collision warning 1 out of every 100 days per satellite, and you have a 100-satellite constellation. That means you're maneuvering every single day. So you've just built like a differential drag maneuvering constellation that has no other purpose in life. So if you have a lot of satellites, then you could do something like single satellite maneuvering. We have our same constellation. We experience or get a warning from JSPOC. We maneuver this satellite into minimum drag mode. It drifts out of phase with the other satellites a little bit, but it successfully avoids the collision. And then we tell it to go into maximum drag mode. That brings it back into phase with the other satellites, and now they're all back in position. So this is pretty good, but another problem is we have that extra resynchronization step, and that actually ends up taking quite a bit of time. You can see here on this plot, so we avoid the collision after about 1 day, and then we bring it back into phase, and that actually ends up taking over 6 days. So now we've multiplied the amount of time that it takes to avoid a collision by 4. But this could be good if we have a whole lot of satellites. We don't want to do simultaneous constellation maneuvering. And so then we took a look at the conjunction frequency, kind of similar to what the last presentation was about, a little bit simpler method. We just used data from the 2 Perseus-M satellites that Astrodigital has on orbit. We found out that we get about 1.8 conjunctions of a 300-meter miss distance or less, 3.78 of 500 meters or less, and 7.87 of 1,000 meters or less per year on average over the 3 years we sampled the data. And then we took a look at the average orbital debris density to correlate that with how many conjunctions you might expect at different orbital altitudes. So for example, if you're getting 3.78 conjunctions at 620 kilometers, you would expect about half as many collisions at 500 kilometers, where the debris density is half as much. All right, so this is a big wordy slide, but I'll just try to walk through each thing. This is showing how much operational loss you would expect for various constellation sizes and for various maneuver methods. So the first one, this is easy. You have propulsion. You're just maneuvering each satellite individually, and you have pretty high, well, relatively high thrust to differential drag, which can be an electric thruster, and that'll get you, not very much interruption at all. You just do a maneuver a few orbits before a potential collision. You avoid that collision, and then you resynchronize your spacecraft and your constellation. It could be 1 spacecraft, it could be 100, doesn't matter. You're only going to end up with like 0.1% loss of operations, which I think that's totally acceptable to any satellite operator. The only problem is it's expensive. Most people aren't going to have propulsion. So if we did simultaneous constellation maneuvering, and let's say we didn't have a constellation, we have 1 satellite, that ends up being not too bad. It takes about 1% of your time. Looking at Corvus, BC for 600 kilometers. So that's not too bad. That's also probably pretty acceptable. But if you have a lot of satellites, like let's say 100 satellites at 600 kilometers, now you're looking at using up 80% of your operational time just to avoid collisions with simultaneous constellation maneuvering. And that is very obviously not acceptable. And a lot of the other ones are also not acceptable, like 10% of the time. That's a direct hit on the revenue of your constellation. You're losing 10% of your revenue because of avoiding collisions. So if you take a look at single satellite maneuvering, doesn't matter the size of the constellation, this is the numbers you'll get, which is still kind of iffy for some of these, like 7% operational loss on our constellation. I know personally Astrodigital, we're probably not going to be willing to accept that, but something like 0.2%, if you had a Planet Labs Dove in a 450 kilometer orbit, that's nearly as good as using a propulsion system. So you're not wasting that much time at all, but now you have a really good response to say, we're responding to collisions just like any other satellite operator. And so in conclusion, differential drag is a viable opportunity for collision avoidance as long as you have attitude control, but operational constraints on large constellations might force operators to use propulsion or just accept collision warnings as a risk. Although we definitely need a coherent strategy as the CubeSat community soon, otherwise regulators might decide what the strategy is for us, and that's not usually a good thing. So together, we can make sure that Sandra Bullock isn't threatened by high-speed orbital debris ever again. Thank you. Any questions? Yeah. Yeah, so there's definitely situations where the maximum drag profile, oh, sorry, I should repeat the question. It's asking, so sometimes minimum drag wouldn't be the most effective because you're moving closer to the potential collision, and sometimes maximum drag would be better. That would just be a function of where exactly the potential collision is predicted, and JSPOC provides that data as a part of the CDM. So it'd be a pretty simple thing to determine where is the cutoff where I actually want to go into maximum drag to avoid a collision. So yeah. Yeah. Yeah, that would be really unfortunate. So what happens if there are two satellite operators and they both maneuver the same way accidentally? That comes down to also what the JSPOC team was talking about earlier on, about having communication between operators, and you just have to plan that out. And I should get a plug-in for Astro Digital. We are hiring full-time engineers, so come talk to us. There's a bunch of us here. Yeah, we need a lot of people. All right, thanks.
Thank you, Brian. And now please welcome Henry Martin from NanoRacks.
Hi there. Can everybody hear me okay? Great. So, again, I'm Henry Martin from NanoRacks. I'm a mission manager, so I put your things into space. And today we're going to talk about a couple things. The first one is readiness, formations, and resilience. And the next thing we will talk about is sort of how we can help get your things into space with some new things that we're doing. Before I do that, though, I want to say thank you, one, to all of you all. Thank you to Cal Poly, to the sponsors. This is a great conference, 14th conference. So 14 years ago, I was 10 years old. So with that, we will go to the next slide. Awesome. So I don't know about if anybody knows about NanoRacks, but essentially we provide commercial access to the ISS. We do a bunch of internal things, but because this is the CubeSat workshop, I will focus on our external things. So over here, is this a laser pointer? No. We have our standard NRCSD, so that photo is pretty famous, shoot out, I think those are doves. We've done that about 140 times. We also have our external Cygnus, so that's the one in the middle. We mount a small satellite deployer on the outside, shoot it out after the Cygnus finishes its mission at the ISS at actually a higher orbit of around 500 kilometers. We have our Caber class, which is up to 100 kilograms. And then our new one is the double wide. That is a 2x3U form factor. We're launching 3 of those on SpaceX 12. Those are all NASA, Alana CubeSats. So we're very excited for that. Back to the topic, it's a new concept that we're trying out. So essentially, most of the time, people want to be launched and operating immediately. But that doesn't always need to be the case. And so what we can do is launch you and stow you on orbit until you want to do that. So hence the name stash and deploy. A good example of this would be, let's say you have a science mission. So you want to launch something, you want to get it out, you want to take measurements at a certain altitude, and then you want to follow that up, say 3 months later to see, well, are my measurements going to stay the same? Are they going to change? Well, this is a great way to do that. So you launch up all at once, and then you deploy half at one point, and a bit later on down the line, you get the other half out. QB50, which is we launched last week, they're trying to do that same thing. So bunch of small satellites that take the measurements throughout the altitude. Another thing you could do is if you want to do a proximity operation, so say you launch one, then you want to get one out a month later to track that one. Just an example of what you could do. So what we've found is that when you leave a satellite on orbit, a lot of people worry about their batteries. Doesn't need to be the case. We've had some sit up there for a long time. They saw very low degradation of their batteries. We're also making a concept where we have a standby thing. So people miss launches, right? Everybody's built satellites here. The schedule never works out. But so people lose their space. Now, from my standpoint, I've already allocated the manifest. There is volume that is going to launch. So if someone drops out, well, why don't you just have your satellite ready to go, and we'll just slot it in and launch there anyway. So that's another thing we'd like to do. The logical next step for this would to be, well, rather than depend on building the satellite on the ground, let's take it upstairs. So with that concept, you can, with like 3D printing, right, you could build a bus on the station, and then you could launch the components in the cargo, and then you could assemble it on orbit. I mean, if we can do it here, I think astronauts can also do it up there. So we're in a couple talks with some people about doing this. Hopefully we can get it done within the next couple years. Another highlight here, the bottom point, is we're also assembling a microsatellite on orbit. Hopefully we'll get that out by the end of this year. So that's another example where you send up pieces, then you assemble it on orbit with the crew, and then you get it out the door. So in order to make all this happen, though, you want flexibility and autonomy. And with the best way to do that would to be, have your own airlock, which is what we're doing next. So we partnered with the Boeing company here to make our own commercial airlock. The idea is that we control it, we operate it, so you provide the control you need to say, okay, I want to shoot something out 1 month away, we'll do that, and then 3 months later, let's do the same thing. Well, you can do that with your own airlock. We hope to have this going 2019-ish. Another good thing about this airlock so far is that it's larger than the Kibo airlock, which we use now, so you can use larger microsatellites, more space for a hosted payload opportunity, which we also do. So that's really it for the proof of concept of, the stash and deploy your satellite. Again, this conference is about you all and all the cool things that you all are doing, our customers. So these are some of the people we've flown recently. We've got a bunch of NASA satellites launching. Virgin is a customer, ESA. So we're doing all sorts of things. QB50, we launched, 20 countries from 5 continents. So it's really neat to see all these different groups from all over the world coming up with cool things to do in space. And we're happy to help you all do that. So things that are just happening within the next few weeks. We have an external platform on the ISS, so it goes on the outside of the Kibo module. We just swapped out the payloads, so those are going to begin operating, I believe, today or tomorrow. We're very excited about that. It's built to the CubeSat form factor, but rather than you all having to roll your own whole satellite, we can provide you the power and the data, and you just focus on your sensor. So that's happening this week. 2 customers are CID, made out of Florida Institute of Technology, and then the DM7 payload, which Morehead State, they're here. I don't know where you guys are, but there they are. So talk to them about it. They're doing some really cool stuff. Next is, since OA7, which was last week, we launched 38 satellites. So it's our largest launch ever. It's a combination of the QB50, whom our keynote was a part of, and it's also some NASA satellites, commercial satellites, really the whole gig. So we hope to get those out by the end of May. We've got a couple airlock cycles coming up, so that's just another concept where you store your satellites till the opening is there. So that's really it, just to show you what we're up to, some new ideas. Come talk to us, we're here. Does anybody have any questions now? Going once, going twice. Thanks. Awesome. Well, we got a booth out front, so if y'all have questions, if anybody does not, come find us. Cool. Thanks, everybody.
Thank you, Henry. Now, please welcome Brian Clofus from Planet.
Hello, everybody. My name is Brian Clofus from Planet Labs, and I'm here today to talk to you about our recent deployment of 88 satellites and also a little bit about frequency coordination and frequency licensing for our constellation. So we just launched 88 3U CubeSats from India on a PSLV in February of this year. There was a total of 101 CubeSats on that launch in 25 quad packs. Everything went really well, no problems at all. And the reason why it went so well was that we had a kind of a Pathfinder launch in June of last year with the same team, also in India on PSLV C-34. And that launch kind of proved to everyone that we could work together really well. Planet, ISIS, ISRO, Antrix, we all got to know each other, and that kind of paved the way for this 101 satellite deployment. Here's a picture of about half of our satellites in the clean room in the Netherlands. There's a whole other table with equal amount of sats. Whoops. Here's all the quad packs lined up, ready to go in India. And we had a beautiful launch on Valentine's Day this year, which was great because I did not have a nice reservation at a restaurant. So the girlfriend came down to the lab, and we had a romantic evening watching the live stream from India, along with everyone else in the lab. Pictures from the launch. They had a video on board. The bigger blob on the far right is Cartosat 2D, which is about 750 kilos. And the two smaller blobs next to it are about 10 kilo sats, and the rest of those are our 3U doves. And then there's more doves, and even more doves. And then the Spire cubes and the rest of the cubes came out after us. Commissioning, we talked with all of our satellites within 3 hours after launch. All the satellites were doing fine. We uploaded 3 megabytes of new software. And actually, the status as of yesterday, we've had 52 satellites that have been fully commissioned and are taking pictures. We're doing about 10 satellites per week for commissioning, and we expect to be finished with that in the beginning of June. As Brian talked about a couple presentations ago, we're using differential drag to space out our CubeSats, and that's going to be complete in October of this year, so it takes a long time to space everything out. We have had 2 sats that have died since launch, which kind of sucks, but it's okay because we were expecting 5% DOA and 5% in the first year, so we're still good with regards to that. And as of April 20th, we have 84 sats taking pictures of the Earth, including the ISS constellations and the earlier PSLV launch. I'm a ground station guy at Planet, so this is kind of a graph of what we're downlinking into the ground stations. We're over 2 terabytes per day now, and we're expecting about 5 terabytes per day once the latest satellites have been fully commissioned. The green section in the bottom there is the 12 sats that were launched from the PSLV last June. The blue section is our ISS sats, and the orange there is the new launch that just happened, and that's through the middle of April of this year. Now on to a little more boring topic, CubeSat licensing. The first 15 CubeSats that were launched up to 2007 all used amateur radio frequencies, even the commercial sats and the NASA sats. The International Amateur Radio Union did coordinate these satellites because they felt that coordination prevents interference and it's better for everyone. Once the FCC kind of realized that this CubeSat fad was here to stay, they started releasing some documents on how to get experimentally licensed in the CubeSat band, in the amateur radio bands, and that worked okay for a few years until the IRU decided that, hey, we've got too many sats in the UHF hand band, and started declining coordination for satellites that weren't strictly amateur radio satellites. The first time this happened was the Raven CubeSat from Blue Canyon Tech earlier this year, and they moved to 401 megahertz. A little bit more about the amateur radio licensing process. I gave a talk at this conference in April 2013 and presented a flowchart on how to get an amateur radio license for your CubeSat. And I kind of punted on the commercial license question in the blue box there. Not done by CubeSats before, we need a Pathfinder. Unbeknownst to me, Mike Safian at Planet Labs was going through the process in April 2013, and I'm here today to talk about how he obtained the commercial Part 25 license for our Earth imaging constellation. So you've decided that you don't fit in the amateur radio service, you want to sell your images or sell your data. What frequencies can you use? Well, it depends on what what service you are providing. We're taking pictures of the Earth, so we're in the Earth Exploration Satellite Service. If you're looking at clouds and weather on the ground here, you can use the Meteorological Satellite Service. If you're doing basic research, you can fit into the Space Research Service. Each one of these services have lots of spectrum that's available to them. I put lots in quotes, though, because there are existing users, and they will fight you to protect their spectrum turf, so to speak. There's lots of information in the NTIA Red Book and the FCC table of allocations about all the frequencies that you can use, the spectrum you can use. Also, Attila Matas from the ITU gave a great presentation at the SmallSat conference in Chile last year, and there's the link to his presentation, which you can look at afterwards. So here in the US, there's kind of two options for FCC licensing. You can obtain a Part 5 experimental license, which is cheap and easy, but does not provide you any protection, spectrum protection. Or you can obtain a real Part 25 commercial license, which protects you from existing services. However, the timeline is designed for decades-long missions, not necessarily for these short CubeSats that we're talking about here today. And I just want to point out that all the FCC interactions are public and posted on the web, so you can go in and look at all of our licenses for free without signing up for anything. A little bit more about the Part 5 experimental license. It was intended to test out new technologies related to radio. You can pick any frequency you want, but I would encourage you to pick a frequency in the service that you want to use for the long term. Kind of respect the table of allocations. You'll have a lot less grief that way, get a lot less grief that way. Licenses are typically granted in 3 to 6 months. They're good for 5 years. It's only $70, and the launch integrator might actually do this for you, depending on which launch you're on. The downside is there's no, you are a secondary user of the spectrum, and there's no protection from interference. And if you cause interference to the primary users, you must stop transmitting. Even if you've got important data to downlink, you have to stop transmitting. Here's the link for the experimental license search online. You can punch in Planet Labs into the applicant name and find our experimental license from 2013. But the Part 25 commercial license, unfortunately, the first step to getting that license is you got to get the lawyers involved. They're the people that can kind of guide you through the process and actually file the paperwork. I encourage you to have initial meetings with the FCC to provide context about what you're trying to do, and just chat with them about the best way to do it. They'll talk with you forever. They love talking about frequency licensing, and they're a really good resource. I also encourage you to pre-coordinate with all the existing users in the band. That way, when your public notice period for comments comes up, there won't be any surprises, and less people will object. Now, during your public notice period for comments, people will object to you using spectrum. In the past, it's the old aerospace way of doing things is wait till the last second and then submit a petition to deny, which kind of resets all the counters and takes many more months. I'm encouraging the SmallSat community to kind of pre-coordinate with everyone in the band, and that way these snafus don't happen at the last moment. We have successfully coordinated with the Planet Labs, UHF, and also Spire CubeSat ground stations. We were causing interference with each other at 401 megahertz, and we decided that spatially separating the ground stations was the right way to do it instead of going through the whole petition to deny process. We also were coordinating with Terabella on X-bands before we acquired them earlier this year. Then you get your license, and there's also some bond milestones that once you reach them, you get your money back. So the approximate costs, you got to pay the lawyers. The application fee for the FCC is $450K. Annual fee is $150,000. There's a $5 million bond, but you can get underwriters for that, so that's around $100,000. Ground stations are $3K per site. At the international level, the ITU charges $40K to publish your satellite in their international frequency registry. And we at Planet have a regulatory affairs person whose sole job it is to kind of keep on top of all the licensing at the international and the national level, and so that's another cost. You can search the FCC database, punch in Planet Labs under the company name to find our license, or you can search by frequency or service or anything else under the advanced search on the left. You don't need to log in. It's really easy. It's not easy to search, but all the data is there. You just have to hunt for it a little bit. So the real question is, is a Part 25 license worth it? You got $750,000 plus people, plus 2 years of your life. When these rules were written, the satellites cost $100 million and it took 10 years to build. So this was not really a big cost. Now, today, with CubeSats, you can build your entire satellite for less than $750,000. And from project conception through launch and deorbit, that's less than 2 years. So I'm not sure that the existing rules are necessarily the best for the CubeSat community. Now, if we want to get together as a community and try and to propose some changes to these rules, the FCC will listen to us, but we need to come to them with a proposal and say, hey, this is how we should do it. At the international level, the ITU is looking at making the licensing process more streamlined. They've written a couple reports. It was on the agenda at the World Radio Conference in 2015, and it's on the agenda in 2019. Things may happen, but not for several more years. So what I've just talked about is only for the US. If you have ground stations or you're building your satellite in another country, there's a whole nother regulatory scheme to follow. We have ground stations all over the world, and we still have licensing problems getting new stations online. There's also the usual license upkeep, filing reports. If you add any new ground stations or new satellites, you have to file more paperwork, and there's more things to do. That's why we encourage your teams to have a regulatory affairs person who just keeps track of all this stuff. And here are some references. The workshop in Chile is a great reference. There's lots of slides there online. And that's pretty much all I had. The video is the deployment, and that may play while I take questions if there are any. Yes? Our latest launch was 10 kilometers circular, polar. ISS is lower than that, and yeah, we're right about 500. We don't have, we use differential drag. We don't have any deorbit devices, so we're staying under the 25-year limit that Dan Altraki was talking about earlier. Expecting lifetime, that's a good question. I think we're about 15 years. And hopefully we're imaging for all that, but probably not. Yes? Yeah, so the question was, you've got a ground station and you kind of do a spectrum scan and you're like, oh, hey, there's nobody here. Can I just use this frequency to talk to them with my satellite? That may be where things are going in 20 years, but unfortunately the current licensing system is not designed for that. We're kind of, you're an Earth exploration satellite, here's your frequency license, this is where you can operate. That leads to a lot of inefficiencies in the spectrum. But unfortunately, that's the system that we have built for ourselves. Yeah, cell phones do use CDMA or TDMA or whatever. Yeah, so our satellites, the main downlink is at 8.2 gigahertz, and they're all on the same frequency, and they're just spread out far enough. With dishes, the beam width of the dish is 3/4 of a degree or something like that. So we can track multiple satellites on multiple dishes during a pass. So the question is, can we use the same frequency for all of our subsequent satellites? This is kind of one of our, this was the bonds that I talked about. The milestones are, first launch, and there's a couple more, and then, the last milestone is, completion of your launches. You're done with building your constellation. We're not really expecting to ever be done building our constellation. We're just going to keep launching more and more of them. So this is kind of a point of contention between us and the FCC. So we plan on using X-band for the long term. No, you have to apply once for the constellation that you're building. So yeah. Any other questions? I'm probably out of time. No? Yes, one more, sorry. Is there any regulation for maximum power that you can transmit? Yes, and that's in the rules. There's maximum power densities on the ground. So, all right, guys, thanks. I'll be around the rest of the time.
Thank you, Brian. And now, please welcome Peter Yu from Spayware Systems Center Pacific.
All right, hello everyone. My name is Peter Yu. I'm a research engineer at Spayware Systems Center Pacific. I'm here to talk about a very long title called Testbed for Demonstration and Performance Analysis of an Autonomous Scheduling System for Communication Nanosets. And I'll explain what does that mean in the next couple of slides. So what is our motivation of this effort? Is that because of technology advancement and lower cost and easier access to space on CubeSats and nanosets, now we can put many satellites on orbit to do various missions, such as comm relays or remote sensing or weather monitoring. So since we're dealing with the many satellites on orbit, it increased the complexity, which needed some sort of autonomy or optimization to coordinate all these different satellites. So there are different tools available currently, mostly the software-in-the-loop modeling and simulation tools, but it has limitations. And a lot of people use a flat set or ground test bed to simulate their individual nanosatellites, but those are not used for mission-level type of simulations. So we propose a solution to create a very low-cost mission-level simulation environment using commercial off-the-shelf hardware and actual flight software to do a hardware-in-the-loop nanosatellite constellation simulation using open source industry standards and, as I mentioned, existing flight software. Also, we developed a graphical user interface to input parameters and analysis output on these algorithms to demonstrate autonomous user-defined algorithms for constellation of a network. So more detail on the testbed architecture that we developed has two modules. One is a ground station module and flight computer module. On ground station module has two segments. One is a virtual ground node, which simulates the ground station in different geographic locations and hosts a graphical user interface and also the user-defined algorithms if you want to test it on a ground testbed. Also, Orbit Simulator provides orbit information for the scenario. And flight computer side has a flight software core that provides a command and data handling services for the satellites. Orbit propagator propagates the position and velocity. Subsystem simulator to simulate the battery, solar panel, and all the other subsystems for the satellites. And algorithm modules that if any users wanted to provide their algorithms and optimization algorithms, they can put it here to use on a flight side. So goes into more detailed design on the test bed for our demo. We basically use a very simple hardware stuff such as just a workstation and 4 different BeagleBones or something similar embedded computers and Ethernet switch. You can also scale it up to have a more embedded computers or a bigger Ethernet switch if you want to test the more constellations and things like that. For software implementation, we are using a fly software that's been developed under Rapid Innovation Fund for our different types of on-orbit missions, VMware for virtual ground stations, and Python for all our interfaces. Just to talk about more on the fly software core, which is one of our enabler for this constellation testbed. As I mentioned before, it actually uses the actual fly software that we have going to use for some of our missions. It also uses a CCSDS compliant message structure called Space Packet. Also, it has an IP-based interface between the components, including the ground stations, which makes it easier interfaces to different components. Also, it has 9 different services for command and data handling for fly software that is a key for this testbed. So next thing is I want to show you the graphical user interface examples for scenario simulation. This is still in development, but I want to show you that we're trying to develop a very simple interface to design a sort of a comm relay messages that goes from the source to destination ground node using the nanosatellite as a mean to deliver the message. And we can generate the different types of messages, including the priorities, the size, and etc. So also we run the orbit scenario for orbit simulation for the satellite access window between these 2 ground nodes. And then once you run your algorithms, and you can check the result and how your algorithm performs based on the different algorithms that you provide. And a more detailed testbed data flow. So as I mentioned, the scenario simulation on GUI basically develops all simulations and the message types that you want to send from. And you're going to start from the original ground node that creates the message and send it to nanosatellites, and nanosatellite relay that message to the destination node. And you can run the analysis to see how that performed. And yellow highlighted area is where you can provide your different types of optimization or autonomous algorithm during this process. Just want to talk about a little bit more detail on the algorithm modules. So not only just in a ground station, but also in the fly software side, we believe that there could be some more optimization, autonomy, or scheduling solutions to help hold this network. So we're trying to provide the users to be much easier to develop their algorithm by providing some sort of a software interface to do this, so the users don't have to really understand the fly software side, what they need to do and things like that. They can just take the different types of telemetry and command, and they can use it. And these algorithms will provide a pathway to implement the sort of optimizations, such as communication scheduling and other event scheduling, telemetry monitoring, and so on. So as far as the summary goes, we developed a mission-level nanosatellite communication constellation testbed framework using components and the real fly software. We defined the ground station node, computer module interfaces, developed the GUI design to help the modeling and simulation, developed the message delivery simulation test case for evaluation. Ongoing work and future work has a more detailed subsystem simulation module to simulate the batteries, solar panels, and other subsystems. Implement the optimized message delivery scheduling system to evaluate our testbed, and also implement more realistic ground station model to be a more higher fidelity and demonstrate various autonomous message delivery algorithms to evaluate our testbed also. And if anybody has a more more ideas or things that we should be thinking about, I'm willing to hear about it. And that concludes my brief. And do you guys have any questions?
Thank you, Peter. And I have two quick announcements before we break for lunch. The first is that at 12:26, outside in front of this building, Jerry Buxton from AMSAT will be performing a telemetry downlink demonstration. He's going to be communicating with AMSAT's Fox 1A CubeSat, which will be passing for 13 minutes. He's going to use his laptop, a software-defined radio dongle, and a handheld antenna to downlink satellite telemetry and the Penn State, Erie, and Vanderbilt University experiments science telemetry. So that is at 12:26 in front of the building. The second announcement is that there's a meeting organized by InfoStellar at 12:30 on the second floor in the Founders Room. And the topic will be International Ground Station Network and automatic CubeSat launch and operations support. So that is at 12:30 on the second floor in the Founders Room. And now we will be breaking for lunch, and presentations will resume at 1:15 p.m. Thank you.
Welcome back. We'd like to welcome Kristen John with NASA Johnson Space Center.
Hi, this will be really quick. I just wanted to make you all aware of an opportunity that's coming out Monday. So this is a request for information, an RFI, for the Hermes facility. So this is basically a microgravity facility about this big that's going on the International Space Station. And it basically has 4 sub-experiments. These are replaceable little experiments that you can send up to ISS. So it happens to fit about the size of a 3U CubeSat. So you'll see in the picture there, this is kind of the heritage of the design we're working on. We actually use tubes, but it will fit a 3U CubeSat. So if anyone has a need to test a 3U CubeSat or any sort of component or experiment or idea that's 3U sized or smaller, you can use this facility. So if you have ideas or you know people that have ideas, the website's here on this slide. It's fbo.gov, that's FedBizOp. Basically, it's a RFI to get information for ideas. It'll be out for a month, and we're still in the design process of the Hermes facility, so we're open for suggestions if there's something you want to make sure a facility like this would include. Anyway, so if you have any sort of idea that could use microgravity that would stay inside ISS, we're offering this opportunity. Very, very inexpensive way to test your CubeSat or your experiment or any sort of component. It'll be up to the user to meet certain safety requirements. Can't have any sharp edges, certain things like that, since the crew will be touching it. But as long as you meet our safety standards and our electrical interface standards, we'll be plugging in experiments for the next several years to this facility. So we hope you guys have ideas. Come talk to me, Kristen John. Thank you.
Thank you, Kristen. Our next speaker will be Pamela Millar from NASA Earth Science Technology Office.
Welcome, everybody. I'm Pam Millar from NASA's Earth Science Technology Office, and I am the INVEST Program Manager, so that stands for In-Space Validation of Earth Science Technology. My colleague, Charles Norton, many of you probably know him. He is ESTO's JPL Associate and CubeSat Expert, but he could not be here today. So an outline of my talk, I'll start with a little bit of context of what the ESTO programs are. I spoke with a lot of you yesterday randomly, and I noticed many of you didn't have that context, so I'll provide that today. Then I'll go into the portfolio that we have and the status. So we had a pilot program of 1Us, mainly 1Us, then an Invest 12 solicitation, which covered 3Us, and our most recent Invest 15 was 6Us. Then I'll talk sort of anecdotally some challenges and lessons learned, very top level, and conclude with a summary. Okay, I already messed up. There we go. Okay, so this slide shows an overview of the ESTO program, and it's been a technology office at headquarters since 1998, so I think it's in its 19th year and has covered many, many projects that are diverse. So the programs are organized by observation, information technology, and validation. So for the IIP, the main idea is to develop new measurement techniques and new instruments and do miniaturization, low size, weight, and power. And a lot of times they'll conclude with a validation on aircraft. Then we have advanced component technology systems, which is usually lower TRL components and subsystems that would then get infused into IIP program. Our newest program is Sustainable Land Imaging Technology, and that is our first program, which is very focused towards one scientific area, one objective, which is to develop technologies for the future Landsat missions. Next, we have information technology, and that covers a broad array of things. I should mention, though, that ACT solicitation is currently out right now, so you would be able to apply, propose to that. Proposals are due June 16th, I believe. And right now, information technology systems, it covers big data, it covers ground systems and data processing, very, very broad spectrum of what it covers, and they're currently in review of their proposals. And all these programs then feed into the INVEST program, which benefits from raising the TRL to 7 or more in some cases. So the idea is to mitigate the valley of death. So a lot of projects, they might stop in their validation at the aircraft level, and that's not enough to propose to Earth Venture. And so we describe that as the valley of death. And so the hope then is once you're done with an INVEST project, you could then propose with low risk to Earth Venture or potentially other opportunities. So this next chart shows the pilot program that we had. I think it was around 2011. It established the foundation for the INVEST program. At that time, we didn't know whether or not it would be worth doing, if we could even do it, because we're an R&D technology office. So what business do we have doing spaceflight? Well, we don't have to do D-class missions. We can do R&D and get away with a lot of stuff, so it can be a lot cheaper and not have the stringent requirements that a Class D or above would have. So this is sort of where are they now? We have M-Cubed and Griffix, so that's a 1U and a 3U that are still operational, although they've all successfully completed their missions. We heard that University of Michigan uses it as a testing ground for students to learn how to do ops, so there's an advantage to that. All 3 of them were very tightly aligned to Earth Science decadal missions, so we have M-Cubed for ACE, IPEX for HISPRI, and Griffix for GeoCape. So that was a very successful program. That was before my time at ESTO. But when I came in, the INVEST 12s have already been selected. And the thing that I'll mention is our prime directive at ESTO is to enable science. So we're all about science, and we leave the spacecraft stuff to STMD, and we are very grateful for that. So starting with Murata on the left, so you already heard a very nice talk about that yesterday. So that's a free frequency radiometer and GPSRO. So that's very exciting. That's going to be launching in September. So that technology validates all weather sounding. The next one that we're very excited about, because it's actually operational, is Raven. It gets its own slide after this one, so I won't talk about that in much detail. But what I will say, it's the first demonstration of the Blue Canyon Technologies bus, so that was very exciting. Next we have IceCube, which was launched on OA7 recently, and it's being stowed on the ISS. I just heard that it's probably going to get deployed in the middle of March, so we're excited for that one to measure ice clouds. Next on the list we have HARP, which is a wide field of view rainbow polarimeter that UMBC is building. They are in their final testing right now, and we're hoping they make it to the deadline. They were actually on the same launch as IceCube. But as Henry Martin said, they're flexible, so we were able to get on the next opportunity, which we really, really appreciated. And then the last INVEST 12 that we have is linear mode photon counting, also known as Aerospace's AC9, which unfortunately ran into some technical difficulties, and so we are putting a pause on that one for now until they can figure out some of their technical problems. Okay, so next we have our, I'm going to talk about Raven a little bit. This is a bit of an eye chart, so I'm not obviously going to read everything that's on here. So let me just step back so I can point to things. Okay, so the idea here was you have a broadband radiometer to measure total Earth radiation budget, and I'm not going to go through all the accomplishments. It is operational, taking data. They did have some issues with COM in the beginning. It took about a month before they got that settled. But the main thing is they've already done TRL-7 for 3 of their technologies. So they have these payload doors in the upper right-hand corner. You have the payload. There are 2 sets of doors that open and close. If they had it their way, they would be doing that 50 times a month. They have an engineering model where they've tested in vacuum 450 cycles, which is pretty impressive. I mean, usually when you do spaceflight, you're not supposed to be doing moving parts, but this is really impressive. They also have, in the upper right-hand side, vertically aligned carbon nanotubes, which is used as an absorber for the radiometer, as well as gallium phase-changing melt cells to do on-orbit calibrations. So they did have a couple of problems which they've resolved. I'm going to give them a little plug here. They were just told that they're giving a talk at the SmallSat conference, so we're very excited about that, because by then, given the solar calibrations they've been able to do, given their limited comm, they're going to have a science paper. So this is going to be our first, I think, science demonstration, even though it's only supposed to be technology. You know, all the scientists, they're going to want to do science if they can. So we're very excited about this one. Okay, so next I'll go into the Invest 15s that we have. Great. So starting on the left, I should mention that these are all 6Us, and with the exception of RainCube, they're all passive, and RainCube is our first active one. So we're excited about that one. You heard yesterday, Travis gave a very nice talk. So on the left, we have CRS. So I should say we have CRS and CRS. So we try to keep them straight by calling CRS, CRS-J for JPL. We've had a couple of times where people have mixed them up, and you have to really be careful with these things. We heard that Blue Canyon also has a series. So imagine trying to keep track of 3 with a similar name. So that's an infrared atmospheric sounder. That one started a little bit late because it got funding from NOAA to do some design studies, and the next step after CIRRUS is going to be a mission called EON-IR. So this is actually in the pipeline to do something for NOAA when it's completed. You already know about RainCube, so I'll jump over to CubeSat. CubeSat is microwave radiometer, nothing too special about that, except for the fact that it mitigates RF interference real-time on board. So what SMAP does on the ground, this will be able to do real-time on orbit. So we're excited about that one. CIRRUS is infrared radiometer, which does not incorporate cooling. It has an onboard calibration device, as well as, let's see. Yeah, that's all I wanted to say about that. And this one could actually be used as a calibrator for a future Landsat mission. And last, we have, it's not actually an Invest project, it's what we call Venture Tech. So Tempest D, Steve Rising is actually here in the audience, he's a PI. It was a proposal for Earth Venture 2, and it was graded as having very high science value, but the technology wasn't ready. So they decided to fund it as a technology demonstration. So that's a 5 frequency millimeter radiometer measuring the transition of clouds to precipitation. So we have a really nice portfolio of missions. Okay, there we go. All right, and I always like to show this chart. It's our manifest status. So the top 2 have been launched, as you've heard. HARP and Murata will be launched this year. LMPC is on hold. Then we have the next 3 on the same mission. We believe it's going to the ISS, and that will be launching anywhere from maybe April to June of 2018. And then we have 2 left, CIRRUS and CIRRUS, to get launches for. So I'm hoping that Garrett will come up with something this summer. That's at least what he had promised us. Okay, now I'm going to jump into sort of my anecdotal lessons learned, starting with sort of the theme of this community, which is knowledge sharing. And I think it's been really powerful because CubeSats have started from the ground up. They haven't started, you know, from big government agencies or industry doing big things. It's an environment where everybody shares knowledge, and with the INVEST program, it's very different from the other ESTO ones that we have. When we have kickoff meetings, we tell the PIs, you know, we expect you to share information to help each other, and many times we'll have PIs calling one another directly without having me or Charles getting involved, and so we're really excited about all that. And it really all started with the experiences from the pilot program, where we've fostered relationships with LSP and U.S. government rideshare, universities, and my favorite connection now is the headquarters frequency spectrum management office. And you can imagine why that might be. I just have a few examples in these bullets of things that have been shared. So we have Cirrus talking with Tempest D about moving parts, so both of them have scanning incorporated. Although they're not using the same kinds of motors, both have looked into it and they shared knowledge, and I think they're better off for it. So IceCube and HARP got a lot of help from Murata regarding the issues they've had with the cadet radio and the Clyde Space solar panels. So that was a good example. And Qbert benefited from Tempest D as well, things that they learned on the Blue Canyon bus. And we have several of the projects that are using Wallops for the ground station, and so they're all talking to one another and helping, and we'll see in the next year how smoothly that goes. And as well, when you have a bus vendor that is supporting many of your projects, everyone's going to benefit. So all the Invest 15s are now benefiting from all the anomalies and lessons learned from Raven, which is operational. Okay, so how many minutes do I have? Oh, I am almost done. So you can read these slides, but if something can go wrong, it will. You can run out of time. But deployment release mechanisms is a big area, as well as single event upsets, and COM, a huge issue. And I'm just going to say one thing on COM. I'm going to go right to the last bullet, which is when you submit your frequency application, do it as soon as possible. And for your need date, do not put the launch date. Put the integration date, because you will not be integrated without a frequency license. Okay, and here's my last slide. That's actually not my last slide. Okay, so I'll just real quick, not all launches are the same. You have to talk with the integrator and find out what are the requirements, because they're all unique. You don't want to do any harm. You can read that in the presentation later. Okay, go for my last summary slide. Okay, so I just want to repeat what's been said earlier. Is in the earth science community, they are taking CubeSats very seriously now, and the timing is right for this, because they're about to complete their second earth science decadal study, and that will be in 2017, December 31st, most likely. That's their due date. And so what's in that document will likely influence the next INVEST call, which will be in 2018. So definitely look out for that, pay attention to that. And ESTO is science-driven, so when you write a proposal, make sure you put a lot of time and effort into justifying the science. It's not just about the technology. And I think I will leave it with thank you for having such a sharing community, because I think that's really helped a lot of these projects that don't have very much money and need to learn all the lessons that everyone has. And although this was all very top level, all the details of what's been learned in all these projects will get incorporated into the systems, the Spacecraft Systems Virtual Institute that Bruce Yost is going to be talking about. And I will just leave with a quote from one of my PIs. Thank you very much. I don't think there's time for questions, but I'll be around today. Thanks.
All right, thank you, Pamela. Our next speaker is Bruce Yost of NASA Ames Research Center.
So I thank the organizers for allowing me to just introduce the next topic as a new endeavor that NASA is kicking off actually this year. The Small Spacecraft Systems Virtual Institute was announced late last year, calendar year, and in January we actually got started, we received our funding and got started pulling together the various components of the Institute. The Institute's elevator pitch for me for right now, the purpose of it is to collect, organize, and disseminate information about small sats that's useful to the larger community and specifically to the NASA, all the NASA projects that are going on in small spacecraft. It is not limited to just CubeSats, but as you all know here in this room, I don't have to say it, a big part of NASA's portfolio is in CubeSats right now. The other thing I need to just make sure that everybody understands, even though I live and work in the Bay Area and some of the servers may be there, the Institute is agency-wide, working with all the centers and other government agencies, industry and academia to try to add value to all of this information and knowledge that's out there that's sometimes easy to find, sometimes not so easy to find. So here's the charter. You can read this. I'm sorry, I don't have a lot of cool pictures yet, but I know where to find them. But the main idea here is to advance the clear communications across all the different things that are going on specifically within NASA. There's a lot of things that we don't want to duplicate. There's a lot of things that we may not be covering that we want to cover. So, if we don't know about that, even amongst all the NASA players, it's hard to manage through there. The other thing I'll talk about more later as well is to create a space or a bucket, if you will, a library maybe, of all this information that's very dynamic and is out there so that people don't have to spend as much time finding the right person to talk to or finding that paper that was needed or understanding what's going on within the different technology disciplines. The other thing we want to do is, again, to enable not just the NASA centers, but the public at large, which is obviously the academic groups and the industry groups, have same sort of access to this information for their benefit, because that in turn then benefits NASA. There's another area that I haven't really touched into yet, only being up and running for maybe 3 months, and that's to reach out to the other government agencies who have substantial portfolios in small sats. The AFRL group, the NRO groups, the Army guys, the Navy guys, to see how we can leverage and share information back and forth to kind of help us all out. And I mentioned, of course, academia and industry are critical to this whole ecosystem. So the strategy is to collect tools. Different tools have been made by different centers or different groups, make those publicly available. Collect information, where do I go to find out about upcoming NASA solicitations? How do I get funded? And then knowledge, things like parts databases, lessons learned databases, other kinds of things that help people to design their mission and then actually go from cradle to grave with it. We want to also provide a place for industry and academia to say, well, where are you NASA guys going? What are your objectives? What are your missions? And if we can communicate that clearly, then that gives some guidance on what kind of investments or what kind of research is of interest to NASA, so that we can get everybody kind of pointed in the same direction. To do that, we're going to create focused working groups for certain topics or certain areas as needed, as they come up. We're going to use virtual collaboration tools to get everybody together, exchange the information, support publications of information and data, and just try to get that all organized and support the community at large. And then the final kind of strategy area is to help enable partnerships that you heard from Jim Ryder this morning. If you don't know who else is doing something, you might not know that there's a partnering opportunity there. We hope to help to facilitate those. So for year one, we started a little bit late in January, so we've got a pretty prescribed set of tasks. The first one is to set up the portal, which I'll show you in a second. That's done and working. That's going to be an evolving thing because, as you know, the information is very dynamic. It turns over very rapidly, and there's a lot of different changes that will happen, so that portal won't be very static. It'll be dynamic as we go forward. Within NASA, there's a small spacecraft community of practice that discusses things about best practices, testing philosophies, reliability, which I'm going to talk about later on as well. So we're going to pick that up and manage that and keep that running and hopefully even grow that community of practice. Again, maybe not so much on the technological side, but on the process side. As I said, how do you do the right testing? What's the way to deal with reliability, mission assurance, that sort of stuff. There is also a small spacecraft coordination group that's being stood up at headquarters. The Institute is co-funded right now by both SMD and STMD. The STMD program exec is right here, Chris Baker. Larry Kepko from SMD is, some of you may know Larry, is the SMD point of contact. And there will be a lot of tasks that may come to the Institute that the coordination group may need for information, surveys, working groups, all kinds of stuff like that would support the headquarters team. We're also discussing with HEO a similar sort of arrangement, and I predict that probably will happen, if not this year, maybe next year. And then the state of the art. I think everybody knows about the state of the art. The state of the art was published, I think, the first time in 2012 and then 2015, or something like that, or 2013, 2015. What we plan to do is to take the state of the art report, and instead of publishing it every other year, is to try to make that information available continuously so that people can submit to a database that can then be scraped or culled for that information as it becomes available, instead of waiting every other year. So here's an eye chart of the portal. I don't know, oh, you can't even read it. Please come by the booth. So the URL is pretty easy to remember. It's nasa.gov/smallsat-institute. It's up and running. This is just a screenshot of it of a while ago. I apologize for not being able to read the URL, but I'll walk through the different elements that are on there right now. And even this is pretty small. But the first part of it is a small spacecraft body of knowledge. That includes for one thing, a parts database that we're collaborating with AFRL small spacecraft portfolio with. You get a lot of questions like, who's testing parts? Who's doing the rad hard testing? We use a lot of COTS in this industry, but there's not a real easy way to find out if someone's tested a chipset to a certain radiation level, or if someone's done a life test on a set of wheels, that sort of thing. So we're going to use that, again, to publish the state-of-the-art report continuously, but we're also trying to capture that information from vendors and others so that information can be made available to the larger community. We'll be issuing RFIs to the industry or academia that says when your widget is ready and you want it to get the message out to people, send it to us. We'll put it in the parts database that everybody can then search on. The body of knowledge will also have a lessons learned database. You saw a little bit of that from Pam's talk and others. We're going to try to collect that for everybody's benefit. So please keep an open mind with that. We'll do it in a respectful way, but we hope to do that. And okay, quick. And then so there also on the page is a link to feature stories. Let me put my glasses on. There we go. Also, we want to announce solicitations for people to propose to different smallsat opportunities across NASA. We'll keep that on there. We'll work with CLSI and others to try to publish information on how to launch or who to talk to about a launch, how that process works. The working groups, I'll talk about that next, the next slide, and we even want to have a seminar series, potentially, where we have invited speakers come and give presentations about smallsat applications and technologies that we'll capture and publish for everybody else. And then we do have virtual collaboration tools that we can use to facilitate a lot of working meetings. And finally, we'll have a place for folks to go find other information even outside NASA, to this conference, to the SmallSat conference, to other places like that. So I just talked about the state-of-the-art report. There's the website. Come talk to us at the booth if you have any questions about that. I already mentioned that we're partnering with AFRL to create a parts database, a components database. Again, like I said, that will be self-submittal. We'll just put an RFI out. You respond with your information. We'll put it in the database and let everybody else see it. These are a couple of examples of working groups. There's already one working group that's up and running. It's the Small Spacecraft Reliability Initiative or Working Group. They had their first meeting, their first face-to-face meeting in February at Caltech down in California. And this is co-chaired by Mike Johnson from Goddard Space Flight Center and Pat Beauchamps from JPL. There is also there's some industry academic participation in this working group, as well as some other government agencies. The idea there is to try to understand how could we advance the reliability of small spacecraft such that they can be used for peer-reviewed science missions on the NASA side, and then how could they be used for operational applications on the military side. We're talking about a small sat access to space working group that's kind of germinating right now. The idea there is to help the agency come up with a coherent small sat rideshare policy, not so much for CubeSats. I think we've got that one pretty well in hand, but there's another class of spacecraft coming along that don't have the advantage of having a process in place to do that. And there's other ideas that we're kicking around, including the cross-linking from small spacecraft to existing constellations in orbit, such as Iridium and Iridium and Globalstar. And someone mentioned it might be good to have the different groups trying to do that come together, share notes, and then also talk with some of those service providers to see how we can take advantage of that. Here's just a quick chart of some of the projects going on by center. I'll leave it to you to read in the presentation package. Again, just when you do searches on things, you get a little bit of different results. There's 146 projects within the NASA TechPort portal when you just search on small spacecraft. When you say CubeSat, you get 121 projects that are active. So part of our job is to collate this, make this information easily available to everybody, policymakers, investigators, technologists. So I just give this as an example. And again, this last chart is the same sort of example of the first chart. There's quite a lot of, this is going to be a very fun job because there's a lot of information out there to be collected and organized, but I'm looking forward to it. So I think that's my last chart. I invite you to please come talk to me or Juliana at the NASA booth. Email us with ideas, things that this institute could do to benefit the community better, things it shouldn't do maybe, that it is doing, because it should focus on other priorities. And I look forward to maintaining and having a lot of contact with everybody in the community in this room. Do I think I have time for questions? Okay, if not, thanks for your time.
Thank you. Next, we have Garrett Scrobot from NASA headquarters.
As you might guess, a CubeSat is shaped like a cube, about 4 inches wide, long, and deep. That's called 1 unit, or 1U. Small enough to hold in your hand, and very light, around 3 pounds. And like building blocks, units can be combined to make bigger CubeSats by stacking them into 2, 3, or even 6 units. Once in space, CubeSats can open up all kinds of tools: solar panels for power, communications antennas, telescopes, and more. CubeSats are great because they let schools, universities, and other teams launch their very own missions, and who knows what they'll discover. CubeSats are also made from standard, low-cost parts that are easy to get and tested for launch safety. Some NASA launches carry spacecraft that don't take up all the space on their rockets, which leaves plenty of room for tiny CubeSats. Build a CubeSat, catch a rocket ride, and you become a space explorer. How do CubeSats get into orbit? NASA's CubeSat launch initiative gives CubeSats a free ride on rockets that have room and fuel to spare. It's like a rideshare program. We're already going into space, so your CubeSat is welcome aboard. Once a CubeSat has a seat on a flight, it'll be loaded into a launcher container on the rocket. These containers have a long technical name, but let's just call them dispensers for short. Each CubeSat is stacked into the dispenser like a pea in a pod, with its power turned off until the right time during the mission. After the launch, once the rocket is at just the right elevation, the main spacecraft separates and heads on its way. Then it's the CubeSat's turn. A few seconds later, the dispenser door springs open, and another spring inside pushes the CubeSats free. Each CubeSat's transmitters turn on, and its power and other tools will begin to work. Then your CubeSat is ready for its mini-mission in space. What does a CubeSat do? That's the great thing about this innovative approach to exploration. It's up to you. A CubeSat is kind of like a cargo container on a ship. It has a standard size and shape, and you can pack in whatever you want. Similarly, with CubeSats, it's what's inside that counts. And it's up to you to decide what you want to discover. Maybe you want to have a weather satellite, measure Earth's gravity, or take pictures from space. Maybe you'll turn your attention to the moon or the solar wind, or be on the lookout for incoming asteroids. With CubeSats, you get to define your own space adventure. Keep your goal focused though. CubeSats are quite small, and you have to pack in all your science tools, wiring, and computer processors, plus add power and communication systems for them to work. But it's not too hard. Even kids in elementary schools have built CubeSats. Someday, these mini spaceships may travel all over the solar system, collecting data for Earthlings everywhere.
One of the things about CSLI and Launch Service Program is we do a lot of outreach. And these are now, we feature these on the launch campaigns during the web segments and also during on YouTube. So these were our latest ones. We're now in the process of developing more to get into the classrooms to get students more involved with the CubeSat stuff. So like I said, I'm Garrett Scrubot. I worked at the Launch Services Program. However, I'm at the headquarters at the Advanced Exploration Systems now, doing a little bit of a detail work, learning how headquarters treats our CubeSats, and so we can make things better for everybody. So, figure this one out. There it is, forward. All right, like I said, the CubeSat Launch Initiative, you've heard about it in a couple other presentations. We are providing opportunities for educational, nonprofits, and also educational institutions to be able to fly CubeSats on various vehicles as auxiliary payloads, and now as even going in as primary payloads. So we have reached that mark. So what I'm going to do is just give it a little update of where we're at today, what we've done in the past. Some of you guys have seen this, but as you can see, this is where we're at, where our CubeSat missions on how many we've launched. We've done 13 Alana missions to date, educational launch and then a satellite. And our last one was OA7 on the 18th. And we have 3 cubes waiting for deployment here shortly. So, you know, within NASA, you always got to have metrics, and measure how things are being done and how good you are, how bad you're doing. Here where we are, when we first started the CubeSat Launch Initiative, it was probably 2010. But before that, we had our first selection, which several of you remember the Alana 1 mission, and I know Dave, and where's Ben? He's out there somewhere. Had those good CubeSats on it. And that's what's first selection. That was my doings. Okay, I went out and just found cubes and we launched them. And NASA goes, "You can't do that." So we had to go start the CubeSat Launch Initiative. We had our 8th call awards back in February, and as of today, we have selected about 152 on the list. We do have some adjustments. Some cubes don't make it. They say, "Hey, we're not going to make it. We don't have the funding." They fall off. They go find their own ride. That's great. You know, more we can do, better. So that's where we're at today. From that, we've flown 49 CubeSat missions, not cubes, but CubeSat missions. And currently, we have 49 on manifest through 2018 right now. So we're running about 32% of our CubeSats have been launched. 64 have been launched, manifested, and we actually have like 74% offered. The reason the number is so low on the offer is because Call 8 just came out in February, and we're now in the process of developing offers for those cubes as well. Okay, here's our manifest. As you can see, we launched OA7. We got JPSS2 coming, JPSS1 coming up in no earlier than August, but I believe it's in September now. And then we have SpaceX 12 coming up later this year. And as you can see, we have Marco. It's not part of the CubeSat launch initiative, but it's 2 cubes that's going to be going along with InSight to help with the relay of data back from InSight as it goes into entry and descent and landing phase. It's going to have 2 cubes flying by and collecting the data and sending it back to Earth. We're managing that. And we have a couple of them in the gray right now, what we call our in-work missions. Tropics, which was discussed earlier today a little bit. 12 CubeSats wanted to go to around a 30-degree inclination at 3 different orbital planes. And we're looking at our ISS. You know, when you guys saw this chart previously, it wasn't as populated in the ISS regime. But now here recently, it's been a very good factor for us, and we're starting to move more of our flights into that 51.6 degree, 400 kilometer. It's given us some good science. So we have 2 right now. We're working on the 3rd. And then down in the ORS, we're on the STP-2 mission. We got a couple cubes flying on that one. And then we're starting to populate into the commercial world. As we'll see a couple charts here on a lot of 19 and 20. We have a couple commercial vehicles, and we're also in work on our next U-class payload opportunities coming up for later in 18. So what's our recent launches? We had a good dry spell. See, we last launched May 2016 to the ISS. That was a deployment. Actually, it launched in December of 2015. We had 3 good CubeSats there that we flew up. But then here recently, we had the OA7 Alana 17 mission that flew CXBN2, IceCube, and CSunSat. So you probably have heard about those guys here recently in the last couple of days. So where are we going? You know, we've got a very busy next year and a half. The team's been working very hard on getting these manifested and ready. We actually got a readiness review, mission readiness review on the Friday and Saturday for Alana 14, which will be launching no earlier in August, more in September. We have the Falcon flight. There's a cubes flying there. As indicated, we do have the 6 U's on that one we'll be flying. Let's see, who else we got on there? And then we got the, we don't know when that Falcon Heavy is going to go, but it's no early in September. It's probably going to push out a little bit. So recently, the launch service program with the Science Mission Directorate went out and did a procurement. I talked about this last year on the Venture Class launch service. We did procure 3 launch vehicle services, one of which is the Electron through the Rocket Lab, and we are able to put 10 CSI payloads, and we have 4 other of our partners on there as well. We're scheduled for no earlier than November. We're supposed to be either the 4th or 5th flight in their cadence. I don't believe they have launched their first one right now. They're still working on it, and I believe it's upcoming here shortly. But as you can see, we have a whole host of payloads. This was very good for us because we were able to take our manifest list, which was getting into a backlog situation, and be able to put a lot of CubeSats on these vehicles as primary payloads. So we're able to do a little bit more than we are when we do a NASA end-to-end mission. We evaluate pressure tanks, propulsion, batteries, different types of scenarios on here, and make sure it doesn't hurt anybody else or do any harm with anybody else on the mission, but we take a look at those. And then we also have Alana 20, which should be on the Launcher 1 with Virgin Galactic. And as you can see, we have a host of payloads on here as well. Some of you may recognize the names. And then we move into April of 2018 with Alana 23. And we have several of the SDOs on here. The Rain Cube, the Tempest D will be flying, as well as other universities, Opal, Rascal, Sortie. So this is going to be a very populated mission for us on going to ISS, and we're hoping to have plenty more. The plan is probably to go, to go and continue on with the ISS and start, try to get a cadence of every 2 years, like early year and then late year flight time. So ISS is good. It gives us 51.6 at 400 kilometers. However, it doesn't meet everybody's needs. So we need to find the SunSync launches. We do have JPSS-1 and ISAT coming up. However, beyond that, how do I accomplish these orbits for our customers? And this is an RFP. The draft went out, I think, last week for comments, and it's for our U class, where we're going to try to award a primary mission. And yes, the consensus on this one is for Ceres and Saras as the primaries for this. And then we have a maximum of 24 U on the mission, which gives me 12 U of additional payload mass to go take a look at. And we've already have, what do we have on there right now? 12, 15, 18 U of opportunities for other people who want it. So we'll be able to fill that with a couple of backups, which will then flow into having an opportunity in the FY20 and 21. We have options for those. So that gives us 3 years of SunSync orbits to accommodate the mission sets and up to about 72 U. We'll continue to work with the ISS and work those, because a lot of the calls that come in for educational and the USEPs, they like that orbit. As you heard earlier, for orbital debris, it's really good. It's below the station, and they get their science, and they burn up in about 10 months. So we try to keep a track of our opportunities and where we're at. Now, I can't go buy all these opportunities. I don't have the funding to go buy every one of these, but I identify where they're going to lie. So when I start looking at the manifest of what's on the backlog or who's ready at what time, it gives me the sense of where I need to go put funding in to identify launches. One of the things you can see, ESPA develop a carrier. There are going to be ESPA rings on flights coming up in the future. I know JPSS-2 has one. I believe SWAT has one. They may already have primary payloads, secondaries identified for it. However, I want to have a mechanism or a system in place that if one of those payloads falls off, that we can just take a rack of cubes and just put it on the side and be able to fly within a few months of the delivery date. So this helps us keep a track of what the opportunities are. As you can see, 2 every year for the ISS, and in the U class, we are working on the contract for that. And then VCLS is going to be some opportunities that tropics going to 30 degrees, if a VCLS vehicle is procured for those, there's going to be extra performance on there. And how do we handle that extra performance? Do I get a little bit of it? There's other agency assets go fly on it. But that 30 degrees is going to be there in the future. So, basically in a summary sense, what I like to look at is that the U's launched. And we started back in 2011 launching U's, and we go all the way up to 2017. We did about 80 U's so far, which is in the 49 missions and 13 allotted missions. However, over the rest of 2017 and 18, we have about 155 U to launch. So we will well double what we've done in a year and a half, what we've done over the last 6 years. So as you can see, it is definitely growing. We do have budget. It's there a little bit. So we're continuing to move forward as much as we can. And with that, I saved a little bit of time, so I'll take any questions you may have. If not, we'll bring the next speaker on. Yes, sir, in the back. Our orbit for Electron is 500 kilometers at 98 degrees. That's the orbit we're going to be offering for this payload, yes. And when we put the call out, we sent a note or a letter or email to the cubes and said, this is the orbit, is it acceptable to you? And they said yes. And so then we manifested on that. We have a database that has all the requirement bases for the cubes, and so we kind of know which cube would like which orbit from a perspective of a desired orbit and an acceptable orbit range. So if we can get something with that, we'll offer it to them, and then they can determine yes or no. Yes, sir. The U-class payloads? It's going to be 95 to 102 at an altitude that does not violate orbital debris policy. Okay, so basically that 500, 550, 450 area. And we try to hold it wide enough so we have some good competition. Yes, ma'am. We had cubes on our list to go to GTO and GEO. It's very costly to go there, where I have probably 20, 30 that want to go to low Earth orbit, and it would probably take my year budget to go do one cube. So we identify what bracket range meets the needs of the most of the cubes. Now, if the cube comes with some money, all right, you know, CSLI has a no-cost effort to the cubes once you're on the list. However, if a cube has funds themselves and they bring it to the launch service program, we will go try to find you a flight as quick as possible. Anything else? I think the hook's coming, so I got to go.
All right, next up we have Dan Adams from ULA.
Afternoon, everybody. My name is Dan Adams. I'm excited to be here to represent United Launch Alliance, the nation's premier launch service provider. I know all of you are familiar with ULA. We've launched now 119 consecutive successful missions, 100% in 10 years, which is awesome. And it's been a real pleasure over the last 2 days to see presentation after presentation have a picture of an atlas. It's just pretty fun, I have to say. And most often, you won't work directly with ULA. You'll be working with our partner TIVAC or an integrator like NanoRacks, but ultimately when it boils down to is we are your ride to space. So I'm excited to talk a little bit more today about our CubeSat program, CubeSat Express. So this is a video of Atlas Vehicle 85. I'm not going to show it because I don't think it's going to work. And I happen to know you're going to see it a little bit later, so we'll just build that suspense. This was flown from Vandenberg Air Force Base a couple of years ago to LEO orbit. It included the NPS Cool CubeSat dispenser, and it was integrated by our partner TIVAC. Couple things I'd point out. You can see in the lower right-hand corner of that thumbnail the Aerojet Rocketdyne RL-10, nozzle, which is I'll come back around to that in a little bit. And even having this picture was a challenge, but it was a cool thing to be able to put a camera on the dispenser and capture it to be loaded to YouTube, which is pretty fun. So anyway, let's talk a little bit more about CubeSat Express. So CubeSat Express is our vision for enabling rideshare launch for the CubeSat set. Ultimately, our goal is that every Atlas vehicle, and ultimately the Vulcan vehicle as well, Vulcan Centaur, then Vulcan Aces, will fly CubeSats. 24U of CubeSat capacity over, say, 8 to 10 missions a year. As a standard service, that's 200 plus U on a consistent, reliable launch vehicle. It's going to change the market, and we're really excited about it. We think it's going to be a very cool thing, and it's not very far out. So, you know, this is really optimizing our ability to take mass to orbit. It's loading up the truck, if you will. It's a train to space, as Tori likes to say. And, you know, again, it's leveraging our core competency, on-time, reliable space access for the big guy up front and for the little mission on the aft bulkhead carrier. So as a standard service, this is going to be pretty powerful. So this is a little bit more about our CubeSat Express program, which leverages the aft bulkhead carrier platform, or ABC. This is a graphic of the Centaur there on the right. It's the second stage vehicle on the Atlas V. The payload envelope is that yellow shaded box there on the right side. And it, what's pretty neat about how we've done this is, in the past, Centaur used to fly with 3 spherical helium bottles, and we were able to condense those 3 bottles into the 2 oblong bottles and enable that real estate on the launch vehicle for this purpose. and to enable some other cool applications of missions that we're flying there as well. So this chart speaks to an older configuration that's been flight proven, and we'll see that in a chart here. But it was the NPS Cool dispenser setup, and you can see how that payload envelope space is canted a little bit off of the center line of the vehicle, and that was done to prevent collision with the nozzle on the rocket engine, and that's why I pointed it out on that thumbnail. But now, in our new iteration, they're going to be launching, or rather dispensing perpendicular to the launch vehicle, which changes the game a little bit there. And that's, again, with our partner TIVAC. So how have we changed CubeSat Express as we've been evolving, and or CubeSat launch capability, rather, in evolving to CubeSat Express? Well, really what it's been is it's a continual evolution to enable a lower cost, operable approach. So that Atlas 58 that I showed, and you'll see the video of here in a little bit, flew with NPS Cool. You know, that's 24 U of CubeSats, flies on the aft bulkhead carrier. It was a great system, it's flight proven, it's flown 4 times. Well, the problem with that system is an operational one, and it's as simple as it weighs 100 pounds. And it's a really difficult thing for our technicians to install a 100-pound system late in flow. So by simplifying down to the TIVAC NLAS dispenser, which is about 50 pounds, and NLAS Mark II is about 50 pounds as well, we can enable late in-flow integration, which provides a lot of flexibility, and it simplifies our process quite a bit. So the evolution of the aft bulkhead carrier it's a pretty natural progression to reduce mass, simplify, and reduce cost. The point is really that this evolution is continuing to serve the rideshare multi-manifest CubeSat market, not generally our primary customer, but it's something that we're excited about and something that we're interested to serve because we have the capability on the launch vehicle. So the next time we're going to fly here, as you see, is the NASA Marco mission, which we're really excited about. There's been a lot of conversation about that. That is going to fly with the NLAS, not the NLAS Mark II, on the Heritage aft bulkhead carrier, not the new aluminum design. So how does CubeSat Express work? Well, really CubeSat Express is a partnership between ourselves, ULA, and TIVAC. And TIVAC does a lot of the heavy lifting as far as the CubeSat community is concerned. They manifest our CubeSat payloads, they provide the dispensers, and they perform our integration functions, test, etc. We at ULA then integrate the full system to the launch vehicle, ensure do no harm with the primary mission, and make sure that everything is ready to roll and execute our core competencies, which is launching on time and doing things really well. So the cool thing about CubeSat Express that we're really excited about is that we're going to be offering 24U on every Atlas mission, but of that 24U, 3U will be awarded free to STEM programs. And we've currently awarded 5, one to University of Texas El Paso, one to Louisiana Lafayette, Purdue, University of Michigan, and CU Boulder. So that's pretty exciting. I know that they're ready and waiting for our first manifest opportunity, which we're hoping is coming up soon. And then from there, we're excited to really operationalize the program and bring around that 3 free STEM CubeSat launch every Atlas mission as a standard service, in addition to the commercialized 21U that flies with the program as well. So that's pretty neat. So we're continuing to improve, and we have some activities that are currently ongoing. The CDR for our aluminum strut design, the aluminum aft bulkhead carrier, is going to be taking place next month, and we're excited about that. It's going to make it ready for launch as soon as later this year, but more likely in 2018. The system will be ready as soon as we have a manifesting opportunity. We've also implemented some class analysis on loads and thermal cycles, provided that to TIVAC for their testing and integration requirements, and it's a pretty big envelope. We can ensure then that everybody's successful with the loads and the thermal environments that they'll be seeing on orbit when we launch. And we're developing a ConUp for a 12U dispenser, because currently our system is capable of hosting only a 6U dispenser, and we have interest. There are a couple of our traditional customers are interested in flying 12U to enable that mission space that can't quite be served by the 6U dispenser. Unfortunately, similar to the NPS Cool, 12U dispenser requires an earlier integration cycle. It's too heavy to be mounted to the vehicle when the vehicle's in a vertical position on the stand. So that does provide some complications, but it enables that mission space as well. So the last thing on this chart is one that I'm really excited about because it just came up in the previous conversation. It comes up time and time again, and that is that our manifest primarily flies to a GTO orbit destination because that's where the primary satellite wants to go. And traditionally, we separate all secondaries after the primary has been separated from the vehicle. So if you're CubeSat, maybe you want to go to GTO, but more likely you don't. And so that creates some challenges. It limits our customer base and the customer base that TIVAC can bring for us. But we're excited to be about to start exploring the option of separating CubeSats and secondary payloads in a park orbit before the primary mission is injected into its final GTO transfer orbit. So that's going to enable some pretty cool stuff. It'll enable us to fly a broader range of mission space for the CubeSat community and also some other potential rideshare applications. And it really just broadens our ability to meet customers' needs. And it enables a couple of different flexible approaches for CubeSat launch. So we're pretty excited about that, and that's going to be starting any day now and should be completed here this year yet. So one more content chart for you, and I really like this chart because it helps provide some context for the consideration that we have when we process through, can we fly rideshare with our primary mission? And really there's just a handful of constraints, and we're working to burn down all of those constraints that we consider when we're exploring rideshare. Obviously, first and foremost, does the primary leave enough mission performance on the launch vehicle that we can add extra mass? If the primary takes every pound of performance that we have, we're not going to be able to fly rideshare. That's as simple as that. The primary is the primary. They're paying for the launch vehicle. Next is really that orbit consideration that we talked about, and we're hoping to improve flexibility with that constraint in that park orbit study, but currently it is a constraint. You know, if we're flying to a GTO, it's difficult for the many in the community. And then lastly, one of the more arcane constraints that we have is this ordnance circuits that are available on the Centaur vehicle. We have 12 circuits that are part of our avionics suite, and every primary mission uses a different set of ordnance circuits for their requirements. And we need those ordnance circuits to trigger the release and dispenser to open the doors on the dispenser. So if we don't have the circuits available, it makes it really difficult for us to fly CubeSats because the door's not going to open. So that's not good. And there are some ways around that. We can consider a sequencer and some other technical approaches. So that's not a huge constraint, but it is a constraint that we consider. So, you know, I just wanted to provide a little bit of sense of our thinking and our logic flow approach every time we assess a manifesting opportunity for CubeSat Express and for other rideshare opportunities as well. And you know, and the point is here that while these traditionally have been consistent constraints, and those are the things that we always point to, no, that we don't have the ordnance circuits, or no, that orbit isn't going to work. We're working to burn those barriers down and create additional flexibility on our manifest. So with that, I'll throw up this chart, and there is an error on this chart. I'm well aware of that, but it's my get off the stage chart, and I'd be happy to take any questions, and if not, thank you. Appreciate it. Any questions? That's the objective. Great question. So all of those constraints that I just showed on that logic flow remain constraints currently. And our primary customers, with our historical in-place contracts, it becomes a little bit muddy and difficult. So this is somewhat aspirational. You know, we're leaning in, and this is our objective. It's championed by our CEO, and it's our goal. And so every commercial customer that we intend to fly CubeSat Express on every commercial customer, and in the future, our traditional customers, U.S. government, civil, and Defense Department agencies as well. Yes. Purposely vague, I would say. Yeah. So the question was, is there a more specific definition of STEM? And what I would say really answer that question is, you know, that's for ourselves and our partner TIVAC to kind of to define what STEM means. As you may have noted, the 5 that have been awarded to universities, but that doesn't necessarily preclude high schools or other education programs going forward. Great question. So the question was, is the Centaur vehicle, does the Centaur use a burn to put it into an escape trajectory to deorbit, or to get it out of the collision avoidance maneuver, right? So, and really, it depends on the mission profile. And so in some cases, we do an escape trajectory. In other cases, we do a deorbit burn, and it re-enters. But that's feasible. All right, thank you so much.
All right, next up we have Justin Carnahan from TIVAC.
Hello, my name is Justin Carnahan. I'm from TIVAC. I'm going to be talking to you guys today about Enterprise, a mission we launched late last year, actually November, out of Vandenberg, just a short drive down the road. See if I can get this changer to work. Hey, look at that. So TIVAC, got a really good introduction from Dan, so thanks for that. We're a small satellite company. We're based here in California. We have 2 offices here. We have an office in Irvine focused on satellite development and manufacturing, and an office here actually in San Luis Obispo. It's where I work out of. It focuses on launch integration. That's what I'm going to talk to you today about. We're 100% US owned. Some information about our launch office here. Our principals have extensive launch integration heritage back to the early 2000s, the early CubeSat launches out of Russia on those Neppers, the Rockets. And we've really been focusing on missions from suborbital to interplanetary. For example, the InSight Marco mission and SLS CM1, we're supporting those guys. We've launched over 80 dispensers, supported over 80 satellite programs, 80 different programs. So we've really seen all walks of life, and you guys have been throwing us all sorts of curveballs, and launched over 155 satellites to date. 11 different launch vehicles, you name it, we've been on it, and 9 different ranges worldwide, and we have over 10 programs ongoing right now. There we go. So what I want to talk to you today about is the ABC, kind of what Dan just talked to you guys about. Leads in well to CubeSat Express. And ABC, it's an acronym for Aft Bulkhead Carrier. And it's that, as Dan indicated earlier, it's that, I don't know if this laser works. Nope, doesn't. It's the accommodation on the aft end of the Centaur, the upper stage of the Atlas V. It's actually the upper stage of the Vulcan, too, for the first stages. It's an interface which is capable of lifting 80 kilograms to orbit and services 1 to 12U CubeSats. And also has a 15-inch bolt circle for single separating spacecraft as well. And you can kind of see in this picture down there from left to right, kind of the integration scheme. On the bottom left would be CubeSats. You can see 1U, 2U, and 3U CubeSats there. The middle is the dispensing systems. This particular image has P-pods. And on the far right, you can see the Centaur itself with the green box indicating where that aft bulkhead carrier is. So the heritage to date and kind of the evolution of the interface itself. We've had 100% on-orbit success rate if we've flown 5 missions and serviced 53 CubeSats to orbit as auxiliary payloads. The CubeSats have been NASA, US government, university, and commercial payloads, and have mission partners ranging from NRO OSL, NASA, Cal Poly, SRI, NPS, ULA, and Aerospace Corp. It's really been a team effort, and it's really been demonstrated through this tight team that we've been able to enable these missions. So the first mission of the Atlas V ABC plate was L36, and the secondary mission was OutSat. On this mission, we launched in September 2012 out of Vandenberg Air Force Base, again about 45 minutes down the road, and we were able to launch 11 CubeSats. This mission really started it all. We were able to develop the processes, develop the kind of integration schemes to get the spacecraft on the vehicle, and that's really no small task on these L missions. The next mission, L39 GEMSAT, was a follow-on effort, and that launched in December 2013. We were able to expand kind of the baseline approach and enable more advanced CubeSats to orbit, able to enable some higher power transmitters, just for example, to get them integrated on the vehicle. This was also a Vandenberg Air Force Base launch, and we were able to fly 12 CubeSats. Continuing the effort and kind of the evolution of the interface, the next mission was actually an Air Force mission, Space 5 Ultrasat. This is where we kind of took the integration effort and were able to expand it to the eastern range, to Cape Canaveral. We, again, continued to improve the process, enable more advanced capabilities, and we launched 10 CubeSats out of Cape Canaveral. L55 is actually a pretty cool mission because we kind of took the baseline approach and we actually added a camera. We were able to tweak one of the cameras on the aft end of the Centaur and actually view the deployments of CubeSats on orbit and actually have that video here in a chart, assuming it works. I've been told it may or may not work. That was out of Vandenberg as well, 10 CubeSats. And then kind of the focus of today, after these charts, is DigiGlobe Worldview 4 and the secondary mission Enterprise, which is a commercial mission effort, which launched out of Vandenberg in November 2016 and flew 7 CubeSats. We actually flew a different configuration than the previous missions, like Dan indicated earlier. You can see those NLASs right there on the vehicle that's actually looking up beneath the Centaur onto those 2 dispensers. So here we go. So here is the on-orbit deployment video of Grace. Let's see if we can get it to play. Hey, there we go. So we have a video on the aft end of the Centaur facing out towards space, and you can see those CubeSats each deploying into orbit. That's probably the best picture right there. You can see the sun illuminating just right. The background, some glint. And the separations are actually on orbit a couple minutes apart, about 4 to 8 minutes apart on orbit. This video was cropped just so it kind of sped it up. So maybe we can watch it one more time. It's a pretty quick video. And so again, those doors lock in place. Those are P-pods. We're launching a variety of 1U, 2U, and 3U spacecraft. This was L55 out of Vandenberg. Great. So kind of overview of the mission Enterprise I want to talk to you about today. This is the first NRO OSL flight utilizing a commercial rideshare. That's a pretty big thing to us and a big thing to the community. Really the mission was put together with a number of different mission partners. The primary mission was Worldview 4 DigiGlobe, and that was the mission on top of the vehicle. The secondary mission Enterprise was sponsored by NRO OSL and integrated by Cal Poly and Tyvek. The launch vehicle, of course, was the Atlas V Centaur, a ULA Lockheed Martin vehicle, and launch date November 2016 out of Vandenberg. So the graphic here on the far right is a pretty neat graphic. NRO OSL again sponsored the mission. They were able to provide kind of mission oversight. They contracted to Tyvek, Cal Poly as a commercial broker to perform integration engineering, supply the dispensers, payload processing, mission assurance, and we turned around and actually contracted to ULA to provide the launch mission assurance as well as integration engineering. That's a pretty cool thing to say that our community come together and we were able to contract ULA and their willingness to support us in rideshare. Another really big thing demonstrated for Enterprise was the schedule. We were able to drive down the typical schedule that aerospace lives by. Aerospace lives in years. We did it in months. We turned around from ATP contract turn on to first launch attempt in 10 months. And I say first launch attempt because after the first attempt, Vandenberg kind of had a Burning Man of sorts and went down for a couple months late last year, and we ended up actually really flying in November. So some pictures, everybody likes pictures, just some mission highlights from the actual hardware deliveries of the spacecraft here in San Luis Obispo. So kind of on the top left, we took the hardware here at Cal Poly, integrated it into the dispensers. The dispensers were then kind of checked out, bagged, packaged, and escorted directly to Vandenberg by us. We actually took it to Vandenberg right at the base of the vehicle to the mobile service tower at Vandenberg, marched it up the stairs, actually up the elevator, and we're able to unpackage it there. And you can see in that bottom left picture that American flag is actually the skin line of the Atlas V. Once we were able to unpackage, do final checkouts of the hardware, we handed it over to ULA. ULA then, the technicians took it inside the vehicle by hand, and were able to lower it into the interstage adapter, carried around to the integration location. And the picture on the bottom right is actually a picture of showing the technicians lifting it above their heads, installing it on the vehicle. And this is a pretty important capability to demonstrate. We're able to reduce integration timelines on these Atlas vehicles down from L-3 months for CubeSats to L-1 month for CubeSats. On-pad integration isn't new for ULA. We do it on the Delta IIs at L-2 weeks, but for the Atlas Vs, it was pretty impressive to be able to implement a process change to improve a secondary payload's condition to orbit. The picture on the top right are those dispensers on the vehicle just prior to final checkouts. You can see the harnesses kind of wrapped around and pigtailed up. Those harnesses were, of course, plugged in before launch, and we launched at Vandenberg again in November 2016. Some of the improved capabilities that we were able to lean against and demonstrate for enterprise: lower cost, reduced environments, faster integration timelines, again, that on-pad integration. Some of these things that were impossible 10 years ago really have become the norm today. I mean, we're talking about interplanetary missions, we're talking about ISS deployments, and U.S. commercial launch. It's quite an achievement, I think, for the community, and really attributed to the successful and ongoing efforts with U.S. government stakeholders, folks like NASA, folks like the NRO OSL, to really help push us, provide the opportunities that we can really capitalize on and develop a community around. On-pad integration, again, was one of the big things demonstrated for enterprise. It cut that integration timeline down by a factor of 2. We took it down from 18 to 24 months to 9 to 12 months. And for enterprise, again, we hit the 10-month mark at the first launch attempt. We were able to implement robust contingency and manifest backups to reduce primary mission risk. And that's kind of one of the things that really is a requirement to, we got to buy down the risk for the primary mission so they'll tolerate us, if you will. The secondary payload mate and launch vehicle to launch vehicle again was improved from L-3 months to L-1 month, and you can kind of see a timeline across the bottom. We had CubeSats delivered to our facilities about L-6 weeks, and about L-4 weeks were on the vehicle. So for enterprise, we also used what we call flexible dispensing systems, and what this is in this particular example is the Tyvak NLAS Mark II. And this is a dispenser that Tyvak has developed. We kind of built off the original NASA Ames Mark I NLAS and incorporated a number of lessons learned, such as access ports, or actually a one-piece chassis is what we developed for the Mark II to kind of evolve that design. The Mark II is designed to be inherently modular. So you can kind of see in the bottom left picture and the middle picture, they're both Tyvak NLAS Mark IIs. One has 2 doors and 2 payload bays. The middle picture has a single door. And we also can accommodate both of the 6U lengths, 340.5 and 366 millimeters in length. We all do this while maintaining identical interface to the launch vehicle. This turns out being to be very important, so we can manifest a dispenser to a vehicle and have that integration work complete and kind of ink dry. And then our program offices can kind of help us direct, and they can select the payloads they like to sponsor, or in a commercial case, we can fill that payload slot later in integration flow and really support those quicker turnarounds for our customers. The one thing that would change between these NLAS, double door example would of course have 2 mechanisms. They articulate independently and they're actuated independently. We'd have 2 independent circuits. And both these designs are fully qualified. They've been tested to ruggedized environments on the Atlas V, and they've been fully compatibility tested with launch vehicle avionics, meaning they take standard pyro pulses. They have telemetry circuits so we can monitor the doors. And so kind of building off the enterprise mission example, we were able to work with ULA and develop what we call CubeSat Express or CubeCore. And what this is, an integration effort focused on manifesting these flexible integration systems, flexible dispenser systems, so we can cut down the integration timelines, cut down the integration cost, and really try to enable most payloads we can. And so really with this configurable hardware, we're able to accommodate payloads 1U to 12U in size with really no change to the launch vehicle interface. The launch vehicle interface being this bottom plane, if we're trying to picture the bottom of the chart here. The Tyvak NLAS, again, is configurable for many different spacecraft sizes, and we kind of look at the bottom from left to right. That would be 4 NLASs configured for 3Us, so we can have 24U capability supporting 1U to 3U spacecraft. Left center would be for 6U, right center would be for 12U, and then far right would kind of be the mother of all configurations, accommodating 1U to 12U spacecraft, all with a single interface that is identical to the launch vehicle. And all hardware is as good as it processes, and if you can't integrate it, it's not really usable. So we have been working on integration processes along with this hardware just to try to streamline the approach and provide the most tailored and painless integration process for payloads and hardware alike. So we work with range safety, licensing, and ITAR if it's international, or if you have international payload coming to the US, and really focus on do no harm. Do no harm is a pretty big thing in our industry. We're trying to demonstrate to the launch vehicle we won't impact their performance. We won't impact the primary mission performance. And as well, for us secondaries, we don't want to be impacted either. We also don't want secondaries to interfere with each other, so we do a lot of work to make sure it's a safe ride for everybody. And then everybody loves fish bones. So last chart here, and then I'll open it up for a question. We are working expanded capabilities. We're constantly trying to see what we can do to help provide more rides to space. We do provide a number of dispensers. We offer what we call the 3U rail pod. We have all these dispensers actually on our desk up on our booth up there. The rail pod is a skeletonized, mass-optimized dispenser solution, kind of targeted for the NLV class of launch accommodations. It's about a third of the mass of a typical dispenser and accommodates rail-type payloads. We also have the Tyvak 6U, Tyvak 12U, and then what we call the Tyvak Inca. And the Inca is a truss structure which is able to be accommodated beneath the primary satellite, or can be used as an aggregation structure for small launch. And you can see the picture on the bottom right. The Inca is kind of buried in there in that rectangular structure. For launch services, we've been actively manifesting in both the U.S. and international launch ranges, and working with NASA, U.S. government, university, and commercial payloads alike. Working with ULA, we have been able to offer STEM-sponsored launches on Atlas V. That's been a huge effort, and we're really happy about that. We also support launch insurance and been really trying to optimize our payload processing with dedicated and purpose-built small satellite test facilities, including random vibration, TVAC, and really anything you need to get certified for launch. So with that, and that's the end of my charts here. Thank you, Q&A. I think I have time for one question. I think we're trying to get back on schedule, so any questions? Oh, there you go.
So in the previous presentation, they said you'll put cubes on every outfit.
Correct.
For this, you did it for a 10-month. Do you see how you can maybe break that integration down to a 6-month phase? You can get it closer to the long?
Absolutely. I think with this flexible manifest approach, we can manifest an interface that we know is there for the launch vehicle. The launch vehicle can design their couple loads analysis, their thermal analysis, and really we can manifest those payloads later in the flow. So if we can get this hardware on the vehicle, kind of like Dan was indicating earlier, build the secondaries into the mission up front, then we can manifest those payloads later in the flow. I truly do believe a 6-month integration window for satellites is possible. All right, that's the hook. Thank you.
Next up, we have Joe Maley and Chris Lothry from Moog.
Hello, everybody. Thanks again for inviting us to present here today. We've been presenting since 2010, and it's a great opportunity to be here in this spanking new facility. It seems like anyway, but it's great to be part of the CubeSat workshop. Let's see. We're going to start off with some background on Moog. We won't take long on that. We can handle that pretty quick. We are a flexible partner. We do a lot of things that the other companies don't do, but we try to get involved with all the things that are fun, attaching satellites to the rockets and helping the satellites get to where they want to go. We work in several areas of the CubeSat market, and we'll talk about our propulsive adapters, the ESPA ring and what's been going on in the ESPA world in the past year, and finally what's been going on with our launch mitigation, including soft ride, but more specifically for CubeSats, the shockwave isolator system. Why don't you take,
the spiel. So if you're not familiar with us, we're Moog. It's not an acronym, it's a guy's name. We were founded in 1951. Our company's headquartered in East Aurora, New York. Yeah, 1950, what's it, 18? Since the Industrial Revolution. But we have facilities all over the US, actually all over the world. We're in about 25 countries, 11,000 people, and we do about $2.5 billion a year in business. But actually, our space business isn't that big. We're about 200 or so million in space, half on the launch side, half on the spacecraft side. Oh, yeah, that's right, I got a point. So you can kind of see our footprint here in the US and then internationally, and then how we kind of break down. So we've got, on our defense side, we do tank stuff, missile stuff, and then in space, primarily spacecraft elements like avionics, propulsion, structures, things like that. So what we actually, a nice little graphic showing that. So these are kind of the things that we focus in on as a company. And one of the things that we found to bring those kind of pieces together is what we call an orbital maneuvering vehicle, which is essentially a propulsive adapter. So if it flies, I get up here and talk about it. If it's static, he gets up here and talks about it. So part of our group, we sort of have kind of an advanced programs type group to go look at some of these things. And we've been doing this for about 3 years now. And we started off with a lot of kind of, call it oddball things out there. So mega constellations, some of the mission planning for that. We had a commercial weather satellite constellation that we were actually part of, some of the asteroid redirect mission stuff. And what we found over time was this propulsive adapter, this flying ESPA. There seemed to be a lot of actual really interesting uses for it, and there wasn't a lot of people in the world doing it versus satellites. There's a lot of people doing satellites. So we started looking at and kind of focusing in on that. So that's sort of been our focus for the last year and a half, 2 years. So we've kind of honed that in onto what we're calling Comet. It's our commercial ESPA tug. Pretty simple there. And the whole idea here is if you're a ride share, you go up, you get dropped off into whatever orbit. There was the planet pictures earlier where the doves are flying out, you know, like a machine gun or something like that. And that's fine for some spacecraft, but not all spacecraft want to go to the same place at the same time. Sometimes they want to go that, you know, couple extra kilometers up, or more likely they want to actually phase out their constellation, not necessarily using differential drag, but actually using a propulsive capability, and then you pull all that into your spacecraft. Your spacecraft are bigger, heavier, more complicated. What we do is pull that into one system, and then you can actually kind of bring that around. Essentially, we become your propulsion system. And then you can actually be part of the architecture as well. So part of that could be like a comm relay or on orbit, where you actually have an on-orbit spare, and it's 6 months later or whatever you deploy it. So here's some specs for Comet. It's based around the ESPA Grandes, and so we can handle 5 300-kilogram ports. So to put that in U terms, I think it's something on the order of 420 U if you loaded that thing up with quad packs. So pretty much all the launches in a year on a single ESPA. We're targeting what we're calling a Class CD mission, so it's D at a baseline, and then there's some C elements for some of the higher end stuff. And we're looking at pricing this out in the sub $10 million range, so it's not you know, the 300K that you might be expecting for a CubeSat launch, but relative to the capabilities that you'd have to do into several spacecraft or multiple launches or things like that, we see it as actually a pretty reasonable price. And we're targeting to be ready to start buying hardware this summer with flight readiness in early 2019. So to give you an idea what it looks like, we have a fixed solar array on top, but it's a simple system. It's basically a flying gas tank. So it's a hydrazine monopropellant system. It all comes internal. It's our thrusters, our tanks, our valves. We put it together, we test it. Our avionics, our ESPA structure we design, and then we buy star trackers, things like that. We also have taken that idea and said, hey, there's a lot of big spacecraft that find use in this, but the 420U on it but probably doesn't make a lot of sense. So we look, could we take that architecture and scale it down, especially for the venture class launch vehicles? So we first started out with this top one, this 38.8. So that's Minotaur, that kind of idea, and started looking at what you could do. So that picture on the top there is an example of how in one launch you could put, you know, a constellation across 3 different planes. Versus 3 individual launches. And we got a lot of interest in that, and then we kind of started looking at Rocket Lab. There seemed to be, like with the U's on spacecraft, there were sort of these launch numbers, like 150 kilograms. That's a common launch up mass. 300 kilograms, well, that's conveniently two 150s. So we looked at what could we do to make the system a little smaller, a little lighter. So down on the bottom, that's kind of it's a 24-inch interface. The overall diameter is about 40 inches, so it fits in an Electron, it fits in a Launcher 1, and then you can stack it to actually do 2 in a Launcher 1. And then one of the things that we came up with that was interesting is 24-inch diameter, 150 kilograms. Hey, that could fit on an ESPA Grande port. So you could actually start doing multiple ones of these. The ESPA could actually carry 2 of these stacks. So in theory, you could have 10 of these, each of them with 6 6Us. All of them could be propulsive. So all kinds of interesting things you could do with that. So that's kind of what we've been working for, small sats down to CubeSats. And then Joe's going to talk about a lot of what we're doing in adapters and some other technologies.
So many of you have heard over the years as we've expanded our ESPA family and other adapters that we build at Moog and Moog CSA. The ESPA ring has become a standard in the community, and there's been some interesting activities going on in the recent year or two. One thing is we are promoting our modular ESPA option. The family is not restricted to the picture I showed on the previous page, but we can configure an ESPA ring for a mission based on specific objectives or configurations that want to fly with that mission. We've designed rings up to 120 inches in diameter. That's twice the diameter of the ESPA ring. And we've designed them, as Chris mentioned, down to the dimension of our small launch OMV, but we don't want to build an ESPA for the small launch OMV because it's a little too heavy. So we build a composite structure for that. But ESPA is a modular system, and we can do a lot of things to fit the needs. Now, in the past year, we have actually retested the ESPA ring because we were carrying a lot of extra margin on the ring, and it turns out that we have now qualified it to almost 75% more than we had been saying for the last 15 years. So the ESPA class is 400 pounds at 20 inches from the ESPA port. That's a significant amount of payload capacity, and you can put a lot of CubeSats into 400 pounds. But we did the testing because we had actually changed the design since the original ESPA mission to a more robust interface at the port. Instead of a flange, we had a boss there. That change was made for integration, to make integration more easy to do, but it actually made a stronger and stiffer port. And then we also introduced a new interface where we replaced the 1/4-inch fasteners with 5/16 fasteners, because those fasteners are a weak link when you're cantilevering a payload out in a launch vehicle that moves up, and the cantilevered payload is mounted sideways. So with this new capability, I'll get to the details of that on the next slide, but this will enable even more CubeSats or more small sats to be carried on an ESPA ring. So what's new now, we've got what we call ESPA heavy interface with the 5/16 fasteners, and we can carry 710 pounds now instead of the 400 pounds we've been talking about. CG is still at 20 inches, and the standard or the light interface would be the standard ESPA. That's now 485 pounds or 320 kilograms as opposed, or 218 kilograms as opposed to the original 180 kilograms, 400 pounds for the ESPA. And furthermore, this year we're just about to have a kickoff meeting for a test of ESPA Grande. So this is really going to expand the capability for the ESPA ring going forward. Now, just a few final words before I get off the stage about our shockwave isolation system. This complements our soft ride isolation systems, which have flown now in 38 launches since 1998 to isolate the whole satellite from the rocket. We've flown on 12 different launch vehicles, shown here from the Minotaur, the little Minotaur, up to the big Delta IV Heavy. Last year here at the CubeSat workshop, we introduced our shockwave isolation system. The idea here is to reduce the history of cyclical vibrations that pile up on your CubeSat through all the different cycles it goes through during assembly, during testing, during shipping, And finally, during launch. And sometimes the shock environments during launch can be the thing that puts the CubeSat kind of out of commission because of some board getting shaken too hard, or solder joints, or various things that can go wrong due to shock. It's usually not so much the vibration issues as the shock for CubeSats. And this was documented by a good paper by Walter Holmans at the CubeSat workshop in Logan, Utah a couple years ago. So we worked with Walter, and we now market these through Walter as well as through our own website. But this is the product line we introduced last year. It's low cost, short lead times, modular, and easy to integrate. So it fits well with CubeSat dispensers, and it can also be. We've also found some applications for on-orbit isolation for a small CubeSat payload, which was actually a small laser comm demonstration. We did shockwave testing at Planetary Systems during their qual program last year, and here's a picture of a 6U dispenser with 8 shockwave isolators underneath it. And some of the results from that are quite impressive. We reduced GRMS. You can see a slight increase at the low frequency due to the isolation frequency modes, but then all the high frequency stuff that tends to break stuff on a CubeSat because of shock gets reduced substantially, and the RMS Gs can be reduced in these two cases from 22 Gs RMS down to 4.8, or in this second case from 63 Gs down to 4.7 Gs RMS. So it's a substantial increase. We've got ICDs available on request, and here's some sample dimensions and some of the specs that we provide for the shockwave. So I just want to try to get out of here in time. So what we presented here is our family of propulsive adapters. Actually, the Comet and the small launch OMV are only the start of our family, but those are the two we're working on the most right now. The multi-payload carriers of ESPA in particular are seeing a lot of changes these days, and ESPA Grande test coming this year will kind of round that out, and we'll finish up. We're still trying to protect satellites as they get launched and go through the various environments that they have to, and sometimes on orbit that works too. So Soft Ride and Shockwave are our two product lines in that area. So with that, I think we're ready to get off the stage. Oh, I do have a Shockwave isolator in my pocket. You can see they're little small things, and we just put several of these under. We got a kind of a lookup table on our website for the various sizes, depending on the mass and geometry of your payload. You can look it up and then just call us up and order a few of these and put them under your satellite for the testing and or the launch.
We're trying to do these COTS, so they're $1,000 each. You know, there's a spec sheet. You say, I want 10 of them, 20 of them, 100 of them. So trying to...
They're cheaper if you get 10.
Yeah, they actually go down in price, but trying to, essentially match the market where people are used to buy it now type functions, and, not the RFP, how much does this cost 10 weeks later type stuff, so. We're hoping to be able to do that with some of our other products as well.
And this is actual test data, the shock response spectra, but we like to jazz it up with the guy surfing down the lower response level. So thank you very much for your attention. And do we have any questions? It looks like we might have a little time.
Don't see anyone out here. Oh, how much time? One unit of question.
Yeah. Well, that was over that whole frequency range. I tried to go back to the slide, but it's not up there anymore. But that GRMS is across the whole range up to, I think it was up to 2,000 hertz. Or you amplify at that lower frequency, which is typically down around 50 hertz or so. The way we designed it is so that lower frequency is above the coupled loads range. So typically, we size them to come in above 50 hertz. So it does not affect coupled loads, and these could be inserted after the coupled loads has been done and won't make any changes in the coupled loads regime. All right. Thank you.
Next up, we have David Pignatelli from here at Cal Poly.
Hi, thank you. My name is David Pignatelli. I'm a staff member here at Cal Poly with the CubeSat program, and I'm here to talk about some added capabilities that we've implemented on the Poly Pico satellite orbital deployer. So just to start with, our overall design motivation for the P-Pod Mark IV was that we were seeing CubeSats that had some sophisticated mission requirements that weren't exactly being met by basic CubeSat dispenser functions. Some CubeSats will have high-power transmitters or want to be powered on during launch. These kinds of things can make the launch vehicles nervous because of the potential for interference. We also have some CubeSats with sensitive instruments that want to be away from oxygen and want to be in a very controlled environment, so something like a nitrogen purge system is desired. And then in other cases, some CubeSat missions might be able to be enhanced if they can be powered on and receive battery charging or transfer data through an electrical interface while they're integrated into the P-Pod. So going over the overall design updates, we implemented EMI shielding in some locations, such as the door and the access ports. We added a purge or power on accommodation to the backplate, which is really, it's a modification of the P-Pod backplate so that if you want to add some sort of extra capability onto the back end, it's an easy mod to just add it on. And so it's not just limited to purge or power on. It's pretty much anything you can think of that you want to stick on the back there. And we also took a look at the door design to improve its stiffness and reduce deflection, so your EMI shielding isn't compromised despite any extraordinary load on the P-Pod door. And while we were making these design changes, we just took a look at some areas where we could remove a little bit of mass, just so, with all these added capabilities, we're not letting our overall mass increase. So looking at the EMI shielding design specifically, we identified some sources of RF leakage, which is essentially anywhere where there's a gap, such as the door, or sufficiently small fastener spacing isn't feasible, like the access ports. So we implemented conductive gaskets in those areas. And of course, when you put the gaskets on, now all your ventable area is gone. So we designed just a vent hole array that would meet launch vehicle ascent venting requirements, but still maintain our EMI shielding. So to test the system, our first setup consisted of an antenna inside the P-Pod mounted through a coupler in the P-Pod wall with a coaxial cable. And our results were not really realistic. They were much lower than we expected for how sealed up the P-Pod was. And we attributed this to the coaxial cable coupling with the transmit antenna on the outside of the P-Pod. So we took a look at our test setup, and in order to eliminate that, we set up a self-sustained, self-powered transmitter on the inside of the P-Pod and use that to transmit and essentially be like a CubeSat inside the P-Pod and then measure the signal from the outside. So this eliminates our coupling concerns, and it worked. We got some really good results ranging from 30 dB of shielding effectiveness at 10 gigahertz all the way up to 74 at 437 megahertz. So really a significant amount of shielding. And then shown here are just an example plot of the 437 megahertz baseline compared to the measurement taken from inside the P-Pod. So an example of a CubeSat mission that is already benefiting from this design is Cal Poly's own LEO spacecraft, which is designed to measure the launch environment while inside the P-Pod during launch, and then transmit that data over Wi-Fi to another CubeSat. So initially, in order to get the launch vehicle comfortable with this, we had to have a EMI shielded carrier. So that's why the decision was made to fly the P-Pod Mark IV. So this was, 2 wins for Cal Poly because LEO gets to fly and we get our first manifest for the new P-Pod. And that's flying on SDP2, actually. So looking at The P-Pod Mark IV backplate, like I said, we made a modification so that it was extremely easy to modify any P-Pod backplate to accept additional capability. Right off the bat, there's nitrogen purge or the power on electrical interface. And as you can see here, that's the nitrogen purge inlet on the back of a P-Pod that flew on ORS-3, because there was a CubeSat there that had an instrument that could not be exposed to oxygen. And so that flew successfully. And of course, that design is, we designed the Mark IV to be completely compatible with that design. And then looking at the power on CubeSat electrical interface, essentially this is a system that can give you up 15 or more pins to do essentially whatever you want. Power on, signal the satellite to turn on, transfer data, battery charging, whatever. There's a lot of pins. And then it uses a zero force connector in order to ensure there's no impediment to deployment. So in summary, we designed the P-Pod Mark IV with the EMI improvements successfully implemented, and it's been qualified for flight and manifested already on STP-2. Our EMI shielding efforts were extremely successful. 30 dB is a lot of attenuation at 10 gigahertz, and then there's even higher attenuation at the lower frequencies. And then the backplate design is now adapted, can be easily adapted to any capability such as nitrogen purge or power on. The options don't end there. I mean, if you want to put a camera there to watch the satellite on the inside of the P-Pod during launch and then see the deployment from the inside, or if you want to, refill propulsion tanks while you're integrated into the P-Pod, these are all options that can be explored. And finally, we increased the door stiffness and just improved the general design, and did all that while actually getting a minor reduction in P-Pod mass. So we were pretty happy. So, and I think that's all I have. A little quick, but any questions? Yeah. So the question is if the EMI shielding limits your ability to transmit from inside the P-Pod. So the shielding is actually to prevent any transmissions from leaving the P-Pod. So it's purely external. So when I was talking about LEO, it's transmitting with another CubeSat inside that P-Pod. Right, not to the ground. Right, yeah. Yes. Yeah, so we can go back. The question was why 437? So we tried 437 megahertz, 4.3 gigahertz, 5.2, 8.6, and 10 gigahertz. So did we see the same reductions in dB? So that in general, the higher frequencies, there were less reductions. 10 gigahertz, 30, 38, 32 dB, depending on what side you're looking at. You look at 5.2 gigahertz and you're hovering around 40, and then 437 is 65, 74 dB. Right. So is your question what the zero force connector is? So the idea is with the zero force connector is it separates without any, there's no force to separate, it comes undone by itself. So when you have the P-Pod deploying, the pusher plate just pushes the CubeSat out and it just separates. Yes? So you mean, can we get data from the CubeSat to the launch vehicle and then down to Earth? I think that's possible. I mean, that's something we'd have to, work with the launch provider to see what's feasible. Maybe for an Atlas it's not applicable, but there might be other launch configurations where you know, they're designed to carry a bunch of CubeSats, and maybe there's a sequencer somewhere that can you know, receive that information and process it and potentially transmit. Potentially, yes. This is just opening that door. So on the Peapod side, we have, maybe you're not going to transmit data, but you can charge batteries, or if there's some telemetry you want from the CubeSat that the launch vehicle can keep track of, anything like that. Yeah, potentially. The mass is just slightly less than a Peapod, than the standard Peapod, and it can carry, depending on the launch vehicle, anywhere from 3 to 6 kilograms. 6 is the typical max. All right. Yes. So far, not yet, but I'm sure it's only a matter of time. All right. Oh, sorry. Yeah. Did we test it compared to a previous generation with no gaskets? So yes, but it was you know, years before this test, so we had a slightly different test setup. So the shielding definitely wasn't there. I don't have the numbers on hand, but. Okay. If I'm not missing anyone, I think that's it. Thank you.
At this point in time, we will have a break. Every sessions will begin again at 3:30. Thank you very much.
I'd like to thank our sponsors for lunch. And next up, we've got Bob Twigs.
I hope you don't expect me to sing or dance. If I could, you'd probably all leave. You know, I have a presentation today I'm really excited to talk to you about. Sometimes things happen in this business that really surprises you. One of the things that doesn't surprise you is things don't happen very fast, right? But I need to tell you a little story about something that happened here that is, to me, is just amazing. This is really one of the, to me, the most exciting things that's happened in my career, and especially the opportunity to work with these satellites and the students. Began last August up at the SmallSat conference in Utah, and a lot of you know I've been pushing this little thing called a pocket cube for a long time, ever since the people got interested in the CubeSats that they thought was such a dumb idea initially, that if we could get something to go smaller, maybe we could get it launched cheaper for the students, because that was our whole thing at the beginning, was education for students. And so I've had this little 5-centimeter pocket cube that I've carried around for quite a few years, and I was leaving one of the sessions at Utah, and Warren Frick from Orbital ATK happened to be walking down the hall. I've known Warren for quite a few years, and a year ago at the conference, one of the NASA guys mentioned that, hey, you could get a real short mission if you went on the second stage of one of the launchers. And when he said that, you know, I didn't do it, but I was about, yeah, I'll take that. I'll take anything that gets above a house for a half an hour. So anyway, I seen Warren, and I walked up to Warren, and I think all of you, probably a lot of you know Warren Frick's big, tall guy, you know. And I walked up to him, and I showed him the pocket cube, and I says, Warren, can I get this on your second stage? And I backed up, you know, because he's got a pretty long swing, and I thought maybe I would be at the end of that. But he said, let me think about this. Maybe we can do something. And what it turned out is maybe a month or a few months before that, a guy named Dale Nash at the Virginia Commercial Space Flight Authority, it's a state of Virginia commercial organization that helps fund the Wallops Island launch, where they're launching the Antares and the Cygnus, had gone to Orbital and say, since we're supporting you guys, we would like to be able to launch some CubeSats. And will you give us 4 essentially P-pods to launch CubeSats on every one of your Antares launch? And so they had an agreement that he agreed to that. And then when Warren went back and talked to Dale about this little pocket cube, they said, maybe that's the idea. And here's the very interesting thing. 1 month from the time we talked to Warren, we were back at Dulles, Virginia in Orbital ATK, and they showed some slides. 1 month now, and pocket cubes were manifested on the Antares. Now, I don't know that anybody gets manifested that fast. So anyway, we've worked on this program quite a bit. So there's a number of people that are involved here. I don't show all of them on the first slide, but there is Hank Voss from Near Space Launch that's doing a lot of work with us, the Virginia Space Authority, Morehead State University, and we have come up with something that I think is going to be exciting. If I can get, now the F stands for forward, doesn't it? Well, can you do the first slide for me? Oh, there we go. So I want to tell you about a new spacecraft and a new launch program. Next slide. Okay, next. Okay, next. Okay, what I want to do is kind of show you a chart here on cost and orbit life. So you see I've got a sun synchronous ELV launch there showing, hey, probably 150K or more and maybe 3 years launch. Next one, please. And just a straight LEV or 125K and maybe 2 years. Next one. You're on the space station and that's 80K plus, 6 months to a year. Next one. Right down in the corner is where this second stage launch is at. Good. So let's go on to the next slide. And let's look at the cost of the spacecraft. So we start out, again, with a small satellite, up to $1 million, 5 years. Next one. 100K to start with for a CubeSat, and then a pocket cube. Other people that have built them, and we've worked on them, is around 35K, and depending on where you get it launched, 6 months to a year, maybe longer. And then down there, I've got a little thing called a ThinSat, and I'll tell you what a ThinSat is all about. Now, what the emphasis here is I'm way down in that corner. I have a very short life, but I have a really low cost, and that's what we're trying to get at. Next slide, please. Okay, what do we need a short life for? I want to get to the kids, K through 12. Would it be neat to have this audience filled with kids K through 12 that are working on satellites? I think that would just really be super. And then we're really building the audience that we need for the future here. Now, why? I've talked about a 5-day life. What is the attention span of students? 5 days. What's the attention span of university students after you launch their satellite? 5 days. The students that I've had previously, that after they get up 2 or 3 times late in the night to go to the ground station, 5 days is too long, so. Okay, next please. Low cost. What is the cost that I want to get to here? I told a gentleman earlier today I wanted to get less than the cost of a Tesla 3 that they advertise, not what it's probably going to cost you. But what's the cost of a Tesla 3? What are they saying? $35,000. Can you have a complete space mission with all of the hardware provided, all of the integration, everything else? Could you have that for a matter of less than $35,000? I hope so, and that's what we're aiming for here on this. Next one, please. Rapid mission turnaround. If we can get on this Antares, and that Antares flies every 6 months, and that's really neat. Now, how do they get launched? They don't stay on the station because they get launched before this thing gets to the station. So the time it's going to get launched is right immediately after the launch off the pad. Next one, please. Next one. Oh, there we are. Getting through the mission cycle. One of the things that in the very beginning when we come up with the CubeSats, that was one of my goals. I want to get the student to go through the mission cycle. Okay. Now, there are not as many students here as we see in Utah. But let me see all of the hands of the students that are working on a satellite program. Okay, how many of you have been through the mission cycle? Did you see? Look around. What happened? It just is taking too long. We want something that's a lot better than that. Next one, please. Scheduling. We know when this thing is going to fly. What we've worked out right now with Orbital ATK is we deliver in the launcher, the P-pod, the CSD that we get from Planetary Systems, we deliver it 2 weeks before they fly. So we don't have to get it there 6 months. Next one, please. Okay, so it's a new space launch program. Next one. There you go. There's that Antares taking off from Wallops Island. It is the coolest thing. These guys are so nice. I've been there twice, and they take us out, and we go through the vertical integration building, and we put on this little white coat, and we walk right out under the rocket. Oh my gosh, you know, how many people give you a chance to do that? And the only thing they won't let us do is take our camera and take pictures. That's the only limitation. And you know, I slobber all over myself when I'm out there walking around that thing. That is so absolutely cool to see that. And can you imagine what that's going to do to kids that have a real interest in it? Next one, please. Okay, next one. Okay, where we are is we drop the first stage, go up with, this is a solid motor on the second stage. Right after that solid motor burns out, they release the Cygnus. They do what they call a crab walk on it. They kind of turn it at an angle to get it away from the Cygnus. And then they release all of these things that we're going to call thin sats. Next one, please. Okay, there's what it looks like. You know, when we went to orbital and we said, how much room is there on that second stage to put things? They showed us this diagram. Every place that's blue, you can put satellites on it, you know? And I asked the guy, I said, ooh, you know, there's this solid motor, this carbon wound motor, and you know what's inside of it. It's a big firecracker, right? And I said, can we attach things on the outside of this? And the guy said, you know, I was thinking about drilling holes, but so I asked him, what can we do to put things on the outside? Oh, we just epoxy things on there. That's no problem. Where would you like to epoxy something? I said, all over, you know. I'd like to just cover that thing with little satellites. Next one, please. Well, what we've actually worked out with them is on the interface between the Cygnus and that second stage, there's a flange. And right now we're planning on putting 4 of these canisterized satellite deployers on there. Next page. I'm sorry, next slide. And here you can see the orbital ATK solid motor. And right on that flange, on the left side, the silver thing there is the Cygnus capsule. The black thing is the second stage, and on the right is the first stage there. Next one, please. So this is what we've got. We're going to make these things called thin sats. Now, when we first proposed this, I wanted to have these little things called pocket cubes. And this guy named Hank Voss come to me and said, hey, Bob, I got a good idea. And I said, well, what is that? He said, I want to make these things called thin sats. And you know, it's like taking a 3U and slicing it up like a loaf of bread. And I thought about that, and I thought, I don't know about that. And then you start thinking about that. We're up at a low altitude, so there's a lot of atmospheric drag, right? So if you kick one of these things out, what is it going to orient to? It's going to orient to the least drag on it, which is going to be the leading edge. What about the PC boards? Is it going to be easier to make PC boards for this thing or a little 5-centimeter cube? So the more you look at that, the more sense this makes. So we can put 21 of those thin sats in one of those CSDs. Next one, please. Okay, and we got 4 of them, so we could launch a total of 84 thin sats with those 4 of those. So 84 thin sats every 6 months. And this is what the thin sat looks like. Now, Hank just give me this. I guess this is the ladies' version, right? This is a pink one here. And I don't know, has anybody ever launched a pink satellite before? I think all of the girls would be happy to launch a pink satellite. Now, the way this thing is made out is it's made out so on the right-hand side is all of the bus. On the left-hand side is the payload. So you get a payload board that's about this size. Not a lot of room, but you can put quite a few sensors on that. The whole idea with this particular satellite is it's a satellite that the students get that is absolutely completed. It's ready to fly. They can either opt to put a board with additional sensors in it, or they can say, I'm going to fly it with the sensors that are on it, which are quite a few. The students do not get in the classroom the flight satellite because we want to make sure that these things work when we launch them. So we will give them an engineering model. They'll build and test their board in. They'll send us the board. We put the board in the flight model, and then we do all of the integration and testing on it. Now, for 5 days, how are you going to get the data back? How many of you in here have got your ground stations to work well in 5 days? All of us know that that's not easy. But you know what Hank has come up with, and he's kind of the pioneer in this, is we're going to use the Global Star radio. Oh my gosh, you know, think about that. You don't need a ground station. This thing starts transmitting the minute it comes out, and it's going to transmit all the way around the world. And how do the students get their data? They get the data back on the internet. How much better is there than that? They don't have to run out in the weather and make sure that that Yagi is pointing in the right direction. But we want these students to get data, and they'll get it back real time. They'll even have a map that shows exactly where that satellite is as it goes around the world and transmits. So can you imagine what it's going to be in an auditorium in a school when these students launch that satellite? I think it's going to be pretty cool. Next one, please. And what we want to do, here's another idea that Hank came up with. How about dividing these up into essentially CubeSat sizes and tether them together with a nichrome wire? Now, why tether them together? Well, there's a lot of good reasons for doing that. First of all, it's cool, okay? And cool is what we want in satellites, right? And what do you think about here if each one of those ThinSats will belong to a class in a school? They can't put all of the sensors on their particular ThinSat. There's just not enough room and power. But what if you distribute the sensors out and they share all of the data from all of the 7 in this tethered thing? There is a radio in each of the ThinSats. On each of the mother sat, the one at the beginning, there is a camera that will actually take a picture of your satellite in space. And also on one of the 3, there's a GPS, so you'll know where it's at. So this is a really different kind of thing to get students to work together, to have, you know, a common goal and so on. Next one, please. Next one. What? We're almost out of time. All right. Go. Next one. Well, there are a lot of advantages to this. I think I've went through all of them. But what I'll do, can I get one question? One question. Anybody? What I'm going to do is I have a sheet here that explains the program for the schools. And I will put those sheets up on the Moorhead table, and if anybody wants them, you can get them. But I think it's going to be a cool program, and I hopefully 2 years from now we have a different population in this audience. Wouldn't it be neat to have K through 12 in here? I think it would. We need to start younger with these students. Thank you.
Thank you, Bob. Next up, we're going to have Mario Saldana from Rocor.
Hello. Today I'm going to be talking about the development of a lightweight thermal capacitor panel for thermal control of CubeSat applications. This product was developed at Rocor, a space hardware company located in Longmont, Colorado. So Rocor's space capabilities can be divided up into 2 systems. Can be divided into deployable systems and thermal management. On our deployable system side, Rocor is focused on developing deployable systems with extremely efficient packaging factors. These deployable systems typically incorporate high-strength composites, and we've incorporated these technologies into solar array deployment systems, deployment antennas, and some custom products like this deployable, retractable boom. It's been used for proximity operations by the DARPA Phoenix program. On the thermal side, we're focused on leveraging 2-phase technologies to develop lightweight thermal management devices. So Rollcore has been around since about 2011. It spent its first 5 years developing core deployable technologies and thermal systems under SBIR funding. Last year, Rollcore made the jump from being a pure technology development house to actually delivering space hardware. And at the beginning of this year, we delivered our first system, and it is going to be launched on a PSLV Indian rocket this summer. Additionally, we have a backlog of 24 flight systems that'll be launching by the summer of next year. So a couple of sample projects that we have on the thermal side, collaborating with Morehead State on a 6U lunar satellite for science missions. You know, as these satellites get smaller, the thermal challenge becomes more acute as the performance and the power requirements go up on these smaller systems. Rollcore's experience and technology is also valued by larger spacecraft companies. For example, we're currently collaborating with Moog on this maneuverable orbital vehicle. And the goal is to utilize some of our two-phase technologies, our thermal capacitors and our heat straps, to be able to handle some of those thermal challenges on that spacecraft. So, you know, why would you even want to use two-phase technology? Well, the simple answer is thermal solutions that worked for these larger spacecraft simply don't scale well to these smaller systems. So, you know, two-phase technology really provides reduction in volume, reduction in mass, without sacrificing performance. So on this slide here, I kind of give a representation or a demonstration of our technology. This is a couple of our heat spreaders. Take this off that way I could turn around. So here, the top one is just a plain piece of copper. It's being subjected to 120 watts by 3 heaters on this end at a flux of 40 watts per centimeter squared. And then on this end, it's being cooled by chilled water circulating in a channel on this end. And you can see that our heat pipe here, or our flat cool heat spreader, has a much more uniform temperature, and it's also significantly cooler than its copper equivalent. And we can make these pieces in larger sizes. We use commercial off-the-shelf materials, and we can get pretty good performance out of these systems. So the main subject and focus of this talk is this thermal capacitor that could be used aboard CubeSats. So what benefit, or why would you even need a thermal capacitor on a CubeSat? Well, it can help dampen some of the fluctuations as you're going from eclipse and being exposed to solar radiation. These large temperature fluctuations could throw the components out of their operational range. Additionally, some of these large thermal stresses could lead to failure of some of the components. So before we built this piece, we wanted to understand how it was going to operate under some condition. So we used this software called Thermal Desktop, and we ran a simulation where we're providing 15 watts of heat to a PCM panel on a 1U CubeSat. The rest is just photovoltaic panels. And you can see that here where we have our heat load, it's this red line here, this section here, it's not only the heat load from our heater, which is a 15-watt load, it's also receiving radiation from the sun and albedo from Earth. So that causes the phase change material in this section to melt. And so for the case where we have the PCM panel, we're able to maintain a relatively constant temperature, which is good, is what we want to get out of it. You can see this, in contrast, if this was just an aluminum panel, you would have these large fluctuations, which, again, are undesirable. The material that we chose to build this with was aluminum due to its lightweightness. And we actually 3D printed these metal structures using this technique called direct laser metal sintering. We designed this piece to be able to be load-bearing and have enhanced thermal conductivity. That's the purpose of these pins here. Additionally, we added ports so that we could charge the panel with our phase change material. So we worked with these DMLS manufacturers to find out how tight a resolution they could get, work with wall thicknesses and the internal support structures. And when we got these parts back, I mean, they looked really nice. They were within the flatness specifications. They could even be post-processed to have some better optical characteristics. In the end, the design that we chose to go with was a balance between the mass of the phase change material and the mass of the internal supports and outer casing. So prior to charging the panel with the phase change material, we tested several phase change materials so that we could experimentally quantify their thermal conductivity and their latent heat. And it was good that we did that because we found that the latent heat for these materials varied by as much as 5% from literature values, and the thermal conductivity varied by as much as 20%. So it was good that we actually, were able to quantify this. We also found that the paraffin that we used to test didn't have a single melt temperature. There were several melt temperatures, so we didn't choose that as our phase change material. And then we also didn't choose icosane, which was one of the materials that we tested, and we didn't pick that one because it turned out to be toxic. So in the end, we went with octadecane. And so we charged that PCM panel with that phase change material, and then we tested it inside this vacuum chamber where we monitored the heat going in and the temperature of the panel. And so we ran at 5.5 watts of power and 3.8 watts of power. And we ran these over 25 freeze-thaw cycles. And over those tests, we didn't observe any appreciable degradation. The melt temperature was the same. We weighed it. We had no loss of the mass of the PCM panel. So, I mean, this was just sort of a preliminary proof of concept. We were able to show that this design worked. In the future, the design will be tailored to a specific customer or partner where we would get what their requirements are and tailor that panel for them. Additionally, we would like to use some of our heat straps to also do some combined testing to show how these in tandem are able to give you much better performance. So at this point, I would just like to thank a couple of people that worked on this project. Stephanie Morrow, Jeff Farmer, a couple people from Moorhead State University, Ben Ralphus, Kevin Brown, and Dr. Boris. So if you guys have any questions, I'd be glad to answer them. Yes? This guy, I believe, let's see here. Oh, I took it off. I think it was 60 grams. Don't know off the top of my head, but I had a slide that had it on there. And really that mass was, like I said, it was a balance between the phase change material and the casing material. I mean, in the future, we really are going to even have to, I guess, optimize that even more, because one of the issues that we found was that there's low thermal conductivity just throughout the system. So really, we want to have a hybrid system where we kind of have, perhaps maybe a foam or something to help enhance the thermal conductivity and get better performance out of the system. No, really, you want, the experimental testing I showed wasn't what you want. You want to stay within tighter temperature ranges. So you would kind of tune not only your amount of your PCM panel, but you would tune the fluid itself to whatever your specification was. So, that would be good in the future once we, are working with partners or a customer, to go after those specifications. But right now, it was just testing proof of concept, basically. Right, yeah. There was quite a bit of deviation from the thermal desktop model to this PCM panel. And one of the reasons was, we kind of had an effective thermal conductivity, whereas this is, there's portions where you have half a watt per meter Kelvin, and another portion where you have the aluminum and you have this thermal conductivity that's orders and orders of magnitude larger. So it wasn't really representative. In reality, we need to develop a more robust thermal desktop model that's taking into account all of those factors. Yes? Yes, yes. So we've tested against pressure as well as we can under that system. The goal was to fill it at the temperature which we think it would operate the hottest, and then seal it under those conditions, and then when it solidifies, it'll be at under vacuum, and then when it reaches that hottest temperature, it'll just be at whatever the pressure that we sealed it at is. But yeah, I mean, that's failure. If it goes beyond that point, then we can't, I guess, design beyond that, because yeah, it'll expand, it'll blow up, it'll just lose its performance. Yeah, I don't think it would explode. I think what would happen is you'd probably get a crack somewhere and you'd leak your PCM out. Yeah. Any other questions? All right. Well, thank you guys for listening.
Thank you, Mario. And now please welcome Andrew Santangelo from SciZone.
All right. Hello, everyone. Notice I don't need to walk around with a mic. Thank you guys back there. By the way, I also want to, is Jordy here? I don't know if he's here. I want to thank him. Every time I come to this workshop, he always clothes me. I got a new outfit to wear here, so I really dig these new duds. And I think this is our clicker. In this very short period of time, I'm going to share with all of you our LinkStar architecture in this very brief 15 minutes, and this is something we're very excited about. I call it an architecture, even though it's a radio, but it's also a flight computer. It's also flight software. It's really a whole package that gets you rolling really fast here. So what I'm going to talk about is, let's see if I got the right one. Is this working? Okay, let's try forward. All right, I'm going to go over the company very briefly. And then I'm going to talk about the architecture, and then the CubeSat vehicle management system, which is really the brains of this software. It makes it really easy for you to integrate and get your system going. And it does work with other flight architectures. It's a very friendly open source environment. Then we're going to talk a little bit about ground communications and future missions. So a little bit about SciZone, if you haven't heard it, got to get the click here. All right, we're located in Holland, Michigan, and Rio Rancho, New Mexico. I like to show this picture here. A lot of water and beaches in Michigan, a lot of beaches in New Mexico, not much water over there. But we do a lot of work with GE Aviation, DARPA, Air Force, NASA, Auburn University is part of our team. We've got a whole list here we'll talk about. Let me go right here and talk about LinkStar, which is, I like to think of as a paradigm shift. It's a very exciting platform that gets you guys rolling fast. And the research we've been doing with the LinkStar and especially with our work with DARPA the last couple of years here. The architecture itself starts with the computer. And what we've done is we've taken a BeagleBone Black and modified that as our flight computer with our flight software. And it's actually an industrial BeagleBone Black. It's flown in space several times. It's flight proven. Even Air Force has tested it internally. From that point, we have our CubeSat vehicle management system, our software that provides control not only for the radios, but a command architecture you can work with. You can tie it into the Goddard flight management system, and you can control sensors and other instruments, and it's a really plug-and-play, easy-to-use environment. And we'll talk more about that. The whole radio part of our system starts with the LinkStar STX3. And we'll talk about this, but it's basically a simplex radio that beacons data nearly all over the world, and you drop it right into that BeagleBone, and all he knows, I'm a radio, and it starts to broadcast. We have our LinkStar D, which is our duplex radio, which provides a full duplex communication to the ground. It's not block, it's not data blocks, it's not large packets. It's a full, it treats your satellite as an internet. It gives you an IP address, you're on the internet, and you're fully communicating with our ground stations very transparently. If it loses that connection, it'll start where it left off and make sure your data is synchronized to the ground. It also provides an uplink capability, and we just did a test flight in December where we've been able to repurpose a satellite in space from our ground stations. We're able to upload files through this system and repurpose it to our hypervisor environment. The big thing we're excited about is our HD radio, Linkstar HD, which provides speeds of up to 256 kilobits. And that's, and it again provides or coverage around half the Earth. We'll talk more about this in a moment. And of course, you can tie in an S-band radio, an X-band, optical radios. We can play with other systems too within this framework. We also provide with this system an interface into a GPS. Our STX system, actually, when you get it, you do get a GPS that provides your position, and it's a lower cost unit, but you can use it on the ground, you can use it for testing, you can use it in space or near space. In the case of, we're a partner with Novatel, and we can bundle with the system, the Novatel 615 and the new 719 GPS, so you can use that in space in low Earth orbit, and in a fully space capable with these speed limits all removed from the system. You just plug it into the Linkstar architecture and notice, oh, I've got a GPS attached. Auburn's actually going a little bit further, and they're tying in with our APIs, which again automatically configures everything for you. It ties into the PRUs on the BeagleBone. They're working a timing scheme between the GPS and the PRUs on the BeagleBone flight computer. We are also working, starting this summer, on a project we're looking at funding, working with Naval Academy, where we're integrating the Maryland Aerospace 400 system. So if you get the Linkstar system and you have a Maryland Aerospace 400, we're thinking by this fall, Christmas, you drop it in, it'll automatically know it's a Maryland Aerospace system, and you can work from there. You don't have to do anything to configure your system. And of course, you can add other sensors, other actuators, however you want to do it. It's a fairly transparent system. We also have people who want to still work with Raspberry Pi, Edison, or other computers. This will network in with other computers, and if need be, we can adapt your computer. Instead of a BeagleBone, we can work with another computer if it's Linux-based and has a little flexibility in the system. The duplex radio, it's again no deployables on the system. It's a rapid acquisition. We get about, it runs about 9,600 baud. You're going to see other presentations on data rates. We've been able to get about 7,700 baud with the system. We have been able to upload files to the system about 1 megabyte within 12 minutes in the system, and we're able to synchronize data to the ground. So again, it's not sending packets. Your satellite is fully a node on the internet, and it's a secure encrypted connection to the ground sending your data into the system. You can use just the duplex radio. You can use your S-band or X-band or whatever radio with the duplex system. The HD system, the big difference there is it's using the same antenna, but it's running at 256 kilobits, so it's a much faster system. This will be coming out this summer. We're providing a bundle with Globalstar with their OEM unit, but we're also we're getting the processor for that system and building our own unique CubeSat baseboard. That system won't be ready, the CubeSat version won't be ready for about another year with all the certification we have to go. But the OEM system, we're looking to have this for the community this summer, going at 256 kilobits. And again, it'll treat your CubeSat as a node on the internet, which makes things really exciting. The big thing with the duplex and the high-speed duplex is we provide the FCC license. You don't have to deal with that. There's no amateur bands. You just tell us your mission. We get you all prepped and good to go. There's no ground stations. We provide, all you need is a laptop. So this is a really straightforward, simple architecture to work with. This is the coverage area. The red area is your basic area. It's a little bit bigger than that red area for the duplex. The area outside the red is the roaming, the very expensive stuff. Most people don't really go for that one. The simplex unit that we fly, it's a Generation 3 simplex, runs at only 350 milliwatts for a split second when it sends that packet out. Then it's running at like 200 microwatts. So it's a very low power system and provides global coverage. Now, I know some of you are dealing with flying simplex systems alone. FCC will not let you do that. But we do have a solution to let you fly your simplex radio with our architecture and to be able to get FCC approval to fly it with an uplink control for your simplex radio. It stacks on a beagle bone. When you put that right on the beagle bone, it knows automatically, I've got a simplex radio, and it will start broadcasting for you. It provides full coverage for UAVs in the US and nearly full coverage within planet Earth and LEO. I like to call this radio insurance policy. If you want to see if your satellite's working, if it's tumbling, you want to make sure things have deployed, you'll get that information. And again, it's near global coverage. And when I say global coverage, this map here, it's like the darker orangish area is the really good signal, and the light orange is not as good a signal, but you'll get that packet out there. This is a picture of the unit right here. The big difference is it's got an external attachment, so you can put external antennas on this. The baseline Globalstar model has the antenna attached to the board. Here, we're providing external antenna capability. It does work with the Novatel OEM 615 and 719, so it can beacon your satellite anywhere all over the Earth. And we provide also two mobile units that can be used on the ground. One with the antennas internally in it. So, both these units are designed to be used on a car, a boat, an airplane, a high-altitude balloon. All you have to do is apply power. It'll immediately know where it's at. It'll automatically set the channel, and it'll start beaconing data for you for this system here. If you're going to put this in space, just open up the case and pop it out. We also have a unit with the external antennas for both the GPS and their magnetic attachment antennas here. So really the differences on these three radios is power. One unit, the D, you're going 9600 baud, 256 kilobits with the HD. We have a special program where we have 4 participants now in this, where we provide a special deal with the data and the services, and then 36 byte packets minimum, or you can go about 36 bytes, so we can go up to 144 bytes with the STX3. All right, oops, gotta learn to point here. How's that? All right. Let me talk about the LinkStar X, because we're evolving this whole architecture. The BeagleBone's a very capable power space qualified system. But we're now working on our new platform where we're replacing the BeagleBone with the Xilinx MPSoC ultra-scale processor, which is an ARM53 processor married with the Xilinx FPGA. So now you have a higher powered system, so you can do maybe onboard image processing. This system's also designed to go into GEO, to the moon, to Jupiter. So this is a high-end or capable space-rated system. You can use it in LEO, and you can use it in LEO to do more processing on board that you wouldn't get with the BeagleBone or a Raspberry Pi and everything. It does support an onboard hypervisor, so you can provide secure, very quick snapshot, and of course you can talk to me afterwards back in the booth, or the booth that we have, but we provide a whole database architecture, communication tools. It has a core command architecture, but it's set up simply to add your own command architecture. You can write it in C, you can write it in Python, you can do it in assembly, but it will seamlessly let you add your commands to the system without we want to make sure you don't have to go in and change the code in the architecture. This is a very easy to use system here. This is another view, just bottom line, data goes from the ground to space, space back to ground here. We do provide encryption of your data through the system. And I know some satellites I've heard are also are running 1720, but very limited data rates. Not the LinkStar system. We give you a full data rate. We get your data securely to the ground. It's not packets. You're a full internet link to the ground, having 2 different databases talk to each other securely. This is some of the screenshots in the web interface. The baseline web interface on the satellite is exactly the same as the ground station. On the ground station, though, you can add your own LabVIEW interface, MATLAB interface, Mathematica, C, your own web, whatever, because you have access to that database here. This shows you the map view, and also we monitor your signal strength. Just like a cell phone, you have 1, 2, 3, 4 bars. We have the same thing. We track that for you, how strong your signal is and whether it's strong enough to send. This is a close view of that signal strength. And up there, you can see it shows the bars in the header area, and it can tell you if you've got a connection or no connection between the ground and your satellite. So we're trying to make this as simple as possible with your satellite. The LinkStar system does have a whole command architecture and tracks all command history between pending, processing, success, and fail. It does have a built-in software monitoring to track if your software is operating or failed. It has a full syslog that we track to the ground. That's all part of the architecture. We also track where you're located in the area here. So I'm going to go really quick. He's already taken the hook to me. So we got other missions coming up. We have a DARPA high-altitude flight at the end of May. North Dakota State is flying our duplex and simplex. We're integrating with NanoRacks in mid-May. And we have the RadSat mission with Boeing. They keep going out. New Mexico State's flying our system. Naval Academy, we're looking at NSAT-2 in 2019. Carthage College has the high definition, as does University of South Alabama, which we're really excited about. Also, Auburn University is flying 2 of these high-definition radios. So we're building this consortium of people using this software, and then we share it with the community here. So this triad mission, which you saw yesterday, very exciting. So that's our architecture. I think we have no time for questions, right? But you can reach me out the doors here if you have any questions. Thank you very much, everyone. I got to get a breath.
All right, and now please welcome Craig Clark from Clyde Space.
Hi, good afternoon, everyone. Great to be back at CubeSat Workshop again and to be in this fantastic new venue. Today, I'm going to give a short presentation about one of the new product developments that we've been doing in response to some of the kind of new applications that we have for CubeSats as that's rapidly expanding. So basically what we've been doing is working on a low noise power supply. So basically the reason for us doing this is because we're seeing a larger number of RF sensing missions coming through. So missions are looking for very kind of weak signals from the ground. So any noise on the bus is causing issues for missions that are really trying to listen carefully to what's these signals coming from ground. So maybe AIS, EDSB, different M2M applications in like Internet of Things. So there's when you've got a tiny spacecraft and you don't have a lot of power, you've got maybe smaller antennae, it's very difficult to hear these signals. So the power system is one of the biggest noise generating systems on board a spacecraft. So you've got a lot of switching converters and other things on there. So we spent a lot of time over the last 9 months in developing a new EPS for these specific applications. So if you know a little bit about Clyde Space, we actually started off about over 12 years ago now. We designed our first power system. That was where we started out. So we have 3 generations of power systems. We've built in the region of about, I mean, I've kind of lost count, of about 800 to 900 power systems for CubeSat. So we've got a lot of experience of making power systems for this type of mission. So on the screen here, you see a couple of them. This is one of the early, it's kind of generation 1, I actually think. Yeah, it's generation 1 CubeSat EPS. This is actually Gen 3. So this is kind of the latest one. So if you're buying a power system from us these days, it looks a bit more like that. So our latest one kind of doesn't look anything like that. It's looks more like a box, because as you would expect from a kind of a EMC clean power supply, it's enclosed. So I've got some pictures of the inside later on. But still, basically what we've done is taken our existing design, our kind of heritage design, and adapted it to be as low noise as we could possibly make it. So kind of building on the heritage we have, but obviously it's slightly different. This is a block diagram. It's a slightly complex block diagram of the system, but I can explain some of the things that we've done. I'll just take this off here so I can turn around. So it's still a system that is based on maximum power point tracking. So we interface to a range of solar panels. What we've done is designed this system so that because it's encapsulated, we've gone for a case where you've got lots of deployed panels on the CubeSat, or it's say a 6 or 12U CubeSat with lots of solar cells. So we actually have 8 13-watt battery charge regulators. So that's these guys here. So we've got line filters on the inputs. We have quite a lot of telemetry nodes on various points of the power system as we normally have. So array sensing is like voltage and current for each of the arrays. On each of the BCR lines, what we have is a common mode and differential mode filters on the input and output. And all of the BCRs are in separate boxes, so they're all shielded separately. On the other side of the BCRs, we have an end of charge circuit, so we have a centralized end of charge control. This system's compatible with the ISS launches, so we've got lots of inhibits built in as well. So a series of switches. These are all linked to solid-state switches on board. One of the differences with this power system compared to other ones is we don't have a 12-volt regulator, and the reason for that is we ran out of space. So in most missions that we come across don't really use the 12 volts. So we've still got 3 volts and 5 volts. But again, we've got common mode, differential mode filtering on input and output, both shielded. We have a telemetry interface here, which again is shielded as well. And then overcurrent protection on outputs to the main header. So that's basically what the block diagram looks like, and the system itself looks a bit like this. So you can see this is the inside of that box. So we've kind of got a shield around the shield as well. I mean, we've kind of went a bit nuts with shields, but I think because noise is such an issue from the magnetics in particular on power supplies, we've kind of gone belts and braces approach to making sure we don't have any radiated emissions coming from the power system. So this is actually the motherboard with the header on it. So we have on this board the switches for inhibits. We have the 2 regulators, the 5 and the 3.3, and we have the telemetry node for I2C here. Then we've got 8 BCRs, and they're all individually shielded, so they all kind of look the same. The main difference between these guys and our existing power supply products is that we've basically, I think, maybe times 4, times 5 the switching frequency. So the switching frequency of the BCRs is more like about 800 kilohertz, I think. So I think we've got that in the next slide. Yep. So actually the BCR is about 500 kilohertz, and our PCMs, the 3.3 and the 5 volt, are about 900 kilohertz. So one of the things we were concerned about by doing this is the efficiency of switching regulators can go down quite dramatically when you put the frequency up, because they used to be 100 and 200 kilohertz, but the problem with doing that is that a lot of your kind of harmonics will then lie exactly where you're trying to listen in certain frequencies, especially if you're like trying to listen for AIS signals or something like that. You have quite large harmonics along in those bands, so we had to shift our switching frequencies up to avoid landing within those regions. And when you're switching more, you have more switching losses, but we've actually, the impact wasn't as big as it could have been, because we actually made some gains elsewhere in the circuits. For example, our inductors are more efficient, they're less lossy. So we're sitting about 90% for the BCRs. We're still working on the other 2 systems. They're synchronous bucks, so they actually, on our existing product line, they're about 97% efficient. So we're still, that has come down a bit, but we're still working to make sure that we kind of maintain a very high efficiency with them as well. So some of this is a prototype. The unit you see there is, we've made 2 prototypes, so that's going through tests at the moment. So I haven't actually started production of the unit for flight yet. So some of the testing we've been doing is obviously around reliability, so doing kind of burn-in, thermal cycling, things like that. But of course, we're doing a lot of EMC testing. So some of our initial EMC testing comparisons against the previous product that we had are here. So this shows the noise floor at certain frequencies of interest for some of the applications that we're designing this for. So on the left is our 3rd generation EPS, so it doesn't have the shielding and doesn't have the input and output filter. So kind of sitting about, I think it's about minus 90 dBm. So we actually made significant improvements on the noise floor for the 162 megahertz range here, which was, you still have some spikes due to some of the harmonics due to the switching edges within the BCRs, but still a massive improvement on where we were. And on other frequencies such as the 865 megahertz, again, we've made like significant gains in terms of the noise floor generated there. So it's still a bit of a work in progress, but it's quite difficult to get the noise down on something that's switching. We've got about, well, 10 switching regulators and a tiny volume, so that's to get the noise to where we need it to be for these types of applications is actually quite challenging. So, but we're pretty happy with the results, and I think that our intention is to release this as a new product, so that if you're doing a mission that has like a very sensitive receiver on board, then this would be an option for you. But we're also looking at next generation platforms specifically for this type of mission, and kind of building that into that. So what I have is an example of one of these missions. So this is a mission that we're doing, which is based on an Internet of Things application. So it's got an antenna array on the bottom, and we've got triple deploy panels. From a power point of view, it's quite power hungry. But basically, the systems that kind of comprise of the bus include our OBC, the new EPS unit, battery. We've got an X-band at 100 megabits per second, ADCS with Star Tracker, and triple deploy panels, which is also a new development we've been working on at the moment. So that's actually the end of my presentation. It wasn't a very long presentation, so I think we've made up a bit of time. I think we're overrunning. But I just wanted to kind of like give an update of at least one of the new products that we're going through development at the moment. So thanks. Does anyone get any questions? Yeah, the question is related to why we selected those frequencies. So it's a bit of fine tuning. So the switching frequencies of the different regulators, we moved during testing because it's, theoretically, you're going to select a frequency that's going to then, your harmonics will avoid certain frequencies when you go higher. So we've had to kind of adjust some of the frequencies so that we, specifically around, the AIS and ADSB sort of ranges where you're most sensitive on the receivers, so that we can make sure the noise floor is as low as possible. So it's kind of fine-tuning the power supply so that you avoid the harmonics in those specific regions. So that's why we selected those specific frequencies. Oh, they're actual results, yeah. So that's conducted emissions on the lines. So, yeah. Any other questions? Nope. Okay, thanks very much.
Thank you, Craig. And now, please welcome Ryan Plochet from CubeSat.
All right, good afternoon. So this is the last talk of the day, and according to my phone, it is 4:36. The guys at the back told me I could take a whole hour if I wanted, so I hope you guys don't mind if I do that. My name is Ryan Plochet. I'm a software engineer for CubeSat. So today I would like to talk with you all a little bit about what we are building at CubeSat, what our motivation is behind what we're building. We'll get a little bit into the architecture of what we're building. We won't really go too much into technical details, keep it kind of high level so that we can get through this quick, get to dinner. Then we'll talk a little bit about why you should care about what we're building. So, the title of this presentation is Bringing Full Stack to Small Sats. The term full stack has been borrowed from the web world, where it refers to the software and infrastructure required to stand up a website or a web application. In this case, we're going to take the term full stack and apply it to the small sat world and take it to mean the layers of software that live between your satellite hardware and your end application. So whether that's your science experiment or your bits of business logic that you need, the things that really make your mission unique and that run your custom hardware, we'll call that your application. So those layers in between, your operating system, your middleware, things that may not be custom to your mission but are still necessary, those are the full stack components that Cubos is working on building out. So, why do this? Why build something new? We believe that software should be treated as a first-class citizen in this world. We are a software company, and that's all that we do is focus on software. We believe that by doing that, we can provide high-quality software, clean interfaces, hopefully easy-to-use development environments for you, the CubeSat developers, to enable you to do even more with your missions. We believe in the idea of vertical software integration, so owning all of the layers of software as well as we can, from the operating system all the way to the ground station, and making sure that those layers of software work really well together, that there aren't any problems, that integration goes smoothly. We're also working to achieve what we call horizontal hardware compatibility. So we are not tied to any specific vendor or bus. We want our software to run on as many buses as possible. So all the hardware that we can get our hands on, we would like to port our software to and make it so that it's easy for you, the CubeSat developer, to run our software on whichever bus that you choose to work with. So, how are we doing this? We'll start with a fairly high-level look at our architecture. So, on the left, which will be the top, we have the application. And again, this is the thing that makes your mission unique. Your science, your business, the reason that you're doing this mission. And that will live on top of this stack. Underneath that, we have a middleware layer. And this represents higher level software services that are specific to satellites, maybe not specific to your mission. They may be things that are used in multiple missions, but still specific to the satellite world. Things like command and control and telemetry. And below that, we have our portability layer. This is composed of multiple pieces of software. This is what allows us to run on multiple different buses, multiple vendors' hardware, things like your operating system and your hardware abstraction. So we're going to take a few minutes to dig into these layers, starting with the middleware. So this, again, is a pretty high-level picture of what a Cubos system could look like. In the middle, we have the Cubos layers of software. So telemetry and command and control are both middleware services. Then we have drivers, which are specific to a subsystem or a peripheral. Then we have the how, which will abstract away the physical interfaces that those devices are connected to. Then on the outside of this, we have our radio, ADCS, payload, EPS. These are all external data sources. So in this system, you might send a request to your radio for a snapshot of telemetry data. Your radio would relay that message to command and control, which would then ask telemetry like, hey, give me a snapshot of the latest data. Well, this whole time, telemetry has been retrieving data using drivers through the HAL from the ADCS, the payload, and the EPS, so collating that data, and then it would send it back through command and control, through the radio, back to you on the ground. In another scenario, maybe you want to reboot your satellite. So you would send a reboot message to the radio. This would be sent into command and control, which would then directly command the EPS, going through an EPS driver, through the HAL, directly to the hardware. So again, this is a pretty high-level picture, just kind of demonstrating what the data flow can look like and what message passing can look like in a system that is using layers of software created by Cubos. So these are our portability layers. These are the pieces of software that allow us to run on multiple different buses. So we'll start at the left, which on this slide is actually the bottom, not the top. So at the bottom, we have the operating system. So very base layer, we've chosen to work off of FreeRTOS and a distribution of Linux. This allows us to target smaller, more resource-constrained satellites, but also bigger satellites at the same time, using whichever operating system is more appropriate. So building on top of that, we have our OS abstraction layer. Right now, we're using a library called the CubeSat protocol, and that helps us to abstract away things like message passing through IPC, threading, timing, different OS primitives that tend to have fairly different interfaces. This allows us to create one kind of clean, uniform interface into those primitives that can be used in our software. And then building on top of that, we have our hardware abstraction layer. This allows us to create clean interfaces into physical device buses, things like your GPIO pins, your I2C bus, SPI bus, and your UART bus. So we're creating a clean, uniform interface that kind of looks and plays the same across all the hardware platforms and both the OSs. Obviously, there's some configuration that needs to be done in order to, set the right registers and all that, but we try our best to put that into configuration files that will be compiled away and to make it so that you don't have to think about that too much when you're writing your end application code. So, speaking of portability, here are some of the hardware platforms that we support right now. The first two are pretty cheap development platforms, the STM32F4 Discovery Board and the MSP430 Launchpad. These can be purchased by anyone for really cheap and can be used to tinker with the RTOS version of our software. We also support the Nano Avionics SatBus 3C1 with the RTOS, and then we are finishing up support for the ISIS IOVC with our Linux distribution. Kind of next on the list is the Pumpkin Supernova OBC, which will also be running our Linux distribution. Okay, development environment. This is really important to us because we think that programming should not be painful. We think software development should be less of a burden than it can be. So we try our best to create developer tools that make the process easier and try to remove any burdens that we can. What we do right now is we distribute, it's an SDK packaged up in a VM, and that VM contains a copy of our source code, a build system that we use, which is called Yada, the tool chains for the different platforms that we support, and also the flashing and debugging tools for the platforms that we support. So you download this one VM, it has all these tools in here. We have a nice Python command line interface to those tools. You don't need to worry about all these tool chains like polluting your system, which is like incredibly annoying to have tool chains and everything distributed across your main computer. So we have it all packaged up into one place, which makes it really easy to get to and really makes development much simpler. So why should you care about this? Why does this matter to you? Well, the CubeSat world seems to be pretty focused on making space more accessible, and we think that by making software more accessible, we can help further that mission. So we are trying to really lower the barrier of entry to satellite software. We want to try to empower y'all, give y'all back more time to innovate by removing the need to reinvent the same software things over and over again. So we want to give you pieces of software that we can reuse, so hopefully you can reclaim some of that time to work on the real science that your mission is about, or whatever it is that you actually want to be doing. And lastly, so I don't think I've mentioned this, but our software is all free, all open source. It's up on GitHub, and anyone can go and watch our development process. You can watch our pull request. Anyone is welcome to go comment on those things or even contribute to our code. So we believe that this level of transparency and collaboration with the greater CubeSat community, this is really what it will take in the future to build better software for satellites and just to build a better community around the software in the space. So that is all that I've got. Probably take a few questions now, or if anyone wants to grab dinner after this and chat about software, that would be great too. Dr. Brandon, I think I know what you're gonna ask. So yes, we're still using C. And why did we choose C? Yes, we've been through this before. So we're using C, honestly, because it's easy to find C developers. Most people know C. So how do we deal with the high error rate? Is your next question? Yep. Okay. So yes, C is definitely a difficult language to program in, difficult to get right, and that is an issue that we are actively wrestling with and trying to improve on. So one is enforcing peer code reviews. No code gets into our master branch unless at least one other person is checked off on it. Another way is trying to be active in integrating unit test and integration test into our source. I realize that's not a perfect solution, but that is how we're handling the problem right now. So you're asking if we agree that the MSP430 is a powerful? Yes, so we see the MSP430 probably as like the bottom that you would want to support, probably the least powerful. It's not our preferred platform, but we support it right now because we were working with someone and that was what they based their OVC off of. So you're asking on the MSP430, do we use TI's provided CCS Code Composer Studio? So no, we do not. All of our tool chains are open source. They're all GCC based. That is a really good question that I don't know that I'm qualified to answer. So I believe we have 2 missions coming up that we will be working with, but that is a better question for our biz dev person. I'm just a lowly engineer, right? I just work on the product. They don't talk to me about any of that stuff. All right.
Unfortunately, that's all the time we have for questions today.
All right, thank you.
Thank you, Ryan. So that was the last presentation of the day. Thank you all for coming. If anyone's looking for something to do tonight, from 6 to 9 downtown is the Farmers Market on Higuera Street. That's always a good time. Presentations will resume tomorrow at 9 a.m. And once again, thank you all for coming.